Data, data, and more data. Every time you scroll, shop, or stream, you're adding to a massive wave of information. But here's the real question: are we making the most out of this data, or just creating a never ending flood of information with no direction? Even world leaders recognize this challenge. The Prime Minister of India recently highlighted the growing data divide and stressed that high quality data is key to meaningful policy making. In simple terms, data isn't just numbers, it's the power. The power to drive businesses, transform industry, and shape the future. And that's exactly why data science is taking over the world. Companies today don't rely on gut feeling anymore. Every big decision is backed by data. Think about it. Netflix knows what you will binge next. Amazon predicts your next purchase even before you realize it. And businesses across finance, healthcare, and manufacturing are using data to work faster, smarter, and better. With all this happening, the demand for data science professionals is exploding. The US Bureau of Labor Statistics predict that data science job will grow by 36% from 2023 to 2033, making it one of the fastest growing careers. By 2026, over 11.5 million jobs will be up for grabs in this field. 97.2% of companies are already pouring investment into data and AI, and the industry is growing at an insane 24.7% annual rate. If these numbers excite you enough and you want to become a part of this growing field, we have created this course just for you. It will take you from a beginner to a skilled data science professional, covering everything from fundamentals to advanced machine learning and AI concepts. So ensure that you watch this entire course till it. Now let me take you guys through the agenda for this course.
First, we will start with an introduction to data science, understanding its key role in today's tech-driven world. We will then explore the connection between data science and machine learning, different types of data, and the key components of data science project to set a strong foundation. Next, we will clear the confusion between data science, machine learning, and AI before jumping into a real-world hard disk production project, applying the practical ML techniques. We will then deep dive into the types of machine learning, followed by mastering linear regression, where we will cover hypothesis gradient descent, its advantages, and how to evaluate regression models effectively. But that's not all. We will also see how linear regression can be used for classification and transition into the logistic regression for better insights. Then we will explore the decision trees and random forest, the powerful algorithms that improve the prediction accuracy. And guess what? You will also build a chatbot project applying everything that you have learned until now. Finally, we will wrap up with commonly asked data science interview questions, preparing you for real-world opportunities. By the end of this course, you won't just understand data science. You will be ready to apply it. So without further ado, let's get started.
Data science. In a world that is increasingly becoming a digital space, organizations deal with zettabytes and yottabytes of structured and unstructured data every day. Evolving technologies have enabled cost savings and smarter storage spaces to store critical data. Now, organizations can analyze this data to understand global market trends and enable their business to thrive. Data science can also predict future events based on the present and past data. Data science is a field of computer science that involves creating algorithms and models to extract, process, visualize, and find hidden patterns from the raw information. Data extraction and transformation, statistical analysis, data manipulation, visualization, machine learning, and predictive modeling are some of the most popular fields in computer science that utilize data science techniques. Every day, 2.5 quintillion bytes of data are generated, and it is more accelerated with the growth of IoT. This data comes from all possible sources, such as sensors used in shopping malls to gather shoppers' information, posts on social media platforms, digital pictures and videos captured on our phones, and purchase transactions made through e-commerce. Now this data is known as big data. Companies are flooded with colossal amounts of data. Thus, it is very important to know what to do with this exploding data and how to utilize it. Amazon needs data scientists to find out customer mindset and enhance the geographical reach of both e-commerce and cloud domains among other business-driven goals. Similarly, Visa is an online financial gateway for many companies. Visa does transactions worth hundreds and millions in a single day. Due to this, the need for data scientists is huge at Visa to generate more revenue, check fraudulent transactions, and customize products and services as per customer requirements, etc. Now we have 5 stages of data science life cycle. We have data discovery. It includes ways to discover data from various sources, which could be in an unstructured format like videos or images, or in a structured format like in text files, or it could be from relational database systems. Next stage we have is data preparation. It includes converting disparate data into a common format in order to work with it seamlessly. This process involves collecting clean data subsets and inserting suitable defaults, and it also can involve more complex methods like identifying missing values by modeling and so on. Third stage we have is mathematical models. These models are planned and built by the data scientist in order to suit the specific need of business organizations. Then we have getting things in action. Once the data is prepared and the models are built, it is time to get these models working in order to achieve the desired results. And the last stage we have is communication. The data scientists need to be liaison between various teams and should be able to seamlessly communicate his findings to key stakeholders and decision makers in the organizations so that actions can be taken based on the recommendations of the data scientist. In India, data analysts with 1 to 4 years of industry experience earn an average salary of 4,14,000 per year. Expert data analysts with experience of more than 10 years can earn 9 lakhs per year. In the USA, at the entry level, you can expect around 66,994 US dollars. A data analyst with 3 to 5 years of experience would take around $74,860, while an experienced data analyst with 10 plus years of experience would be around 83,673 US dollars.
The understanding of data science. And in this case, before moving forward to machine learning projects and algorithms, you need to have an idea that what way these algorithms work and how they are written, and some of the fundamentals of data set, how data set is applied to a machine learning algorithm, how that process is connected. We need to get an idea about that. So in that case, we will start to talk about those things. But before talking about anything in particular about machine learning, I just want to ask you, what do you think is the reason that everyone is suddenly running to data science? It's a very normal, it's a very general question. But what is the reason you think suddenly there is such a high boom of data science? Because if you see any other particular field, which is like web development, software development, those kind of things, Android development, or any particular programming language, when they came into the field of IT, they were not like this. They did not become suddenly popular. They were quite normal for maybe 7, 8 years, 10 years, and then they started to pick up pace. A lot of developments have happened into that. But that is not the case with data science. Data science just came in front of us, and it became such a huge, important topic that everyone is suddenly running towards it. And it is not that we are running towards it unnecessarily. It has a very important use case. It has become crucial nowadays to work with it. On the digitalization, that is one thing. Okay, will ChatGPT AI replace data science? See, that's a very common question that is running around, not in your minds, but in the minds of a lot of experts also who are working in the field of data science. Will ChatGPT or these kind of AI tools replace data scientists? For now, you can't say anything. And if someone says that no, nothing will happen to data scientists or nothing will happen to developers, that is also not correct. Because no one has currently any idea about what is going to happen 4 years, 5 years down the line. No one can say that. But what we have to do is you should be doing your best about what is there in front of you. So in front of you, there is an opportunity to become a data scientist. You should focus on that. Once you have become data scientist, if the industry is moving in a different direction, your skills are changing, so you can adopt to that. So that is what your idea should be. You can't know what is going to happen. If you think developers are replaced, data scientists are replaced, so what will you do? Okay, are you going to open up just a repairing shop? That is the idea, right? So you can't do that. So you should not be worried about what is going to happen with AI, what it will replace, what it will not replace. See, when internet came into the picture, it was creating same kind of problem. When internet came into the picture in 2001, 2002, when it became so popular that every shop, every business which was offline started to think that we are going to go extinct, and all the online businesses who understand internet, they are going to uh, get a lot of profit out of that. That happened for quite some time. The people who were not following digitization, those who did not want to learn internet, they were left behind for some time. But again, when they started to pick up pace, when internet became very easy, very accessible, everyone grew. Not just one or two people, everyone grew. So very similar to that with AI also, that is what is going to happen. So when AI will come, it is not going to happen that it will just remove everything, every job from the market. It is going to modify the way things are happening. See, mainly it will modify all the normal tasks which people are doing, which does not require our intelligence. Okay, we are doing a lot of tasks in IT also. You would see day-to-day tasks, similar tasks we are repeating on everyday basis, and that we are doing very slow. So if that is handled by the AI, it can do much faster, and we will be left with, or we will be forced to uh, put our effort to something where our intelligence is applied, where our critical thinking, where our decision making is applied properly. Okay, so that is going to happen, and it is not going to be bad as everyone is thinking. Something good will come out of it, because obviously everyone is not going to lose their job. Everyone is not going to be jobless. That will create a very bad structure, right? That cannot happen. Yes, it will increase different kind of job. It will just make some jobs which you can't think for now that might exist, but it's not going to happen that there will not be jobs or something like that. You should make the best out of what you have in front of you, and let's see what happens in the future. Now, so we were talking about data science. So starting with the topic that why suddenly there is a requirement of data science is because of this. See, there are mainly two type of data. There is a types of data. And what are the types of data? One is structured data and one is unstructured data. Okay, unstructured data. These are two types of data which we have currently in the market, which we deal with. Now, what is unstructured data? Structured data and unstructured data. That is mainly the two type of data we have. Now, in the case of structured data, what we have, the data in tabular format. Tabular form of data. What do we have in unstructured case? We have images, we have videos, we have text, we have audio. Okay, so these kind of thing you can see. And there are other files also, other type of data also, like the data collected from your smartwatches. Those are stored in log files. Okay, so IoT devices which are there, smart sensors which are there. So they all collect some data which are collected in format which is not structured. So now, when you take a look at this type of data, there are two structured and unstructured. See, for a very long time, this type of data was there in the market. And to work on this type of data, one very powerful tool was Excel, Microsoft Excel. And a lot of information could be gathered by working on this structured data. And also this structured data was in the format of databases. SQL databases you have already studied, you might have. So that is a form of structured data because it is in tabular format, rows and columns, everything like that. So that was being handled for quite some time. But suddenly what happened? After the year 2010, when Instagram was launched, okay, Facebook was launched quite long ago, and there were other social networking websites in different part of the world. So when this Instagram launched, then what happened? Suddenly, it was such a easy to use, you can say, application, which gained popularity very fast. So when Instagram started to gain popularity, the other social networking websites or applications like Facebook, Orkut, and Reddit, all the other applications which were there, they also started to take a boom. They also started to increase their number of users and the platform, and sharing of the images, sharing of the videos, like, dislikes, following each other, those kind of information started to flow on the company server. So now what Instagram was collecting, Instagram was collecting a lot of images, videos, text, audio, those kind of information about every other people. Okay. Now, we have this 2010, this thing started to happen, and a lot of unstructured data started to came into the picture. Just take a look at this. Just take a look at this image for now. What is this image talking about? Is what happens in 1 minute in 2021. Okay, 2021. What happened in just one single minute on the internet? If you take a look at any of these images, what we are talking about is the amount of information, amount of activity that happened for different websites and applications. So if you look at it, Twitter users post 575K tweets. Now, what are tweets? Tweets are in the format of a text. Okay, 575K tweets. That is what happened on Twitter in just one single minute in 2021. Now you can think how many minutes were there in a whole year. In Instagram, in just 1 minute, 65,000 photos were shared. On Facebook, 240,000 photos were shared, 240K photos were shared in just one single minute. So very similar to that, TikTok users watch this much video. Facebook got this much live views. So very similar to that, different platforms. If you look at them, how much of a data is traveling, how much activity is happening in just one single minute. So now, when you talk about such kind of data, which is in image format, audio format, text format, video format, these are all under unstructured data, because videos are not having any structure. Structure means they should have rows, column, proper structure to that, a tabular format. So this is obviously the audio does not have any structure, or the video does not have any structure, text does not have any structure. So this is mainly the unstructured data. Now, if there was structured data, then people would be able to do something with it, or find some kind of answers with it. But when unstructured data comes into picture, there is no tool apart from data science which can deal with it. Maybe one or two things you can find out, but it is observed that when you have unstructured data, you can't do anything with that if you're not using data science. So data science is one single solution, and the only solution available that can do so many things with it. So I'm not just talking about analyzing that unstructured data. I'm talking about also using it for prediction purpose, for predictive analytics, those kind of things. See, when you go to the deep learning topic, you will see that a video or image will be broken down into NumPy arrays. Okay, any video or any images will be broken down into some format like NumPy arrays and everything. But by itself, when you take a look at a video, it is not structured. When you take a look at a raw video, when you process it, when you convert it into different type of information, then you might make it structured. But as you look at it raw, it is not structured. So that is the thing. Different type of information you're going to get later. That is the main reason. So in total, we were talking about why do we suddenly require data science is because of this reason. So if you understand about this scale, how massively amount of data that is being collected every single minute, so you can understand what is happening in a year. If this much videos, if this much photos were shared in just one single minute, so a lot of data. Now, what companies have to do? The companies have to find a way to utilize this information to understand the information from a text, from a video, from an image, to be able to serve the customers better, to be able to bring new products which can increase the engagement on their platform. Otherwise, they will lose the market, they will lose the customer to any other new platform. That is the main issue about it. Also, when we talk about unstructured data, it is around 80%. Okay. Out of all the data which a company is collecting on their server, 80% of the data is in unstructured format in for most of the companies. 80%. So you think that if the company started to neglect the unstructured data, if they don't find a way to work with this unstructured data, they just have the option to work with 20% of the remaining data, and that also they might not utilize properly the complete 20%. So that is the reason why suddenly there is a requirement of data science, and that too very critically. Every company has to find a way to implement data science into their product, into their company culture, so that they can properly take advantage of all of these things which are flowing through, all the data which is unstructured. Correct? Because when they study this data, they find out a proper information about what kind of product should be created, what users are liking, what they are not liking. So, informed decision, a proper decision they can make when they study data. And when data tells something, it is in most of the cases, it is correct, because data does not lie. Data is what it is simply telling you the behavior of the customer. Okay. So that is the thing. Now that is the basic idea because of which suddenly there is a form of data science. Now let's move forward into the technical details of it. Okay, technical details of it. So data science we have understood. Now, if you are going to work as a data scientist, what are the things you are going to do? What is the process you are going to follow to make a data science project? Components of a data. Speaking at the similar pace, similar loudness. Now, so let's see the components of a data science project. So when you go to industry, you will be making data science projects. And what it is? So data science project is nothing but a process of few steps combined. Okay, it's a process. What happens in that process is this. If you take a look at the first step in the data science project, do you know what happens? What is the first step that you will perform when you're trying to solve a data science problem? Where will you start? What is the first thing you should know before starting a data science project? Okay, I got one answer. Purpose, then data, cleaning the data, importing the data. Bala, are you going to do cleaning of the data directly? You should first import it, right? Before that, obviously. Read the data, objective of the study, collecting the data. Okay. So before starting any data science project, what happens is if you pick up any project, okay, whatever type of projects you're going to work on, that is essentially going to solve a problem of a business. Okay, you don't randomly make a data science project. It will be created specifically to solve a problem that a company is facing. And they want to find out whether we are going in the correct direction or wrong direction, or what should we do that will be correct. So to solve a problem of a company, what is the first thing that you should be is you should have a proper understanding of the problem statement. So that is the first step. Where are you going to start? Understanding the problem statement. Very first problem. Before even collecting the data, reading the data, importing the data, anything of that, what is the first thing required? Understanding the problem statement. So understanding the problem statement is very important because when you go for collection of the data, then what will happen is you will have too much data to collect. But you should be specific about what is important in all of that data and what is not important for you. If you unnecessarily collect a lot of data, or you're wasting a lot of time to collect the data, which is not necessary in the further approaches. So you're wasting time. And what type of data should I collect and how much data should I collect? You will be clear about that once you are clear with the problem statement. That what exactly is the problem faced by the company that we are trying to solve. So before starting anything, this is the most important step that you as a data scientist have to follow. Most important. If you mess this up, if you don't understand this problem statement properly, either you're going to waste a lot of time to complete the project, or whatever you create is not going to be helpful for the company. So you can't mess on this one. And to understand the problem statement, a proper documentation will be given to you. It will be created by someone in the company, and that will be given to you. You have to study the problem statement. In some of the cases, you have to sit down with the other teams of data scientists, data analysts, business analysts to create the problem statement properly. That way, there will be a proper documentation. Now, so once you have understood the problem statement, what is the second task that you perform is you collect the data. You go to the internet to do the data collection. Now, data collection will be done in the different formats. You will have Excel file, you will have CSV files, you will have text files, you'll have JSON files, you'll have images. I'm talking about all structured and unstructured because a business problem can consist of different type of information. Okay, different type of data might be required for that. Databases, etc. These kind of things are you going to collect. Okay, .SQL files, correct. So that is what the second step would be, to do the data collection. After the data collection is done, what is the third step that you're going to follow? Third step comes to be processing and cleaning the data. Okay, processing and cleaning the data would be the third step. How would you perform this process? That is mainly done with NumPy and pandas. You will do this with Excel also, sometime with SQL also. But in the case of Python, if I'm talking about, you will be following the process, or you will be following these packages, NumPy and pandas for that. And we have understood few of the process. Few more things will be taught to you when you go to a process called as exploratory data analysis. You'll be studying about that when you study the advanced statistics after that. So once you have got an idea about the cleaning of the data, then you move forward to explore and visualize the data. Okay, after cleaning the data, your main exploration of this process starts. In exploration, what you do, you try to understand the relationships. Okay, relationships in the data. Then the next thing you would have is relationships in the data, and can say behavior of the data. Behavior of the data means the distribution and outlier kind of things you will try to find out. And how do you explore and visualize the data? You do that with NumPy, pandas, and visualization. That is the kind of thing you are going to do. So after the fourth step, what process comes up is you bring in now, apply the machine learning algorithms. Okay. After applying machine learning algorithm, the sixth step is test the performance of ML models. What is ML models? Just will explain in few minutes. then tuning the ML models. Okay, so with fifth step, you are applying the machine learning algorithm. Then you test the performance of that machine learning model that you have created. So what is machine learning model is nothing but when you apply data set with a machine learning algorithm. Data set plus machine learning algorithm. When you combine that, when the learning has happened, that is called a machine learning model. So when you create a machine learning model, you have to test the performance, you have to test the accuracy of it. Because whatever ML model you create, it will not be 100% accurate. It is not going to happen in the real world. Never. So the main thing is what you can do. You can achieve the best you can get. That is what your task is to do. Okay. Machine learning algorithm, I'll talk about it. These are mathematical algorithms, the machine learning algorithms. There is some mathematical formula which is going to work through something and it is going to give the prediction on a data set. Okay. So we will talk about it. What is this algorithm all about? And then the last step is present the result. Okay. So these are few steps which you are going to perform. Understanding the problem statement, collect the data, process and clean the data, explore and visualize the data. And after that, you bring in the predictive part where you apply the machine learning algorithm, test the performance, tune the performance, and present the result. Now, when you talk about this machine learning algorithm, these algorithms are nothing but some mathematical formula, which is going to help us do future predictions on a data set. So when you apply data set plus machine learning algorithm, you get ML models. And the performance of ML models or the prediction capability of any ML model will not be 100%. Okay. What is the work of ML? Machine learning, you all will know, must have heard about it, that it predicts the future outcome for you. So it is not going to be 100% accurate. So how can we make it 100% accurate? We first need to check the performance. How accurate is it when I have applied it to my data set? Let's say it is 80%, but you want that it should be at least 93%, at least 92%. So what you will do in that case, you will tune the performance of the ML model. You will try to increase it somehow. Processes, we will be talking about that. See, I'm going to come with it. It is not something I'm going to explain. I'm just talking about overview. I'm just giving you overview that how do we test the performance of the model. Those are technical terms. We will see when we come to that. Then we will present the results. After we have tuned the model, after we have got a very good prediction capability, so we will predict the future outcome and then we have to present the results. Present the result of what? Presenting the result of what is the problem we are trying to solve. Okay. So a problem was given to me at the start. We worked on that problem, and at the end, we are going to get something which is going to be a solution to that problem. So once we have reached that solution, we need to present it because the people who asked for this, they may be the CEOs, they may be the managers who don't have technical knowledge. So you can't show them the Jupyter notebook directly and say them to study this. So you should have created dashboards, you should have created presentations, you should have created the visualizations to show them in most of the visual way what you have found out and what is your suggestion about this problem. How can we solve it? So you will have to present it by creating presentations and dashboards of whatever you were creating. So that is the basic of it. Now, how ML, data science, and these kind of things are related. Let's see an example of that also. So I think these 8 steps are clear to all of you. Basic idea. We will dive deep into all of this, but for now, we will have to understand just the basic. That these are 8 steps which are followed. Correct? Now, just to show you what way they are related, I'm going to discuss about it. This image will make it little clear. So you all have heard about what data science, machine learning, deep learning, AI. These kind of things you have heard, or data analysis. Now, what is the relationship between them is this. Now, AI is one big box, you can say, or one big skill inside which there is a skill of machine learning, and inside machine learning there is a skill of deep learning. So this deep learning that you're seeing is nothing but it is called advanced machine learning. Okay, advanced machine learning. What happens in this deep learning is we try to mimic our brain. The human brain has neurons. Okay, and the use of with the use of neurons, the prediction, the understanding, the learning, the decision making happens by the humans. So that same structure is being followed to create something called as deep learning algorithm. And if these deep learning algorithms are created in a proper way, they can become as powerful as humans. So all the things which you are seeing in current times, all the chat GPT and everything is created with this deep learning technique. This is the most powerful system that you can get, and with that you can create any powerful thing that you are seeing in front of you. Okay, you can give the human based capabilities to a machine using this deep learning. Now this deep learning is nothing but advanced machine learning, as I told you. So deep learning, ML, are a part of AI. When you have the skill of deep learning, when you have the skill of machine learning, you learn few extra things which are AI algorithms, AI based few algorithms. When you learn these three things, you will become AI engineer. So no one becomes AI engineer directly. You become AI engineer after working for 5 to 10 years of experience. When you get, then you start to work on AI. AI is a very, very complicated or a very advanced system which you can't understand as a fresher at all. A lot of mathematical knowledge is required, a lot of research knowledge is required. You should be able to understand and read the research papers which are created by the PhD candidates. Then only you will be able to understand what AI can do. But you can learn the fundamentals of machine learning, you can learn the fundamentals of deep learning. You start working, you get the industry experience, then after quite some time you move into AI. And also not every company will give you a chance to work on AI. Very few companies are there, okay, which are working on this. And there comes data science. So data science is nothing but it is a combination of data analysis. Okay, it's a combination of data analysis plus machine learning. So when you take data analysis and when you apply machine learning together on it, both the things together, then you create something called as data science. So what data science has done, actually this data analysis part was very separate, and this machine learning field, this machine learning world was very different. They were completely separated from each other. So data science has somehow found a tool, it has somehow found a process through which the data analysis and the machine learning, two different and two very powerful fields, could be combined together to get a very powerful result. That is what data science is all about. With the advent of data science, the use of mathematics, the use of statistics, which were quite neglected in the IT field, they started to come in the picture. It was not completely neglected, but when you work on software development, as a software engineer, when you become, you have to understand a lot of math to understand data structures, algorithm, and proper coding techniques. You have to have a knowledge of maths. So, but it was not very in depth, and also statistics was not something which was used at all. Okay, maybe very few people who were specifically the statistical developers, researchers, they were working with it. But a lot of people, a lot of developers were not even talking about statistics. But it was found to be very powerful because it can give a lot of information from the data in a very easy to use manner without even going through the effort of making projects and everything. You can just look at the data, apply the statistical knowledge to it, and on the theoretical basis itself, you can get a lot of information. So these two things were combined and you got what you know as a data science. So when you learn data science, you can become a ML engineer also, and you can become data analysis analyst also. You can become business analyst also. You can become deep learning engineer also. There are multiple aspects to it. Okay. So what you're going to use out of them, ML or DL more? It depends upon company to company. Whatever task a company is doing, according to that task, you will be either using machine learning more or you will be using deep learning more. But actually, in most of the cases, you will be using machine learning. Deep learning is a very specific and it's a very advanced task, which is not required in most of the cases which a company is trying to do. That is the whole structure. So we have got some idea. Let's try to understand a little bit more about it. Yes, let's see a little bit more. So when you take a look at it, wait for a few minutes and I'm going to talk about a lot of things. Data analysis plus machine learning. Now, what is this data analysis? When you talk about data analysis, it is nothing but a study of past data. Data analysis is nothing but study of past data. All the past data which was collected by the company, you study that to find out the trend, to find out the behavior of the customers in the past. That is what data analysis is all about. And for working with data analysis, what are the tools required? Currently, if you go to industry, you will be using Python, you'll be using SQL, you'll be using Excel, you'll be using W/Power BI. These are the main tools of data analysis, these things. And what we do with machine learning, when we have studied the past data, and now we want to predict the future outcome. See, whenever something happens, whenever prediction capabilities are to be applied, how do you predict the future? If you are a human and you have to predict the future outcome, then what happens is you should know about past. If you are just born, if you were born and you are just of the age of 5 years, 6 years, 7 years, 8 years, can you predict something of the future? No, you don't predict at that time. But when you become adult, when you are 14 years of age, 15 years, 18 years, 20 years, so in that case, what happens is you understand a lot about the past. Okay, you have been through a lot of things, you have understood a lot of things. So when you have understood the past world, past scenarios of the world, then you can make a prediction about the future, that this is going to happen, this is going to happen. And in that case also, maybe you are correct, maybe you're not correct. But what are you doing? You are making a prediction based on the best of your knowledge. That same thing happens with the data science also. That when you talk about these two things, this data science, data analysis plus machine learning is what create data science. And in data science, you have both the things, study of the past data and predicting the future out. Okay, predicting the future out. That is the next step. Now, that is the whole thing happening. Now, if you go to industry, you will see these things happen. First, they will study the past data. That will be done by data analyst, business analyst. They will work on these things. And then there will be prediction of the future outcomes to be done. But that is also not every time. See, there will be many projects. If you're a data scientist, you will have to do most of the tasks of data analysis. Just data analysis you did, and there was no requirement of applying machine learning to that, so you did not apply. It is not going to happen that if you are a data scientist, every time you will work with machine learning, every time you will work with deep learning. It may not happen. So just with statistical analysis, you might solve a problem. Just with proper use of SQL and Excel, you solve a problem. So it depends upon problem to problem. It depends upon the task at hand, which is required. You take the certain steps. That is what happens in this. Now the Hadoop and R you are talking about, R is a different, yeah, you can say that R is alternative of Python. But R is not being used a lot in the industry. Python is used by 95 to 96% of the companies, and R is used by 4 to 5% of the companies. So if you want, if your company requires R, you can learn that later. But as a proper bet, you should be learning Python, because mostly you're going to work for a company which is going to use Python in most of the cases. Why Python is so popular that it has taken 95% market share is because of the availability of the packages. The NumPy, Pandas, visualization libraries, the visualization libraries that we see, these are what gives advantage to Python. These things are not there in R. So in R, you will have to write a big code, a lot of code that is done easily in 1 or 2 lines in Python. So what we do as a machine learning engineer, we understood that when I'm creating a machine learning model, when I'm trying to apply a predictive capability to something, what I'm doing in that case, I am going to teach that machine the past data, that this thing happened in the past. Now predict the future for me. Let us understand that with an example to get an idea about it, proper idea. Then we will talk about the other things. So I'll talk about example. And this example, let's see heart disease. But to understand ML algorithms, you should have an idea about what actually happens in machine learning field. What are the steps you take? What are the processes you perform? So let us work with an example to understand what exactly I'm talking about. So let us say I have to predict heart disease of patient. Which patient has heart disease? Which patient does not have heart disease? That I have to predict. Now I don't know. These are very new patients that have come to me, and I have to just look at the conditions of the patient, and I have to find out whether this patient is going to have heart disease or not. So in that case, what will happen? I'm going to talk about that. Let's say these are some of the medical conditions. I have age, I have chest pain level, I have sugar level, and I have info about blood pressure. And let's say I have info about cholesterol. And then what I have is the output column. Okay, output. Now, what are these things? These are medical conditions of the patient that you're going to collect. And once you have collected these medical conditions, you are going to see the output of it. Which patient has heart disease? Which patient does not have heart disease? Yes, you can take obesity, weight, a lot of things are there. I'm just showing you an example. That when you do data collection, how do you know what is required, what is not required? So let us suppose this is the data you're going to collect from the past patient. How do you predict the future patient? Which patient is going to have heart disease or which patient is not going to have heart disease? You will study the past patient. So when you study few past patients, what you know is that there's a patient of age 32, patient of age 35, patient of age, let's say 27, 45, 38. These are the age of the patient. Let's say chest pain level I'm talking about. So let's say a person has chest pain of level 5. Someone has level 1. Someone has level 3. Someone has level 2. Someone has level 4. Let's say sugar level. I don't know what is the number of diabetes, what is good, what is bad. But let us just assume there are some numbers which talk about severity. The higher the number, the higher the sugar level in that patient. The lower it is, the better it is. So blood pressure, let's say low, high, low, high. And cholesterol level of the patient was 45, 65, 78, 44, and 15. What is this? I'm talking about past patient. So this patient with age 32, chest pain level 5, sugar level this, blood pressure level low, and cholesterol of 45 was found to be having heart disease. Just as an example, don't go into technicals of it, that it should be yes, it shouldn't be no. I'm just saying that this patient was found to be yes, this patient was found to be no, patient was found to be yes, and this patient was found to be yes. This is the past data. So once you have studied past data, you will study very similar like that. You will study 5,000 patients, 10,000 patients in the past who had heart disease. In different hospitals, these data are collected. So you're going to study that data. Once you have studied that data, what are you trying to understand? That if a person has this around an age of 32, if that person has just been around a 4 or 5, sugar level of around this much, blood pressure low, cholesterol level of 45 to 50, then what is going to happen with that patient? Was he suffering from uh, heart disease or not? That we are going to understand from the past patient. So this is the data set, and this is the data set about the past patient. We have understood it. Let's say our machine learning has learned the pattern, understood the pattern. After that, what is going to happen? You will apply that machine learning for future prediction. So let's say you take a new patient and you collect the data about that. So a new patient comes up whose age is 33, chest pain level is 4, and this sugar level is 125, and then the blood pressure level is high, and the cholesterol level is, let's say, 72. This is about a new patient I'm talking about. So is this patient going to have heart disease and not heart disease? Then what is the case? So from the past data, my machine learning has learned that it is yes or it is no. Only these two answers my machine learning is going to give. So let us suppose for these medical conditions, for these conditions of the patient, we found out that it is yes. That this person whose medical condition currently is this is going to have heart disease in the future. Once you have identified it, what you can do, you can now put that patient into proper treatment. You can suggest proper medicines, proper treatment to them so that they are not going to face this problem in the future. What can happen in this case? Let us say you are collecting the same data for 100 patients. Okay, same data you are collecting for 100 patients. So out of 100 patients, what your machine learning will do? Somewhere it will classify or it will predict correct. Somewhere it will not predict correct. So let us say out of 100 patients, 80 patients it has predicted correctly. Predicted correctly means the person who was supposed to uh, happen or supposed to suffer from heart disease, it predicted them to have heart disease correctly. But in the second case, 20 patients, they were found to have heart disease later, but my machine learning has predicted them to not have heart disease. So that is incorrect predictions. Okay, predicted incorrectly. Also, what way you can predict incorrectly? So if a person is having heart disease, the opposite of that. A person was not supposed to have heart disease, but you predicted that this person is going to have heart disease, and they go undergo the medical treatment unnecessarily. It was not required. So it is the case that around out of 100 patients which I taken in the future, 80 were predicted correctly and 20 were predicted incorrectly. Correct. So whenever you do incorrect predictions, then what happens? This is going to be the performance of the model. Okay. How many times it is accurate in how many cases, that becomes performance of the ML model. ML model. And it is going to be 80%. Why 80%? Because it is able to correctly predict 80% of the times and it is not able to predict 20% of the time. So that will become the performance of the model. Now you tell me, taking a look at this scenario, taking a look at this problem that we are trying to solve, is 80% good performance or good accuracy or is it very bad and we should be improving it definitely? What do you think? Is it good? Will you take that as a good prediction or bad prediction? Taking a look at this question, I'm not talking about in general 80% is good or not. I'm talking about specifically this question, which is talking about medical conditions. It is terrible for healthcare. That is the correct answer. When you take a look at 80%, you would think that it is good. Okay, 80% feels to be a very good number. But when you talk about such a critical case where healthcare is being discussed about, so when you go to industry, you will see that in healthcare, in most of the cases, at least 95% accuracy is required. At least I'm saying that is also a very bad accuracy. You would be aiming to achieve 99% accuracy, 99.5% accuracy. These are the kind of accuracy you have to achieve, because this is human life you're talking about. This is healthcare you're talking about. You're not talking about a general prediction scenario. If I'm trying to predict any other thing, that uh, this person is going to purchase this in a e-commerce market, or when a person goes to a website, they will purchase this, they will not purchase this. There you can predict something wrong, there you can predict something correct. You're not going to lose a life. You will lose maybe few revenue, or some time will be wasted, but you can correct it later. But in this cases, when you're working on such a thing, before bringing this model to the real world to be used in healthcare industry, in the hospitals, you should achieve to get uh, like 99% accuracy, 98% accuracy. That is what that is going to happen. Okay, talking about specific domain, it is not that you don't see money in healthcare sector. It is a very different thing. What we are talking about, we're not talking about money. We are talking about if a patient has come to the hospital, they have come with a thinking that whatever will happen will be best for us. Okay, they are thinking that whatever doctors are going to predict, in that case it will be good, it will be very good for us. But if doctors are predicting something incorrect, then what is happening, that is a disaster for the patient. Okay, they lose their trust, and obviously their loss is happening in the health sector. So that is one thing they have to get an idea about. So that is the performance of the model. Now, when you talk about performance of the model, suppose when you have taken a data set, when you applied that data set for the prediction purpose, you got this much as the performance of that particular model. So what you have to do in this case, you need to improve it before launching it into the real world. So now what is going to happen? You are going to tune this. Tuning means you are going to do some processes, you are going to apply some procedures. We will talk about them to increase the performance from 80% to 90%, then to 95%, then to 98, 99%. You have to increase it. So how do you increase the performance of the model? Let us see. When you talk about machine learning algorithm plus data set, that is what I'm terming as machine learning model. This is the terminology that you should not forget. Machine learning model. So when you hear about this machine learning model, it is not about any algorithm. It is talking about you pick a certain algorithm, you apply it to a data set, and you get a machine learning model. Now with this machine learning model, you predict the future out with this. Because what you have done when you did this process, when you took a data set and when you combined with the algorithm, you're learning. You're making that machine learning learn the patterns from the data set. So here your machine learning happens, the term that you hear, and it creates something called as machine learning model in technical terms. Now this machine learning model can be very good, can be not good, or can be very good, very bad. So how do you improve it? If you have to increase the performance, or if you have to improve the performance of the model, how will you improve it? Like let's say in our case, we got the performance of 80%. So if I want to improve the performance, there are two options available to me. What are the two models? I do something in this algorithm. something I try to change in the same algorithm. Or second case is I replace this algorithm with another one. In the field of machine learning, there is not just a single algorithm that is going to help you for prediction purpose. There are more than 20 very good algorithms, very powerful algorithms that you can apply. So out of 20, based upon the problem statement, based upon the task you're trying to solve, you will pick one. If one is not working well, you pick the second one. Second is not working well, you pick the third one. So like that, you're going to try multiple algorithms. If by changing algorithm you're not seeing much of the improvement, what is the next option? Maybe you need to take more data. Maybe something is missing in that data, something more is required, or you're taking unnecessary data in those cases. Correct? So data is not accurate or adequate or enough, you can say. So these are mainly three options. You try to improve the current algorithm, you replace that algorithm with the next one, or you increase the data, or you try to modify the data that you have. These are the only three options using which you can improve the performance of a model, the accuracy, the prediction capabilities. That is what we are talking about. So now you're getting some idea that what we do in this case. Sahil, we will talk about that. There are functions, there are code that we will write to find out accuracy. We will take the data, we will do everything. That is, we will have to do. When we start, I will show you what are the code you need to write, what are the functions there, how things happen, that we will see. Okay, so third step is you take more data. Maybe your data is not enough, or maybe your data is not accurate. So you should be changing the data. Maybe you have taken too many columns, and out of that, let's say a data set you have taken which is having 80 columns. 80 columns was not required. Let's say 19 of them is bad. They are not helping for the prediction. So you remove that 90 and you take the rest 61 of them and use it. So those kind of things you will understand once you're solving the problem firsthand. You get that with practice, you get that with experimentation, you'll get that idea. There's no single step that this is bad, this is good. It depends upon domain, it depends upon data. That is what you're going to do. So we have understood till now. I think you have all got the idea what we are talking about. Let's see a few more things to make a better understanding of these ideas that we are taking. So there are two things. One is software development, and the second thing is ML. What you do in ML. So when you talk about software development, okay, software development, what happens in that? What you generally do is you have input, okay, and then you write code for that input to generate some output. This is not a very technical definition, but that is an overview of what happens on software development. You have some input that what are the features you want to have for a website, what are the things it can do, what are the things it can't do. You have some input and then you write a code to get a certain output. So software development is this thing. You have some input that this is what you want to create, and by taking the input you write the code to generate a certain output, that this is what we want to have. Now what happens in ML is little different from that. Okay, ML is little different from that. What happens in ML is you have input with you and you have output with you. Okay, you have input with you and you have output with you. And what you do, you give that input and output to ML algo, machine learning algorithms. You give it to that. What machine learning algorithm will do, it will create the code for us. This code that we were writing in the previous case. In the case of machine learning, it will create that code for us. Not exactly like Python code or Java code. It will be in the format of a mathematical functions. Okay, but in the layman term, you can say that it writes the code for us to understand it better. but it will be a mathematical function, because any of the machine learning algorithm are created by mathematicians. It was not created by computer scientists. So whatever output you're going to generate will be in the format of mathematical functions, formulas like that. And using those functions, what are we going to do? We are going to make predictions. Just to show you an example of how that function will look like, we will be studying about our first algorithm, which will be linear regression algorithm. So let's suppose I have some input, I have some output. Let us suppose I am trying to solve a house price prediction problem. House price prediction problem. So now in this case, let us say I have the input, the past input, I have the past output, that these are the features of the house, and then this is the price of the house. I have the past input, past output. I give that to machine learning algorithm to learn the pattern. And after learning the pattern, it will create a code, it will create a mathematical function for us. And using this function, we can make prediction. So let's see how. So the function that it will create in that case for house price prediction, it will be in the format of this. Beta naught plus beta 1 into x. What is x here? This x that you're seeing, beta 1, beta naught plus beta 1 into x. That is what it is. This is a function. What can we do with this function? This x is nothing but some input. What input? Future input, not the past input. So we have given past input and we have given past output for our machine learning to learn that by having this, there are 3 floors, 4 bedroom, 1 bathroom, and this much is the land size, this much is the, you can say, area given to it. So does it have balcony? Does it have terrace? Different inputs are there, particular features about the house. And then you know the output of the house, means the price of the past houses. Then you give it to ML algo, then you will give it to code and function. It will create code and function for you. And it will be in this form, beta naught plus beta 1 into x. Now what we have to do with our ML linear regression, we will have to find out certain values for beta naught and beta 1. We will see more in detail. But let us say the value of beta naught is what? 5. We have found it out. We have to search for it. And let us say the beta 1 value is 1.8. Now what we have to do with it is, once we have got the answer of beta naught and beta 1, and then there is a x. X is what? Future input. Let us say I take a new house for which I'm just considering one input. Let us say the floors of the house. So there is a new house which has 4 floors. According to 4 floors, what I will do, I will just put it into this equation. 5 plus 1.8 into 4. See, these are nothing but these are, there is a function, there is a function will be created by ML algorithm, will be in this format, beta naught plus beta 1 into x format. So once we have found out the value of beta naught and beta 1, beta naught we have found out as 5, beta 1 we have found out as 1.8. I'm just taking an example that how do you solve, how do you predict something. So let us say you take a new house which has 4 floors. That is an input. So input is mentioned by what? X. So you put x is equal to 4, and then you know beta naught and beta 1. Now you understand why knowing the value of beta naught and beta 1 is important, because you have to do this calculation. So let us say 5 plus 1.8 into 4, how much it will be? 52 plus, I think 10.2 it will be, right? 10.2. Okay. So suppose this is 10.2. And how have I got it 10.2? 5 plus 5.2, it will be 10.2. Now, in this case, this 10.2 that I'm getting, it is, let's say, $10.2 million. Okay, $10.2 billion. This is the house price that our model is predicting. This is the house price that our model is predicting. Now, what you think is this in this case? See, 5 that I've written here is the base price of any house in a certain area. If the house is being created, if the house is being constructed in a certain area, let us say its base price is $5 million. It's a very, you can say, expensive locality. Okay, 5 million. Then I have a multiplier. 1.8 is a multiplier that I'm multiplying 4 with to get a house price that is $10.2 million. So that is how the prediction of your model is going to be done. Prediction about the future is going to be done. I'm not talking about the functions in detail. This we will understand tomorrow. But now you get the idea, right? That you take input, output, you have ML algo, you have a function. No, beta naught and beta 1 is not fixed. The whole process is to find what will be the beta naught and beta 1. Because if I change beta naught and beta 1, our prediction will change. So it can't be fixed. It is always going to change in that case. So now when you take a look at this, a function will be in this format. I'm just talking about this. Don't go into detail. This will be the format of that function. This function will have some numbers, and when we give input, x is our input. When we give it input, then it will predict some output. And that is the prediction output I'm talking about. That is the prediction value that our house price is $10.2 million for a house which is having 4 floors in this particular area, in this particular city. It can be for Washington, D.C., it can be for, you can say, Amsterdam or Indian city like New Delhi or something like that. This is the prediction we have done. So machine learning algorithm is going to create that function for us. The function will be in this format, but a function will have numbers in this format itself, but it will have some numbers that we have to find out. So that is what happens with ML. Now, once we have got this idea, let us now understand the further things, which is this types of machine learning. Now, there are various types of machine learning that you will study during the program and later also when you go to industry. One is supervised, one is unsupervised, there is reinforcement, there is transfer learning, and there is one more semi-supervised that you can see, but that is not very much required for now. These are 4 main type of learning that happens in machine learning: supervised, unsupervised, reinforcement, and transfer learning. What they are? Supervised and unsupervised, we'll be talking in detail, but let us see what happens in reinforcement. This reinforcement learning makes prediction based on reward and penalty. It works on the basis of reward and penalty. Okay, so what you will be doing in industry is these 2 type of learnings you will be working with. And these 2 also not in most of the cases. In most of the cases, you will be just working with supervised learning. I'll show you example that why I'm saying about this. But as a fresher, you will be working with this. Once you get some experience, 1 or 2 years of experience, then you will be given unsupervised task. When you get 4 or 5 years of experience, then you will move to reinforcement learning. And little more than that, you will then study transfer learning. Because these are way too advanced algorithms. These are way too advanced processes that you can't understand as a fresher. So when I talk about transfer learning, what happens is that in transfer learning, let us say one machine learning model you have created. And you want to create a second machine learning model very similar to this. So instead of creating the second ML model from scratch, what you do? You transfer the learning from first model to the second model and then improve upon that. So let us say one model you have created, which has got 85% accuracy. So you take whatever learning it has done, you pass it to the second ML algorithm, ML model, and then you make it even better. That's a transfer learning. Okay, you transfer the learning from one model to second, second to third, and you keep improving it to make it better and better. But that is a very advanced part of the system. You are going to study supervised and unsupervised in most of the cases. Let us see what supervised and unsupervised is. This reinforcement learning works on reward and penalty. What happens in this case is some data will be given to some algorithm, and that algorithm has to make prediction. Okay, that algorithm has to make prediction. If that algorithm makes wrong prediction, it will be penalized. Some penalty will be given. If it is making good predictions, then it will be rewarded. It has been taken actually from the cat that mouse experiment that is done in the labs. So mouse is kept into some container. He is supposed to do some task. If he is doing the task which has to be done, he is rewarded with cheese. If he does a wrong task, which is not he should not be doing, he is penalized. That cat is penalized. So then in that case, with the reward and penalty, your machine learning algorithms learns the process. No, obviously it will not be monetary. It is just machine learning algorithm. It's a mathematical function. So reward and penalty is in a mathematical form. You'll see about that. But when it is working well, when it is learning in the correct direction, it is rewarded more and more and more. So your algorithm will know that I have to improve in this direction. When it goes to a wrong direction, it is penalized. So your ML knows that I should not be going in this direction. I should try something else. So with this reward and penalty, this reinforcement learning will work and try to improve over time. In this reinforcement learning, a data which is given is a dynamic data, is a live data, which is connected to the internet. Every minute, every second, live data is flowing through it, and it is learning upon that. So it's a very advanced process to handle. As a fresher, you won't be able to handle it. That's a basic idea I've just given. Now let us see what is this supervised and unsupervised learning. That is what our main agenda is. During this course also, you will be studying supervised and unsupervised in detail, and you will be seeing reinforcement as a introduction part of it, because that is not required now. So if I talk about first, which is supervised, any learning that you know is decided upon input and output. Okay, according to input, according to output, your learning changes. So let's say in the case of supervised learning, you will take a data where input is also known and output is also known. So I have just shown you an example. This one, this heart disease prediction we were talking about. The age, the chest pain, the sugar level, the blood pressure, and cholesterol. What are these? Input. The medical conditions, these are input for a patient, of a patient. Then you have output. That person has heart disease, does not have heart disease. Very similar to that, if you're doing, let's say, loan prediction, which person should be given loan. So what you study the background of the person. You study the qualification, you study the job, and different things. That is input. Then you decide whether that person should be given loan or not, or you study whether in the past that person was given a loan or not. So that is output. Yes or no, that is output. The features related to that person, the features related to a house for which you are predicting the price of the house, those are input. So a supervised learning is a learning where you take a data set where input and output both is given. So let me just wait for a few minutes, you'll get that answer. Input and output is known in that data set. Now inside this supervised learning, there are two types of supervised learning inside this. One is called classification task. Okay, classification task. In classification task, what happens? Your output is categorical. Okay, categorical output. Categorical output means yes or no kind of output. So whenever you take a data set where the output is supposed to be yes or no, 0 or 1, like credit card fraud detection, those kind of things, then it becomes a classification task. Here also output is given, but the output is categorical. So it will be in the format of yes or no, 0 or 1, fraud or not fraud. Yes. So in this case, what can be the some of the use cases of it, like heart disease we were talking about, heart disease prediction. Then we have loan approval you talked about. That is also in yes and no. Yes, survival also. Then we have credit card fraud detection. Credit card fraud detection. Okay. These are all classification tasks. So when you take a data which has input and output both given, that is a supervised. In supervised, if your data has output in the format of categories, yes and no, fraud or not fraud, so then it becomes a classification task. The algorithms which are going to be used for this classification task are, let's see, the classification algorithms. So there are certain algorithms that you use for these cases. And these algorithms have, I'm going to write the name of these algorithms now. It's called logistic regression. Second is called decision tree. You have random forest. Then you have naive Bayes. And then there is a support vector machine. See, I could have shown you this thing pre-written, but I'm writing in front of you so that you understand it more properly. Because when we write, that's become important. You are able to remember it properly. Then you have the last one, which are something called as boosting algorithms. You'll be taught about all of these algorithms, how they work, in what scenario they perform well. So these are some of these things are there, which are, I'm trying to show you what are all the algorithms which are present, XGBoost and AdaBoost. So there are logistic regression, decision tree, random forest, k nearest neighbor, naive Bayes, support vector machine, and few boosting algorithms like XGBoost, AdaBoost, gradient boost. These are all algorithms which are going to be used in the data set which has categorical output. Second case, let me show you the second case also. This is called regression task. Fifth one is naive Bayes. Naive Bayes. That is the name of this algorithm. In regression task, what you have is you will have continuous output. Can anyone say what will be the use case of that? Continuous output. So continuous output like any floating point number. So in that case, what are the problems we solve? That is like house price prediction. Any price prediction, house price, land price, stock price prediction, those kind of things. Then you have sales prediction. Yes, temperature, weather, those kind of things. Then you have stock price. These are all continuous values. Continuous means it can be anything. House price can be anything from $0 to, you can say, $1 billion. The houses are of any amount around the world. If you take a look at it, the house price can be starting from $100 to whatever, you can say. Suddenly you'll say where it is $100. Currently there was a bank sold for $100, if you've heard about that, Silicon Valley Bank in Britain. That bank just collapsed and another bank purchased that. If I followed the news of it, it's a very recent operation that happened. Yeah. Right, a Silicon Valley bank that has fallen. It was doing a lot of scams which it could not keep up, and then it failed. So there was a lot of startup that they have put money into that bank. So they were not able to take out the money, and because of that, many of the startups just closed in single day. Okay, in a single day. And because of that, in Britain, around 10,000 people were fired in a single day. That happened. Okay, so currently it's a very bad time going on. A lot of things have come together. Now, so what are the algorithms for regression? We have linear regression. It will pass, it is not going to be there for a very long time. You know why these layoffs are happening? Have you known the reason of that? Not exactly. See, there is not a single reason. The first reason is that inflation has reached to a very high. So it all started mainly from US and UK. Okay. Mainly it started from US and UK. Before Russian and Ukraine war itself, it started. So what has happened is that US has taken debt. Okay. Every country takes debt to run its country. They take debt from different countries and then they repay with a certain interest. Now, US has been taking a lot of debt from a very long time. So when it was very long time, it was decided that US can take a maximum debt of $25 trillion, which is a very huge amount, $25 trillion. So in the current times when Joe Biden came and he was elected, he printed $5 trillion in a single year. Okay, he not printed in a single year. He actually announced that $5 trillion will be printed and pushed into economy. So that announcement was done as soon as Joe Biden took over as the president. And suddenly this maximum capacity, that this maximum allowed debt US can take, was also improved. There was changes made in their documentation, in their legislation, to improve this from $25 trillion to $30 trillion. This is itself a very huge amount. That much debt any country cannot pay ever. But they have increased this debt and they have also printed a lot of money. Because of printing a lot of money, every company got a lot of money. In the Corona time, in the COVID time, you saw that Facebook, Amazon, the market value of these companies crossed $1 trillion suddenly in just few months. So what happened is that they started hiring a lot of people. Talking about the example of, let's say, Facebook has hired a lot of people, and there it started all the story. So Facebook actually requires one of the senior developers of Facebook. They said that Facebook requires only 7,000 people to run its operation all over the world. Okay, only 7,000 people. But do you know how many people they have employed in total all over the world? More than 75,000 people. And they require only 7,000 people properly to do all the tasks. So, and they started to employ more and more people during the COVID time because they got a lot of money. And they thought that it will continue for 10 years like that. Okay. But COVID was a very different situation. A lot of people were sitting at home. So they were using Instagram, they were using Facebook a lot. So it was a very unique time. And they thought that they will be having their users like that. But it failed when people started coming out of their houses. They started to go offline into restaurants and they started moving. So they reduced their uses of Instagram, Facebook as much as they were doing during COVID times. So a lot of their projects failed according to that. They were not getting their users and everything. So because of that over hiring that they have done, they had to fire them. Over hiring. So over hiring came because a lot of money was printed and these companies got them, and from there it started. So first was one reason. So one reason was that. Second, because of this this Russia and Ukraine war situation got worsened, so it added up onto that. And then suddenly it was found out that UK is also suffering from inflation, which they were hiding for quite some time. That also came to light. So these are all the problems that happened because of which this is happening. So this inflation is very much required to bring everything into normal pace. Because of this inflation, because of a lot of money that came into economy, many companies which were very bad, okay, they should not have got fundings. They have got funding in this COVID time. So this money flew into wrong hands, which should not have happened. In India also it happened. In US also it happened. So all the companies which got funding unnecessarily, they were not able to sustain it because they did not have a proper background. They did not have a solid product to sustain over a long time. They all closed. Now slowly and slowly the slowly and slowly all the things will come back to normal. And now the companies will hire only the people which are actually important to them, and they will be giving good amount of money because in the COVID time they have given lot of money to freshers itself. In India itself, you if you see the freshers got 35 LPA, 40 LPA, 45 LPA as a fresher. Okay, that's a lot of money. Okay, considering Indian markets, considering developing markets. So those kind of things will normalize. They will be given what they actually deserve. Okay, if there is a good talent, we understand that they should be given good money, but 40, 45, 35 is quite a huge amount of money as a starter. So let's talk about that later little. So talking about this algorithm for regression. When you talk about regression problem is what? Here also input and output is given, but the output in this case will be continued. So if you're having a data set which is talking about house price prediction, sales prediction, stock price prediction, any continuous value prediction, then that becomes a case of regression task. Both classification and regression comes into this supervised learning, but they are divided into two different structures. If you're solving a regression task, you will be using one of these algorithms. If you're solving a classification task, you will be using one of these algorithms. So there are multiple options available to you. So let's say you're solving a credit card fraud detection and you use this. If you use this, you will get a performance. How better you are able to predict a fraud is a credit card transaction is a fraud or not, how better you are able to predict it. So if this one does not work, you have the option of using this one, then this one, the other ones, the boosting algorithm. So this happens. You are going to do experimentation. So let us say you took this. You will have option to improve it also. Suppose it gave you 80%. So you can do some improvement in this algorithm itself to make it from 80 to 85%. But 85% is the best I can improve in this. That is also not enough for me. What I will do now, I will go to, let's say, random forest. The random forest is giving a base accuracy of, let's say, 91%. So from 91%, I can take it to 96%, 97%, 93%. So which one is better? Random forest in this case becomes better. So it is not that any particular algorithm will be good for all the cases. You have to experiment, you have to try different algorithms to get to know which one is working good, which one is not working good. So these are the names, I've written them. We will be working with them. We will be understanding their working, how they are created, how they make the prediction. The input that you see in a data set, the input columns are there and output column is there. There are multiple input columns and only one output column, always. So there are few names given to input column. So input column is also called independent column or independent variable it is called. We'll talk about that, mathematics. Features and your output column is called dependent variable or target. Okay, dependent variable or target. This neural network, it is called neural network. It is a deep learning algorithm which will help you for regression tasks. These are just the names of the algorithm. Correct? Now, so if you take a look at it, input and output columns are there. Input column is also called independent variable or features. Output column is also called dependent variable and a target. These are different names. So if you hear this independent variable, don't get confused. It is talking about input columns. If you hear features, features mean input columns. These are the terminologies used for that. So if you take a look at this example itself, There are multiple input columns: age, chest pain, sugar level, blood pressure, cholesterol. These are called features, these are called independent variables, and these are input, all in white color, all the columns. Why they are called independent? Because age is not dependent upon chest pain is not dependent upon sugar level is not dependent upon blood pressure. They are called independent variables. Okay. But output column is called dependent variable. Why it is called dependent variable? Because a certain output is dependent upon this, and this. Okay, any output is dependent upon the input of the data. If I change input here from chest pain from 5 to 1 and sugar level from 110 to 65, your output will change. Maybe it becomes from yes to no. So this is dependent upon your input. That is why it is called dependent variable. And input is called independent. Output is also called target column and input is also called features, just names. Don't have to remember it for now. With practice, with working, you will hear these terms many times and you will get this idea. This thing I was talking about, right? So you give input and output to ML algorithm. It creates a function, and using this function, we will be making prediction. So I've given you one idea that a function that our algorithm will create will look like this. It will be a mathematical formula equation kind of thing. So once you get this, you will have to solve it. You will have to give input to this function and you will be working with prediction. You'll be getting a prediction.
I have one more announcement for you guys. For dedicated learners like yourself who want to make a difference in their career, for the first time, we at Intellipaat have decided to offer a straightforward 20% discount on our premium data science course, which is in collaboration with iHub IIT Roorkee. If you want to take control of your tech career and do something extraordinary, do visit this link in the description box given below and fill the inquiry form. Promptly, a team of course advisors will reach out to you to activate the offer. So don't miss out this opportunity.
Every algorithm that you're going to study in machine learning is actually created by mathematicians. It is not created by computer scientists in total. Maybe if they have created any one of that, they have got help from mathematicians to create that algorithm. So in the background, every algorithm is just maths. Okay. And to understand them properly, you should have a little bit of knowledge about linear algebra and little bit about calculus. Okay. These are the two things required for you. But for now, whatever is required, I will just give you an idea about it, that this is what happened and this is what this is telling you. Okay. So you need to know the basic of math as linear algebra, little bit of algebra, and little bit of calculus. In calculus, there is a concept of differentiation, and that is what you have to know. Okay. So now, if possible, if you can go through it, you can go through a little bit of maths on YouTube. You can watch few videos to understand the maths required for machine learning. You can search for these video, maths required for machine learning. You'll get to see few videos, and 15-20 minutes if you give, you will get some idea. That will help you. But again, I'm going to touch upon that. You're not going to miss anything if you don't know calculus or algebra at all. So that is the task we are going to do. Let's get started and let us understand our first algorithm. Now, how many of you have heard about this linear regression? And this linear regression is the algorithm of regression task. Okay, regression task means house price prediction, sales prediction, those kind of things. For one of those tasks, you're going to use linear regression algorithm. So let's understand. Now, this linear regression, as the name suggests, something linear is going to happen. A model will be created, which will be a linear model, which will help us do the prediction task. The whole concept of machine learning is to help you do future predictions, the prediction of future outcomes. Now, how do we do prediction of the future outcomes? Goes something like this. So let us understand it with a simple example that I'm going to take now is this. So let us say, suppose this is the line, and then these are some dots. Suppose these are some dots. And what are these dots? This is your past data. Now, what are we trying to do? We are trying to make a prediction between two of the data, one input and one output. So as I told you that whenever you are going to work with machine learning, you will have an input data and then you will have output of that. So according to some input, what output is going to happen? First, you study the past of that, the past results, that according to this input, what output was there in the past. Once you have understood the past, accordingly, you're going to predict the future outcomes. So that is what is going to happen. And let us get an idea about it. So just once again. So I'm trying to, let's say, I'm taking a very simple example for now, where I have marketing budget as my input. This is my input. And let us get to see the sales. Okay. Let us get to see the sales. Now, what we did in this case, if you understand, why am I making a scatter plot? Is because of the reason that these two columns are numerical. So when you're going to work with the machine learning algorithms, what you will have is you will have the data which will be numerical. Okay, numerical. So in this case, I'm taking an example where the marketing budget and sales. In all the data sets that you take, you will have similar type of information. You'll have numerical columns, and according to numerical columns, you're going to make a scatter plot. So for the explanation, everywhere, if you see the explanation of linear regression, one input and one output will be taken for you to explain the things. Because if I take multiple input and multiple one output, then it will not be feasible to explain it at all. So whatever follows with one input and one output will also be same for multiple input and one output column. We will talk about that, but don't worry about that. Let us focus on this. So let us suppose I have my marketing budget, which is my input, and I have sales. Now, what are these points denoting? These points are denoting that you have to match it here and you have to match it here. So any particular point, if you remember, is a data point, which is representing that if a company has spent this much marketing budget, whatever that amount is, they have got this much of sales. That is what every point is denoting. According to some marketing budget, how much sales this company has got. Now, this is a scatter plot. This is a visualization plot. And what we do with visualization, if you remember, we study the past data. We try to get the information from the past data. That is what visualization is all about. But using the scatter plot, I can make predictions. That is what I'm going to do. So what I should do in this case, how will I make a prediction from this, out of this? So what I'm going to do is I'm going to pass a line through it. Okay, I am going to pass a line through it. That is what happens in linear regression. This is what happens in linear regression, that you take input, you take output, there will be a plot of it, a scatter plot, and then you pass a line through that. What is this line going to do for us? This line is going to help us to make a future prediction. How it is making a future prediction, how it is helping for that, let's see. So when you take a look at it, this line is actually called a best fit line. Okay, best fit line. Why it is called best fit line, we'll understand. But the task of this line is to help us do a future prediction. Future prediction in what sense? Let us understand. That let's suppose a company spends this much marketing budget in the future. Okay, which company has not spent till now? Or let us take here. So you can see here the final or the maximum amount that has been spent by this company for marketing is represented by this dot, which is somewhere here, if you look at it. So let us suppose now the company wants to spend little more amount of money, which is this much. Whatever this is, let us suppose they have spent 300K. Okay. Till now, they have spent 300K for marketing budget. And now they want to, let's suppose, spend 350K now. So if the company is going to spend this much money, what they will want that I should have some idea how much sales we are going to generate. They want to have some idea. So what they do, they take the help of this best fit line, this linear regression line, to make a prediction, to make the future prediction. Now, what happens in this case? How will they make the future prediction? Is they have to just touch this line. Let's suppose, okay, first they are going to touch this line from here. And once they have touched this line, they are going to touch from here to here. Okay, we're just going to touch from here to here. That is what. Now, so let us see, when we look at this value, what is this value? There is a some sales value. So let us suppose that the final this company has spent was this much amount, was shown by this understanding with this data point. Now, what happens here is this. So when you take a certain data point, you have to touch it on this line, and according to this, you touch on the y-axis. Y-axis is what? Our output. That is what we have to achieve. So let us suppose that according to 350K, the sales value that comes out to be is, let us suppose $4.3 million. Okay, $4.3 million. That is what the sales have generated. You get this idea, right? That we have to predict anything, a future outcome. So we take the help of this line in linear regression. We're talking about specifically linear regression. Every algorithm has their own different way of working. So linear regression does this. What they do, they have the past data and they fit a line through the past data. And when they fit the line through the past data, what they do, they are going to use this line to make any predictions in the future. So you take the X value, you touch upon it on the line, and then you mark it on the Y-axis. And what is this? This is your predicted value of the future. Now you might be correct, you might be wrong. You don't have any idea about it. You're just making an assumption that this is going to be what a sales value in the future, our sales value. So whenever you predict something, you don't predict it to think that it is my final value. You don't make a prediction for that. You make a prediction so that you get a sense of how much you're going to generate, how much will be the value, final value. So accordingly, little higher, little lower, it will be in the future. It is not going to be exactly 100% this amount. In the future, when they spend this much amount, they might generate $4.5 million or 4.1, $4.2 million, which will be lesser or more, but we are going to predict something. Now, how do we know that how closer we are to accurate result? Because in some cases, if you don't create a proper linear regression algorithm, if you don't create this process properly, you can get a prediction value which will be very wrong, which can be very different from what actual is. That is also going to happen. If this learning, this is a learning that is happening, machine learning that you say. So according to linear regression, this is the learning that is happening. So how do you know my assumption about the final value is close to accurate? How do you know about that? Because you're just making an assumption, thinking that you're going to get a very correct result, a close to accurate result, but you don't know how close to accurate you will be. Let us suppose you have predicted $4.3 million, but you get $5 million, or you have supposed created or predicted $4.3 million, but you get just $3 million. So that is a very big difference. You are not even close to what the actual value is according to what you have predicted. So to get an idea about how closer to accurate we are, we do analysis of the previous result. Okay. So in that case, the best fit line is going to help us. According to a certain data, the best we can observe is given by this best fit line. Now, what is this best fit line all about? Let us understand. Now, in this case, when you take a look at all of these data points, how a best fit line is actually created is taking a look into these all the previous data points. Now, you have all understood that this line is going to be used for prediction, this line. So to make a future prediction, we try to understand first how it is able to predict the previous outcome. That way you will be able to understand how better it will predict the future outcome. If it is very good for predicting the previous outcome, it will also be able to predict the future outcomes properly. That is what we understand. So now if you get to see here is this. Let us see how we identify if it is working well for the past data or not. So all the white dots that you see, these are your actual data points, the actual result that has happened. So it is telling you, let's suppose this particular point, if I pick up, it is telling you this much marketing budget was spent and this much sales we have generated. This is actual result. But what we do, how do we identify how good my best fit line is for prediction purpose? Is we try to predict, let's say for this dot, this is the marketing budget spent. Okay. So what we do in this case now, for this particular data point, what we will do, we will first mark it on the line. Okay. For this data point, I will mark on a line. So what is this mark telling me? This red dot that I have given you, what is this telling you? Can you say what is this telling you? For this is my X value. That company has spent this much marketing budget in the past. So what is this telling you? It is telling you the sales of the, according to this X value, according to my line. For this sales value, according to my line. This dot is what my line is predicting. But what is the actual value? This is the actual value for this X. This is my X, this is my input. So if company has spent this much amount in the past, they have generated actually this much, according to this white line, white dot. But what our line is predicting, if we are using it for that, it is predicting this much. Now, is my answer correct in this case? My answer is not exactly correct. And if you take a look here, there is a difference. Okay, there is a difference of this much between my actual line, actual dot, and the red dot. Actual dot is my actual sales value, and red dot is my predicted sales according to the line that I've created, the best fit line that I've created. So how do I identify our best fit line? We are looking for why I'm saying this is the best fit line and can be used for prediction or not. We are trying to understand that. So for that purpose, we are looking at how better it is able to identify the past data. If it is able to identify the past data properly, then it is an assumption that it will identify the future also properly. So what I'm doing is this. You see, I'm taking an X value and actual is this white dot and my predicted is this red dot. Now there is a difference in this. What is this difference here? This is the distance between 2 points. That is one thing. And it is our error or variance, you can say. It is our error. That is what we have to say. Error, why? Because if you take a look at it, what was your actual sales value? This. But what are you predicting according to the predicted line, according to the best fit line? This. So let us suppose according to this input marketing budget, your actual sales suppose was $2.7 million. But what you have predicted was $2.7 million, and what is actual, let's say $2.98 million. That is what your actual sales value was in the past. But what you have predicted with this line, you have predicted this value to be 2.7. Now, this difference between the actual and the predicted, 2.98 is my actual minus 2.7 is my predicted, actual minus predicted. So it comes out to be 0.28. Okay, 0.28. That is what this comes out to be. So this 0.28 is my error. This line has done this much of error in the prediction value. So 0.8 million is my error in prediction. Got it? Now, difference is not in million. See, it is not that very wrong. How much is the difference in there? 0.28 million. Because whatever value is there, it is going to be in that same scale. We are looking at the same scale. So if my actual value is 2.98 million, it is 2.70 million, and 0.28 is the error. See, we don't have to look at the number that it is 0.28 million. We have to understand a relative thing. What we have to understand, I'll talk about in just 2 minutes. Wait. So is everyone able to get this idea? Same thing we will do for every data point, all the white data points. For this also, for this also, for this also, for this also, we will have to do that. So for, let's say, for this one, where the dot will be, here the dot will be. For this one, here the dot will be. For this one, here the dot will be on this line. For this one, here the dot will be. For this one, for this one, for this one, for this one, this one, this one. So now we have to just check the distance of a white dot from my yellow line. Yellow line is my prediction line, best fit line. And I have to check the difference from all the white dots to my yellow line. And now what I have to do, I have to calculate the total error. Total error means the error made by every single dot. Okay, from dot to my line, I have to calculate every error. This error also, this error also, this error also, this error also, all of the errors I have to calculate, and I have to combine them. When I combine them, I'll get some final error. That error may be anything. We don't have to get this exact value. Let's suppose I get the total error to be 62.8. That my line is making for predicting all the values. Okay, this is the total error that my line has made. What I'm saying as a total error, you see, one error was this 0.28. Somewhere it will be 4.5. Somewhere it will be 3.2. Somewhere it will be 1.9. Somewhere it will be 0.11. So you combine all the errors for all the dots and you get a total error. Now, how do you know that this is your best fit line? See, there is a concept of this best fit line. This concept of best fit line says that when you take a best fit line and if you make a prediction according to that, you will get the best result. But how do you say this is the best fit line? There is a comparison made for that. How? So when you look at this data point, okay, when you like, it is going to be sum of all the data points, sum of all the errors. So now, how do you say this is the best fit line? Let's see about that. Now, when you look at these dots, when you're seeing these dots visually, you can say that, okay, pass a line through this, and that will be your best fit line. And here I have given you very few data points, 7-8 data points are there. And what are these data points representing? Your data set. Now, suppose if in a data set there are 10,000 data points, if I give you, okay, if I give you 10,000 data points, will you be able to tell me which should be the best line? You will not be able to tell which should be my best line. Similarly, your algorithm does not know that this is the best line. Your algorithm does not know, or algorithm can't look at the data and tell that it should make a line like this. It does not work visually. Algorithm or anything which is working on your system, on your computer, everything takes help of some mathematics to do this kind of task. So my linear regression is also going to take the help of a mathematics to find out whether it is my best fit line or not. So how does it tell me that this is the best fit line? Is it makes comparison with other lines. So let's say I make this yellow line, I make this yellow line, I make this yellow line. Now it is line number 1, line number 2, line number 3, and line number 4. Correct. So how can I tell which is the best one when you take a look at them visually? Line 1, line 2, line 3, or line 4? Which one feels to you the best? According to the concept that if I let's suppose take the line number 4. So how do I find out line number 4? I have to check the total error with line number 4. So all the data points which are there, checking for the line number 4 will be very far away. It is very far away from all the white dots as compared to line number 2. Line number 1, you will say that it might be very close to line number 2, but it is not as accurate as line number 2 because it is making little more error. Line number 3 will make little more error. Line number 4 will also make more error. So when I compare these multiple lines, whichever line has the total least error, okay, total least error, whichever line has, that is our best fit line. So our task is to just reach to that best fit line. Once we reach the best fit line, we will say that this is going to give us a very close to accurate prediction. That is what whole concept is all about. Okay, so we need to look for that. Now there is a proper mathematics. We will talk about that now. I'm just giving you an overview of working of linear regression. So what we do essentially, this is what we have done to get this. And now what we do is this. For certain data points, I'll be making this line. 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 Like this. Now, not just this. Your linear regression will do what? Linear regression has no idea that your dots are here. Okay. It's just an algorithm. It can't see visually that dots are here. So what it will do, it will just create line everywhere in this area. It will try to create a line everywhere. How many lines it will create? It can be infinite number of lines it can create. But what it does, it creates around 1500, 2000 lines in that sense to get an idea about what is going to happen. Once it has created those many lines, it is going to compare out of all the lines, which line is giving me least error. So it is going to create 1000 lines, 1500 lines, 2000 lines like this surrounding the data in this range. From this area to from this area to this area, in all this range, in all this area that you see, it is going to make many lines. And once it is making the many lines, what it has to see, whichever line is closest to all the white dots, that is your best fit line. That is your best fit line. Yes. So you have to calculate total error for every single line. Then you compare them that this line has given total error least. Okay, least total error, whichever line gives you, that is your best fit line. So let us suppose if you make 5 lines for the comparison, just for an idea. So line number 1 gives you error of 62.8. Line number 2 gives you an error of 79.4. Line number 3 gives a total error of 110.5. Line number 4 will give you, let's say, error of 480.7. And line number 5 gives you an error of 600. Now, this is the kind of error you're going to get. Line 5 is giving a very high error. How it is giving very high error? So let's say your data points are here, and if you make a line here, so how wrong it is, you can see. You have to calculate the error. You have to calculate the distance of all the white dots to the line. All the white dots, the upper one, the lower one, all the white dots, you compare the distance from the line. Get it? That is how your linear regression identifies that this will be my best fit line and this will not be my best fit line. So you're getting the idea? You don't have to do anything manually. You're just understanding the working of this algorithm. Everything will happen for you automatically. You just have to understand this, how it happens. Because when you go to interview, they will be asking you this. You don't have to do anything. It will just do everything in the background. There are code written for that. We will see that code also. But we are just understanding the background working of an algorithm. Where we started that I have past data. Okay, you take a past data, you study the past data to make a future prediction. That is what I have explained. That is what happens in machine learning. You study the past data. Now I have a past data which was about marketing budget spent by a company and sales by a company. Okay, marketing budget by a company, sales by a company. So in that case, what I did, whatever past data I had, I made a scatter plot of that. You all know when I take two numerical columns, the best plot to create is the scatter plot. And all the columns, all the input data that you will have in the case of machine learning, every column will be always numerical. If you're getting a text column, that also you have to convert into numerical. We will see about that process. There should not be a single column that is left as text before applying machine learning on that data set. Every text data should be converted to numbers. That should be clear. We will see that. So now I am taking just one input and one output to understand the idea clearly. Then let us suppose company has spent some marketing budget in the past and they have got this much sales. And all these sales are being presented to you by this white dot. Okay. And what we do in linear regression algorithm, we fit a line through this. The line is the yellow line which is passing through this. When you are having this yellow line, when you're passing the line through all the dots, what we do, we make a future prediction with this, as I have told you. So let us suppose in future, this company wants to spend this much, 350K, which they have not spent till now. Till now, how much they have spent, this white dot is representing the final value, the maximum marketing budget that company has spent till now, this 300K. But now company wants to spend 350K and they want to have an assumption or some idea that what can they expect? What is the sales they can expect in the future? So for that purpose, we use this line. This is our best fit line that gives us future prediction. So I have created this best fit line, and this best fit line I'm using for the prediction purpose. Now I have made a prediction that is correct. I understood that I take this best fit line. I use this best fit line for my prediction. How I made the prediction? I connected the X value with this line and connected this dot to the Y value. So this Y value that I'm getting here, this is my predicted output. That when the company spent $350,000 for marketing, $4.3 million they are getting in the future. That is the predicted output. But the whole point is that how do you know your predicted outcome is correct? How do you know about that? Whatever you are predicting, it can be wrong. You have no idea at this point. So what we do in that case, how do we know that the assumption we are making is correct or not? So our task is to find out the best fit line. Why we are looking for the best fit line? The best fit line is nothing but you have to study the past data now to find out the best fit line. So best fit line is such that it is closer to all the white dots. Okay, all the white dots, it is closer to all of them, and that is your best fit line. Suppose if I take another line which is like this, let us suppose this. What are we doing in this case? We are trying to find out the distance of all the dots. You see, now you have to find out distance of all the dots to this yellow line now. Okay, this white, this white, this white, this white, this white, all of the white dots which are there, you have to calculate their distance from the new yellow line. Now, if you take a look at it, which yellow line you think is closer to all the white dots? The closer it is to the white dots, the lesser the error is. Okay, so as I can easily see, when I take a look at line number 1 and when I take a look at line number 2, line number 2 is closest to all the white dots as compared to line number 1. Line number 1 is also a regression line. You can also use this for prediction. Okay, you can also use this line for prediction, but let me show you what disaster will happen if you use this line. Okay, so according to 350K marketing budget, where our prediction value will come? Here. So it will predict me something around 2.65. Okay, what my this yellow line is predicting? This value. This value I have to map on the y-axis, and here it will come. So this will be 2.65 or 2.6, something like that. Correct. So my line number 1 is giving me prediction of $2.6 million, and line number 2 is giving me prediction of $4.3 million. So you're saying there is a huge difference between the best fit line and all the other lines. If I make any other line, some of the line will be very close to the best fit, like this. So they will also give some prediction value which might not be so wrong, but it will be different from my actual, different from the best fit line. Got it? So that is how I identify that my this particular line is not the best one, line number 1. My line number 2, which is there, is my actual best fit line. Once you have found out the best fit line, your task is done. Then your machine learning will take care of the future prediction. Then you are going to settle down that, okay, I have found out the best fit line. That was my task. Now make the prediction. Now there are certain properties with it. What if the lines are very scattered? What if the lines are having outliers? Then that is a problem. We will talk about that. I'll talk about those corner cases. Don't worry about that. But for now, has everyone got the idea? Because you are using this yellow line for future prediction. So if after prediction, how will you do it? If you don't have the line, you can't make a future prediction. That is the whole concept of it. So you should have a past, first you create a line, then you use that line for any future prediction. So first you create the line. How do you create your line? You take its distance from all the white dots, the previous data points, and you see if this line is giving me total error as least as compared to any other line, you say that this is my best fit line. Now, that was the overview I have given you for now. But the things don't happen with an overview. This is the visual representation of the machine learning, the linear regression that we have done. So visually, it will not happen. Any machine learning will take help of some mathematical formula to give you final answer as correct answer. Because you can say that it is my best fit line, but I don't know whether this is my best fit line or not. Maybe my line should have shifted a little. I have just given you a basic idea that a line passes through the data points, and the closest it is to the data point, the best it is. But I don't know, or your linear regression also can't see this visually. It has to take help from some formula. So what the formula it takes help, we are going to talk about that. Okay, let's see. So before talking about that formula, this line has an equation. Okay, this line has an equation which is going to help us predict the future value. And this equation is actually given by this. Your linear regression line is given by beta naught plus beta 1 into x. Okay, this is the equation which we are going to use to find our best fit line. Now, every single line which you make will have this equation. Every single line, whether it is best fit or not, they will all have this equation. But what we have to do is, see, this formula is very similar to y is equal to mx plus c. Okay, y is equal to mx plus c. So the mx that you're writing is beta 1x and c is beta naught. So this is what, this y is equal to mx plus c is what? It is the equation of line. If anyone has studied the mathematics in class 11th and 12th, generally it is taught there that it is called equation of line in complete mathematics. Anywhere you study in mathematics, any equation of line is given by this formula mx plus c. What is m here? M is this tilt. You see, a line is tilted at a certain right. It is called a slope. So this tilt is given by the m value. And wherever it cuts on the XY axis, okay, any line that you pick, let's say this red line you're picking, it is cutting this Y axis at this point. So wherever it cuts, it is represented by C, which is also called intercept. Okay, intercept. So our best fit line also is behaving in the same way. That best fit line also has a slope like this, and it also cuts at a certain point on the y-axis. So this slope is given by beta 1 in our equation, and this cut that you see here is represented by beta naught. So it becomes the similar formula which is given, which is a universal equation of a line. In universal equation of the line is this: y is equal to mx plus t. What are we making? We are also making a line. So if we are also making a line, what will our equation be? It will also be very similar to that. It is just beta 1 x and beta naught is used to represent this, just some other notation, some other symbols I'm using instead of m and c. Now, that is what our linear regression is going to do. So linear regression is going to create a equation in this format, beta naught plus beta 1x, to give you or to tell you that this is your best fit line, and you can use the best fit line for a prediction. Let us understand that. So let us see how a particular line is created. Let us see. So your intercept is, your slope is now beta 1, and your intercept is beta naught in this case, in our equation. So a linear regression equation goes through beta naught plus beta 1 into x. Now, what is this x value? What is this x value? This is your input. Future input, when you give it, it will give you output. Okay, future input, if you give it, it will give you output. Now, let us say input is something as 3. Can you give output according to this? I can't give any output for now. Because if I say beta naught plus beta 1 into 3, what does it give you? You have to get a certain value. It should be a number that you say as this is my final prediction. Let us suppose you give that 300K we were talking about as the input. Okay, 300K. This is my input, or sorry, 350K we were talking about, right? So that 350K that I was talking about, and I was getting a prediction of 4.3 million. How that prediction I was getting? So you give that 350K as this X value, that is your input. And then it will be multiplied by something called as beta 1, and it will be added by beta naught to give you $4.3 million. So how will I multiply it? Before that, I should calculate what is beta naught and what is beta 1. They should have a numerical value. So let us suppose I get this beta naught. Suppose this beta naught comes out to be 4. Okay. And beta naught, beta 1 comes out to be 1. So 4 plus 1 into 350. So this 4 is in million. This 1 is in million. So 350 will become what? 0.35. Okay, 0.350. So 4 plus 1 into 3.50. Do you get $4.350 million? You get the prediction, right? So I have assumed for now that beta naught is this and beta 1 is this. Our whole task is to find out a best fit line. When we find a best fit line, we will find out a particular value for beta naught and a particular value for beta 1. That is what we will find at the end of the whole concept, of the whole working of it. Now, let us see. So why I'm saying a certain value for beta naught and beta 1? See, when I have beta naught, it can have any value. Beta 1 can also have any value. So when I take, let's say, line number 1, this is line number 1, this is line number 2, this is line number 3, this is line number 4. Every line that I'm getting will have a certain beta naught value, will have a certain beta 1 value. Make sense? Every line, if you take a look at line number 1, line number 2, line number 3, line number 4. So as I told you, line number 3 is tilted. You see it is tilted in certain way. So it is called slope. So if line number is tilted in a certain way, it will have a different beta 1 value. And line number 2 will have a different beta 1 value. Line number 3 will have different beta 1 value. And line number 4 will have different beta 1 value. And they will also cut the y-axis at different places. Got it? Now, don't worry about the calculation and try to understand this first. I'll show you the calculation. Correct? That is a very big concept. We are just touching upon basics. So it makes sense to all of you that if I'm changing the line, my beta will also change, my beta 1 will change, and beta 0 will change. Is it clear to all of you? When I change my line from line 1 to line 2 to line 3. Correct? That is the concept. That is the whole concept. So let us suppose my beta 1 is 0. Or let's say 1.9. And beta 0 is here, let's say 4. So when I say a certain beta value, in any particular beta value, if I take randomly, what will happen to it? According to this beta naught and according to this beta 1, it will make a line. According to this, I'm making a certain line. If I take, let's say, another beta, and I say beta 1 is equal to 1.2, and beta naught is equal to, let's suppose something. So according to beta 1, which is 1.2, beta 1 is the slope. So according to this, what will happen? A line will be created like this. So the lesser the slope, the flatter the line. The more the slope, the more upward it will go. Basic idea. So for this particular thing, I'm making this line. And for this particular value, let's suppose this is also, beta naught is also, let's say 4.2. So for this beta value, I have this line. Similarly, if I change beta 1 to anything, line will change. If I change beta 0, line will change. So you don't change them one by one, you change them both to get a different line. You change them both to get different line. So if I keep changing these beta naught, beta 1, I'll keep making different lines because a line depends upon these parameters. Got it? A line depends upon these parameters, beta naught and beta 1. By changing beta naught and beta 1, we get a different line. So let us suppose I have created 3 lines here. And let us suppose this is my best fit line. This 1, 2, and 3. Line number 1 is my best fit line, suppose. So for line number 1, there is a certain beta value attached. Certain beta 1, certain beta 0 value attached. For line number 3, also certain beta value will be there. Okay. And let's say for this, the beta 1 may be 2.6 and beta 0 is, let's say, 4.1. Correct. This is the different beta values. Now, what I'm saying is my best fit line is this one, suppose. So according to my best fit line, what I have got certain beta values, which is beta naught plus beta 1. Now let's use this for our equation. I was saying that whenever you find out linear regression, you use linear regression, you get the answer in this format. Okay, beta 0 plus beta 1 into x. Now, what is our task? I said that a linear regression line, when you use this linear regression, you get the equation in this format, beta naught plus beta 1x. But what is our task? To get the best fit line, I should find out proper beta naught and proper beta 1 value. When I have found out proper beta naught and proper beta 1, I automatically get my best fit line. Automatically. So in that case, what I'm trying to do now, I'm trying to show you a mathematics. According to that, you can find out the best fit line and not make any assumption that here my best fit line should be, here my best fit line should be. You don't make it visually. If beta 0, beta naught cannot be same for all the lines. Can never be. Okay. Why it can never be same? See, I'll discuss about that. But I was saying that whenever you have to get a certain line, your best fit line, you should have a certain beta naught and certain beta 1 values. Now, in this case, what will happen? Let's see here, our best fit line is this. Beta 1 is 1.9 and beta 0 is 4. So 4 plus 1.9 into x. So when you have completed your linear regression, when your learning has happened using this linear regression, at the end, you are going to get something like this, an equation like this. What should be the starting point of this? What should be the, how do you calculate beta? I will come up to that. Okay, don't worry about it. It's another calculation. I have to come to that. But for now, you should be clear with this overview. If you don't understand this overview, whatever I talk later will not be clear. It's a very difficult. First time you are understanding these things, it is having a lot of maths. So get the overview first. I'll come up to that. How do you calculate beta naught and beta 1? Everything will be. So suppose what I'm saying is you take a data, you have to make a best fit line. How do you know it is a best fit line? We have to search for a certain value of beta naught and certain value of beta 1. Once we have found out what is the final value of beta naught and final value of beta 1, I get my best fit line automatically. Okay, this is the equation, final equation of your best fit line. How I am saying that best fit line will give you very accurate result? So in this equation, you see x values there. If I give 4 plus 1.9 into that 350k, so 350k will become 0.350. So when I use this, I'll get a certain prediction value. The actual sales, sorry, the predicted sales for the future, I'll get according to this formula. Let us say I take a line which is not my best fit line. Okay, so let us say I take my line number 2. Line number 2 is not my best fit line. So according to that, there will be some beta 1 and beta naught, 1.2 and 4.2, let's say. So I use this 1.2 plus 4.2 plus 1.2 into x. Now, according to this, when I take this equation 4.2 plus 1.2 into, I'll get a different result. Okay. According to this, I'll get a different prediction. According to this, I'll get a different prediction. So which prediction is more accurate for you? You don't know future. What you have the current information, and according to current information, you have to decide which one gives you the most accurate future prediction. So this is the formula of the best fit line. This is the final equation of the best fit line, and this is the final equation of not best fit line. So the equation of best fit line is going to give you accurate result. That is your assumption, and not best fit line will not give you the most accurate result. So what have we come up to? We started that we have to make a best fit line. We don't make a best fit line visually. You have to make a best fit line. Once you create a best fit line, it will create it according to this formula. Okay, according to this equation, a best fit line is created. In this equation, what you have to find out? You have to find out this and this to be found. Once you have found out this, beta naught and beta 1, then you have automatically found out your best fit line. That is the whole concept of linear regression. Whole concept. There are further calculations, we'll come to that, but this is the whole concept of it. You have to memorize this beta naught and beta 1, not mx plus c. It is the same one, you don't have to memorize. You will see this so many times that you will remember it automatically. All these scatter points you have to consider. Okay, all these scattered dots that you see, every single scattered dot, if my data set contains of 10,000 values, 10,000 scattered dots will be calculated, created here. And you have to take into consideration 10,000 data points. And you have to find out the distance of 10,000 white dots to the line, all the 10,000 dots, okay? And then at the end, you compare and you try to understand the total error. That is what it is, okay? calculation will be done in the system. I'll talk about it. For finding that beta naught and beta 1, computer will create. So what is happening? To summarize what we have done till now, we started from here. We have to find out best fit line. Best fit line gives us most accurate prediction. Got it? Now we don't create a best fit line visually. There should be a mathematics involved to get that, to get the actual best fit line. We should not be making any guesswork. So we should be getting a proper best fit line. And to get a proper best fit line, we take the help of mathematics. And the mathematics says that the mathematics of linear regression, which is created by some mathematicians in the past, they said that the equation of my best fit line will look like this. It will not be exactly this. It will look like this equation. Look like this equation means it will, the equation will be in the format of beta naught and beta 1x. Any line. So if I take a look here, if I make line number 1, line number 2, line number 3, line number 4, they all have different beta naught. They all have different beta 1. All of the lines. So when I have shown you, let's say 3 lines are there. Out of these 3 lines, line number 1 is there. Line number 1, I am saying as my best fit line. So according to this line number 1, there will be a certain beta naught attached, beta 1 attached. What is beta naught? Wherever it is intersecting here. Okay, on the y-axis. And what is beta 1? Beta 1 is nothing but the tilt, that slope. Got it? Now, so when I take the beta naught, beta 1 of this is my best fit line. If I change the beta naught and beta 1, I get a different line, which is not your best fit line. Not. So what have you got at the end? You said that your linear regression equation should look like this, beta naught plus beta 1x. So like this means not exactly this. This should be a number so that I can use it for my calculation. If this is not a number, how can I make this equation? How can I use this for a calculation? How can I predict the future outcome? You can't. So this beta naught should turn out to be a number. Now there are infinite possibilities for beta naught, infinite possibilities for beta 1. It can be anything. What we have to do, out of all the infinite possible values for beta naught and beta 1, I found out that it is 4 and I found out that it is 1.9. We have not found it out. I'm just saying that at the end, you will get something like this. Once you have done the calculation of linear regression, total calculation, at the end, you will get it something like this. And this equation looks like this format, where 4 is the beta naught value, 1.9 is the beta 1 value, and x is the input you have to give. So at the end, you will reach this equation, which looks like this. This is the flow that is going to happen. Now, till now, whatever I have told you is the overview, that this is how linear regression works. So if anyone is clear till now, you can explain it in interview. That is the whole concept. Okay. You don't have to understand anything more than that. But since there is a proper mathematics attached to it, we will talk about that mathematics now. Beta 1 and beta naught, both we have to find out, not just beta 1. Both we have to find out. Okay. So when I say linear regression, when I say I am applying linear regression to my data set, that is my whole task. My complete task of linear regression is to just find a beta naught and beta 1. Out of all the infinite number of possible values, I have to find out one beta naught and one beta 0 value, beta 1 value. That will be my final answer. Once I have got that final answer, my task is completed. X is given. X is your future input. Okay, future input. Let's suppose, what is this X value? Let us suppose you have to do house price prediction. Okay, suppose you have to do house price prediction. So what you have done, you have studied the houses of that area, the past house, for which you know their prices. And once you are studying those house prices of the past houses, what you have done, you have created the scattered dots, you fit a line, and you get the equation like this. How do you predict the price of a new house? So that X value is going to be one of the input of that house. Okay, let's suppose that X value is the number of floors. So when I say 4 plus 1.9 into 3, x is number of floors. Let's say 3 floors are there. So x is that input, a particular input for that whatever you're trying to calculate. So when you put that input into this equation, you will be able to calculate it. Similarly, if you're trying to find out anything, any regression sales value or stock price prediction, so you will give those kind of input. You give that input into x, you do that calculation, you will get your final value. So x will be your future input that you are going to take. So if you have calculated beta naught and beta 1, there is going to be a lot of beta naught and beta 1. So you have to find out one beta naught and one beta 1 that will be for best fit line. So when you have got that one beta naught and beta 1 that is for best fit line, you get your best fit line automatically according to that beta naught and beta 1. So you have to calculate the error for all the beta naught and beta 1. Exactly. X value is nothing. See, X value is not a thing to be considered here. X value is the future input. Okay. What I have told you, this X value is the future input. So I told you that when you bring in future input is after making the best fit line. Okay. After making the best fit line, then you give the future input. What your main task is to make first beta naught and beta 1. This will not change. Once you have got the best fit line, so for a best fit line, you will get a certain beta naught and beta 1. Whatever that is, you will get that. Then it will not change at all. You can keep changing X value. X is your input. For one house, there might be 3 floors. For another house, there may be 2 floors. For third house, there may be 4 floors. So X value will keep changing, but beta naught and beta 1, once you have found it out, it will be constant. It will never change once you have found out the final beta naught and beta 1. They will never change. What we have to do, we have to keep changing this till we reach our best fit line. Once we have reached our best fit line, then it is never going to change. All of you must be clear about it. Now, at this point, still a lot of things are to be discussed. That if I'm saying my final value is 4 and 1.9, there should be a starting value, right? From somewhere we are starting, then we reach to the point where we got our best fit. The beta naught is 4 and beta 1 is 1.9. I should have a starting point. Somewhere we are starting with some value we are starting, maybe from 0, maybe from 5, maybe from 10. Somewhere we are starting and then we are improving it to get to this. That is what I will discuss, but don't worry about it. Now, so when I have understood this, if all of you are clear till here, you have understood most of the part. Now, what are we going to talk about? The main mathematics. Whatever I've explained in here, I'm going to write it down so you can use it for studying later. Okay, so before writing down the further mathematics of it, what we discussed is you have a training data. Training data means you take a data and you use it for training a machine learning algorithm for future prediction. That is called a training data. You give a training data to a machine learning algorithm. So I'm just trying to put it to you that what we have done till now. Okay. And what does it create for us? We saw that yesterday. What does it create for us? A function. Okay. It creates a function. Sorry. And what does it create for us? It creates for us a function. Okay. Function. Yeah. So diagram is nothing. We have seen this diagram. There is a training data. You give that training data to machine learning algorithm. I discussed about that. Whenever you use machine learning, what you do, you give a data set to a machine learning algorithm. It creates a model. Okay, it creates a machine learning model. So that model is created like a function. At the end, that model is what? It is nothing but a function. So you use this function for what? You give a future input through this function to get a predicted output. That is what we have seen. Now, what is this function in our case? For every algorithm, this function will be different. They all have their own way of working with it. What is the function in the linear regression? That function is beta naught plus beta 1x. So this function is also called hypothesis function. This function is also called hypothesis function, which is our beta naught, which is in the format of beta naught and beta 1x. This is the whole concept. I have to reach this. What will be my final value? My final value will look something like this, that there will be an equation in the format of this. See, if I just take beta naught, if I just take beta 1, and if I take this input, x is what? X is my input. Explaining once again, you take input in x. What is your task? Before taking your future input, you should have found out beta naught and beta 1 before giving any input, future input. With the past data that you have, you find it out, beta naught and beta 1. Once you have found that out, then you never change it. Okay. Let us suppose what we were talking about, let's say 4 plus 1.9 into x. That is the final thing we have to reach. Once I have reached to this point where I know a particular value for beta naught and I know particular value for beta 1, when I get to this point, then I should never change this beta naught and beta 1. All the future inputs that I'm going to take will be done on this equation only. Only these will change, only this x value will change. 4 and 1.9 will not change after this, because this is my best fit line. Do you change your best fit line? You never change your best fit line. So that is why you can never change beta naught and beta 1. Because if you change this beta naught and beta 1, you're changing your best fit line to something else. So you should never change it. First you find this out, then you multiply x with it. So this was our whole idea. Now you must be asking that how do I know? Till that we have not discussed. How do I know that beta naught is going to be 4 and how do I know beta 1 is going to be 1.9? I have not discussed that for now. I'm going to talk about that. There is some other concept I have to touch upon, but I'm giving you an overview that here I have to reach by the end of the linear regression. I have to reach here where I get a certain beta naught and beta 1. That is the whole concept of linear regression. Find the best fit line. Once I found the best fit line, I'll automatically get this beta naught and beta 0. That is the whole idea. Let's see this hypothesis equation. So this hypothesis function that we have written is to be created. Okay. So it is a very common problem in machine learning. Whenever advanced statistics starts, people start to run away because they think that data science is supposed to be easy. We were supposed to create recommendation engine, AI engines, and the voice assistants, all of those things. Everything will come. But obviously, if it was so easy that all the things would be just simple, then how are you going to get to this? If it was easy, everyone would have learned it, and then there was no concept of data scientist and everything. Because someone can make a software if it is so easy that it would do the task and there would be no requirement of data scientist. It is complex, but what your task is to understand it, give it time, will be clear. So don't run from it. Anything should not be running. Because once you have taken your decision to get into this field, then stay in it. Whatever time it takes, whatever effort it takes, stay in it. So hypothesis function is beta naught and beta 1. And what does it give? It gives us something which is called prediction. And prediction is represented by this y. And what is the formula of it? Beta naught plus beta 1x. Sometime you will see that instead of beta naught and beta 1x, someone will use theta naught plus theta 1x. Yes, it is y cap. It is just a representation, y cap, as a prediction. So what is, there are two things. Y is your output and y cap is your predicted output. What you have to take? You have to take the difference between actual output and predicted output, and that is the error. So y cap is your prediction. It is called as y cap. Okay, now. So some on some of the website, on some of the articles, when you read it, Instead of beta naught and beta 1, they might have used theta naught and theta 1. Same equation, but just different notations. There's no any other change. Sometimes they will be using h naught plus h1x. Okay, these are three terminologies. These are three symbols you are going to see for representing this hypothesis function. Normal y is this, actual output, and y predicted is this. So you take the difference and you get the error, that how much error we have made in future prediction versus the actual. That is the whole idea. Okay, and just to make it clear that for this value, we will move forward from now onwards with this equation. With this equation, it will be a little easier for you to understand. I'm going to show you some other formulas, so it will be easy. What we have to reach, as I told you, we have to reach, let's say, 4 plus 1.9x. You have to reach this. And how do we get to this point? We said that I'm writing it down so you can use it as a notes. Writing it down at multiple times. Let's suppose this is one line, and let's suppose this is one line. Both will have different beta 1 values. Let's say for this, the beta 1 is equal to 1 or 0.6. And it will have a beta naught as something. Let us say this is your best fit line. So it might be 1.2. And it might be 0.8. And where it cuts on the y-axis, it can be 4.2 here, and it can be, let's suppose, 2.8 here. It's a comparison that whenever you change beta naught and beta 1, your line changes and how it is going to look like. So for line number 1 and line number 2. Line number 1, you're saying 1.2 is the beta 1 and 2.8 is the beta naught. Beta naught is very easy to find out because wherever it cuts on the y-axis, that will be given. You don't have to calculate it, just you should know that this happens. Everything your ML will do. Then your beta 1, 0.8 is going to be slope of this line, and 4.2 because it cuts here. So here 4.2 value was there on y-axis, automatically you'll get it. So with this, you understand that if you change theta naught, if you change this beta naught and beta 1, you change your line. So for a best fit line, there will be only one single value of beta naught and beta 1 that will be final. There cannot be multiple value of beta naught and beta 1 because there is only one best fit line. So obviously only one pair of beta naught and beta 1, only one that. To find our best fit line, we use a mathematical concept, which is called this. To find we use something called as cost function. Okay, this cost function is an equation which will help us find out the best fit. Okay, so this cost function is one very popular term that you will hear multiple times in different equations. So now what I'm going to show you is whatever we have seen as a visual, I'm going to put that into some formula, whatever visually we have seen. So to find our best fit line, we use a cost function. Cost function is nothing but whichever line gives you the cost function as least will be our best fit line, and other lines which give you cost function as higher, they will have higher error. So cost function is a formula which will tell us that this is the best fit line, because for a best fit line, cost function will be least, minimum. So how do we get a best fit line? To get a best fit line, we basically have to update and find what? Find what? Theta naught, or let me write. Should I use theta naught, right? There's no problem with it. At just the place of beta naught and beta 1, I'm using theta naught and theta 1. Okay, same thing. Just you can understand. It is going to be easier for you to see. To find theta naught and theta 1, for which what the y predicted, y cap or predicted, is close to y, is close to y. What is y? Actual, for all the data points. Take a look at it. Are you able to understand what I've written? To get a best fit line, we basically have to update and find that final theta naught and theta 1 for which any y predicted value is close to y actual for all the data points. All the data points means what? This one. So my white dots are actual data points and my yellow line is giving me that line. So what we have to do? We have to find out the theta naught and theta 1 values which give me best fit line. Once I get my best fit line, so in the case of best fit line, my actual and my predicted is closest. All the data points, when I take a look, the actual and the predicted will be closest as compared to any other line. That is what I have written. What we have to update? What we have to update? You have to update the theta naught and theta 1. What does it mean? So let's say what your line will do. Your linear regression will do what? Let's say it makes this line. Is this line your best fit line? Don't know. So linear regression will make second line, make third line, it will make fourth line, fifth line, sixth line, seventh line, eighth line, 1,000 line, 1,500 lines like this. How it is making different lines? Updating theta naught and theta 1. Once it has created a certain number of lines, 1,500, 2,000, then it will start comparing them. After comparing them, it will get that this particular line is giving me least error total. That is my best fit line. That is how it works. But now there is a problem, right? Can you tell me the problem? What is the problem with this approach? Everything is fine. The approach is fine. At the end, we will get our best fit line also. But what is the problem here? Can you see something should be optimized? Something can be optimized? What do you think can be optimized in this process? Not the other thing, like outliers and everything, that is other thing. But in this process, what can be optimized? So we can optimize that. Instead of finding out, or instead of making 1,500 lines, then comparing that, can we do something? Can we do some optimization that only after making 200, 300 lines, I get my best fit line? Can we optimize that? Because the lesser number of lines it makes, the lesser time it will make, and our comparison will be done fast, and our best fit line will be find out fast. So that process will become faster if I can optimize that. I should not be making 1,500, 2,000 lines. I should optimize in such a way that I should only make 200, 300, 400 lines, then compare it, get my answer. That optimization also we will have to do, because obviously I can't let it run for 1,500, 2,000. I'm just saying it may be 1,500, 2,000. Maybe it is more than that. Maybe it is going to make 5,000, 7,000, 10,000 lines. What you will do in that case? It's a big equation, and it will become complex, because here I have taken, you see, 7, 8 data points here I have taken, right? So every line, see, if it is making 2,000 lines, for every line, it is doing what? Finding out actual minus predicted, actual minus predicted, actual minus predicted for 10,000 points. Okay, for a single line, for 10,000 points, it is finding out actual minus predicted, then adding it all up to find out total error. So if you have so many lines, so many calculations are to be done, and it will obviously take more time. So we should optimize this process, that lesser lines are created. Lesser lines means lesser calculation, and in faster it can do the task of linear regression. So we were talking about this cost function, that this cost function is something which will give me our best fit line. We have understood it already. How do we get a best fit line with everything? But there is a concept of a cost function. It's a formula which will find out that equation. Okay. So in this case, when we have a cost function, I can give you cost function directly, but we are going to make the cost function. So you never forget. Okay. I can just tell you that this is the function of it, and I'll tell you that remember it. But that is not a correct way. Let us create this cost function. So cost function is for what? Understand, cost function is for giving us the best fit line. So a best fit line is what? Total least error. So first we will start here. We will start with error in prediction. Okay, we will start with error in prediction. How do you get error in prediction? Y cap minus y. Y minus y cap minus y, same thing. Anything you can write. Second thing, what we do. Now, what we have to do is we have to sum up, as I told you, this y cap minus y is for all the data points. Okay, so let's say I pick up this data point. It will have a y value, which is actual dot, and it will have a y prediction, which is on the line. So every single dot has y cap minus y, y cap minus y, y cap minus y. So what I have to do, I have to sum it up. Okay, for every dot y cap minus y, there will be one error I will get, and I have to sum up the errors, as I've told you. Correct. Now, is it going to be okay, or is there a problem in this? Is it going to be okay if I sum it up, or is there going to be any problem? See, if I take the dots which are at the bottom, if I take this dots which are all the dots which are at the bottom, what will happen? This will be a negative error. And all the white dots which are at the top, there will be positive error. So the negative error and the positive error will start to cancel out, or it will reduce the total error. And that is what something I don't want. So what we should do, we can take the mod of it. Okay, we can take the mod of all the errors. One is that solution. But we can't take that mod because of one of the further calculation we are going to do. That does not work with mod. So we can do square. The next best option to nullify the negative, we have to make it square. Correct? That is the next best option. So what we do, we square the errors. We square the errors so that they don't cancel out. So this equation will now take the form of y cap minus y square. So any error that you were finding it here, for a single data point, a single white value, white dot, you'll find out the error and you just square that error. So what you have to do, you have to first find out every error, square it, then add it up. Not just directly add it up, first square it, then add it up. Then the third value will be, so what will my equation become now? For summing it up, there is a symbol used. This is called sigma, or it is also called summation. It's just a symbol. For those of you who have not seen this symbol before, it is just a mathematical representation to show that I'm trying to add up something. So what I'm trying to add up, I'm trying to add up y cap minus y square. So first I'll find out error, square it, then I will add all the errors which I have squared. So this is also given some name. This particular equation that becomes, it is also called residual. These are two more names given to this equation: residual sum of squares and sum squared error. What is this residual? Error is also called residue. That is just a second name to it. So I'm not saying you all you remember all the names that I'm giving for now. Just I'm writing it down. So you take a look at the document and everything is clear to you. That is why I'm writing this all for you. Okay. Number 4, we take the average. Okay. If I have done this, I solved one problem. But when I solve this one problem, there will be another problem created automatically with this. The other problem will be that, see here, if there are 50,000 data points, or 1 lakh data points, or 2 lakh data points, 300k data points, 500k data points. What will be the problem? You are finding out the error for every single data point, for every single 500k data points. You're finding an error and you're squaring that. So once you start squaring more and more and more value, the more data I take, the higher this value start to become. And in the real world, you will be working with, let's say, 1 million data point, 5 million data point. So for 5 million data points, the error that you're getting, you're squaring that up and then you're adding it. So it will start to become a very huge value. Okay. What will happen? Explosion of values will start to happen. So at the end, the error will become so huge when you add them all together. It will become so huge that it can't be stored in the memory. So what we do, we take the average of this number, whatever the number calculation comes out to be, we take the average, then we store it. We take the average of sum squared error, because if the value of SSE will explode and can't be saved in the memory. Can't be saved in the memory. So what we do? We reach our final equation, which will be 1 by n sigma of y cap minus y square. Okay. And now this particular equation is called mean squared error. Mean squared error. Because we are taking the mean of the squared error, right? We have almost reached our cost function. So final cost function becomes, you see, we have created the cost function. I did not tell you that just take up this formula and remember that this is the formula for cost function. Now, whenever you look at the cost function, you can easily tell anyone because we have created it. You started with y cap minus y, and then we have got to this certain point. Now, when we create this cost function, we take this equation and we just attach a 2 here. But this 2 will not do anything. If you're dividing by 1 by n, you divide by 1 by 2n, does not make any difference. N is what? N is the number of data points. So if your training data has 1 million data points, you first find out their sum squared error and you divide by 1 million. So that higher value, that huge value that you have got will reduce a little. Okay, so that is one step we take. And then if I multiply by 2n, multiply by 3n, it does not make any difference. But it will be used in the optimization process. Okay, so I is equal to 1 to n and y cap minus y and square. This is what? This is our final cost. Average error is what? Once you have found out the total error, you have just taken the average of the total error. Why we have done it? Just because whenever your data is huge, your total error becomes high. Then you take the average of the total error. It is obviously in the end also, you can say that it is also the total error. But again, yeah, in more technical terms, you can say it is a mean error. See, what is this I is equal to 1 to n? I is equal to 1 to n means if you have 10,000 data points, okay, sorry. If you have, let's say, 10,000 data points, so what happens? You're doing a summation of for all the 10,000 data points. I is like nothing, that for I is equal to 1 to, for I in range 10,000, you write that loop. So what happens? Loop runs from 10,000 times, for 10,000 times. So now this is the same thing. A loop is running for 10,000 times from I is equal to 1 to 10,000. And then what will happen? This calculation is happening. What calculation? You find out the predicted value, you square the predicted value, then sum it up for 10,000 data points. Got it? So this I is equal to 1 to n is that. the fourth step. Now, what is this cost function? Let me just give you the final answer. What is this cost function? So this cost function will give us, this is the equation that gives us the best fit line. Okay. So we have understood the overview of that. And when we have to do the same thing mathematically, if I have to find out the best fit line mathematically, this cost function will take us, will do it for us. Now, what is our main task? Our goal in linear regression is to minimize the what we have to minimize. Error, okay, error is there, but the cost function, right? Minimize the cost function. Yeah, number of lines I have not talked about. What we have to minimize? When we minimize the cost function, automatically I will get a best fit line. So go through this equation. So for now, what I'm saying, for each line, if I have created 1500 lines, for each of the 1500 lines, this cost function will be calculated. Cost function is nothing but the total error if you look at it. The total error that I was talking about, it is nothing but a total error for a single line. For if my linear regression is creating 1500 lines, so for each line, 1500 cost function will be created for each 1500 lines. And then the cost function of each line will be compared to give me the best fit line. Now, whichever line has the least cost function is my best fit line. This is the whole concept of linear regression. But you go through this and you will understand the proper working of linear regression. You cannot get easier explanation than this. I can guarantee you that. And if you go through it, you will have a very strong foundational concept in this case. Okay.
I have one more announcement for you guys. For dedicated learners like yourself who want to make a difference in their career, for the first time, we at Intellipaat have decided to offer a straightforward 20% discount on our premium data science course, which is in collaboration with iHub IIT Roorkee. If you want to take control of your tech career and do something extraordinary, do visit this link in the description box given below and fill the inquiry form. Promptly, a team of course advisors will reach out to you to activate the offer. So don't miss out this opportunity.
Now, the best fit line is going to give you the best prediction for that data. That is the concept we have seen, and there is only one best fit line. There can never be more than one best fit line, always just one. Because that is best, you are saying. No, there can be not two people best. Better, there can be many lines, but best is only one. So in this case, we saw that we actually take help of this cost function to identify that which line is my best fit line. This cost function actually helps for that. But the problem here was that when we take a help of cost function to get the best fit line, there is a problem that it is going to create many lines and then it will start comparing out of those best line out of that. So in this case, what it was doing, it was making a lot and then start to compare them. Which line has least error? And that's a problem because I don't know how many lines it will make and then start comparing. It might make 2000 lines, 5000 lines, 7000 lines. I have no idea about that. So the bigger the data, the more complex it is going to become. Right. The bigger the data, the more complexity will come into my my approach of this linear regression, that it is going to make more lines because the data is huge and it will be time consuming. That is the very obvious thing. Now, so what is this gradient descent? Gradient descent is an optimization algorithm which is applied with the linear regression to make that process little faster, that gradient descent. So what is this gradient descent? Let us try to understand this. Now, gradient descent is one of the mathematical algorithms which is actually going to help you for the process of optimizing. It's a mathematical algorithm. And it is not just used in machine learning, it is used in a lot of the other places also for the optimization. So the people who created this algorithm, this machine learning algorithm, linear regression, they saw that this gradient descent can be applied with that linear regression to do the optimization of it. So gradient descent is an optimization algorithm that helps minimize the cost function faster. And in doing so, it gives us the best fit line. So it's an optimization algorithm that will help us to minimize the cost function. What do I mean by minimizing the cost function? Minimizing the cost function means find a line which is minimizing the error. That is what I mean by saying minimize cost function. Find a line which is actually minimizing the errors. Find that. So it is an optimization algorithm that is finding a line by minimizing the cost function. And in doing it gives us the best fit line automatically. Because once it is finding the line which is giving you the least error, that is our best fit line. So we automatically get. Now, the question was, if we have to find our best fit line, if we have to make our multiple lines and then compare to find the best fit line, where do we start? Okay, because there can be multiple ways we can make the line. So where do we start? We actually start with this concept that theta 0 and theta 1 both will be 0 at the start. I will start here. And then I will keep updating theta 0 and theta 1 to reduce the cost function until we reach the minimum of that cost function. This j theta is the representation of the cost function. It is the symbol used to represent cost function, if you can see. So what we do, we start with theta 0 is equal to 0 and theta 1 also 0. That is my starting point. And I say that keep updating till we reach to a point where we get our best fit line. So if you remember last session, I told you that you get to the best fit line by updating theta 0 and theta 1. There will be a certain value for theta 0 and theta 1 that will give that best fit line. You need to keep updating. Now, how that updation will happen? These are the two steps which gradient descent is. Start with theta 0 and theta 1 with 0 and keep updating it till we reach the best fit line. These are the two main concepts of that. Yeah, so you know what is theta 0 and theta 1? Do you remember what is theta 0 and theta 1? It is the concept of the y cap in itself. So when you write y, what it is the hypothesis function which is created out of theta 0 plus theta 1x. Right? That is what is hold inside of y. So y cap also has theta 0 plus theta 1x and yi also has theta 0 plus theta 1x. Okay, right. So what we do, we update our this theta 0 and theta 1 to get our best fit line. Those are the two main concepts. Now, when you take a look at this gradient descent algorithm is actually this formula. You don't need to remember the formula for now. Automatically, by working on it, you will be able to remember. Just before going to the interview, you can remember it for that part. But let me make it very simple for you to understand. See, it is actually using the concept of differential calculus, which will be taught to you in the later sessions in proper detail. But don't worry, I will tell you what it means and you don't have to go into that much of mathematical depth. All these formulas will be applied by the algorithm itself. It is written for you. You just need to understand how it is working in the background. It is all written for you. So what we have in this gradient descent algorithm, we saw that we have to update this theta 0 and theta 1 till we reach a point where we get the best fit line, which has the least or the best theta naught and theta 1. So how that updation happens? That updation happens with this formula. We are saying that take theta j. Theta is nothing but a common representation of theta 0 and theta 1. Okay, both. So how theta 0 and theta 1 will be updated? You say theta 0 is equal to theta 0 minus alpha, this derivative of theta with the j theta. Don't need to go into the complexities. Just understand what this formula is doing and how it is finding the best fit line for you. This I have written, this is an alpha. Alpha is actually going to give the speed to the process of finding the best fit line. And this whole box that you're seeing, this is going to give direction to you to find your best fit line. So gradient descent has two very important things, two important things it does. First, it gives a direction to my approach. Second, it gives a speed to my approach so that I can find the best fit line very easily. So let us understand what is this all about. So suppose I have this as my best fit line. This is my best fit. Now, without gradient descent, what cost function will actually do? It will randomly make lines. It will make this line, this line, this line, this line, this line, this line, this line. It will randomly make multiple lines. And by making randomly many lines, there will automatically be one line which will overlap on the best fit line at the position of the best fit line. That is how cost function will work in itself alone. It will just randomly make the lines. But what gradient descent says that don't make the lines randomly. You're not going to get to your best fit line in a proper time. You will take a lot of time because you are making just lines randomly. So what gradient descent says to the cost function that, okay, don't jump randomly. Start from 0 and 0. Start from theta 0 is equal to 0 and theta 1 is equal to 0. So theta is 0 is equal to 0 means the line passing from the origin. Origin is a point which is actually this point. Okay. At this point, if a line is passing through, that is called that theta 0 is 0 there. Okay. When you plot the lines, you will see that here it is 0. So that is also 0 and theta 1 is also given 0, which is the slope is 0. So when the slope is 0, then a line is created properly flat. Okay, a line is created properly flat. So the first line that gradient descent will create with theta 0 and theta 1 will be a line on the just the x-axis, properly on the x-axis, a very flat line. Then from there, what it will do, it will start to move in this upward direction. Yes, not parallel to x-axis, just on the x-axis. It will be on the x-axis. So now the x-axis is that you will not be able to see. It will be on the x-axis. So what gradient descent tells them? First thing it has told that start from this point. That is your starting point. Then suppose this yellow line is your best fit line. Okay, yellow line is your best fit line. And you are starting where? You are starting here. This is your first line that is created. And you have to reach the yellow line. So what gradient descent will tell to this line that you have to move in this direction. In this direction, when you move, you will find your line. Okay, you will find your line. Okay, so gradient descent says that we start from theta 0 is 0 and theta 1 is 1. So in this case, what are you seeing? First, it has given the starting point. Second, it will give the direction. That if the first line is this, where you have to move in this direction and you will reach your best fit line, because yellow line, which is your best fit line, is available in that direction somewhere. It does not know that is the best fit line, but it will reach in that direction. And by reaching in that direction, just in few minutes, I will tell you how does it know that this yellow is the best fit line. At the start, it does not know, but it will know that in which direction my best fit line is. That direction it will know. Once it knows this direction, then there is a speed it will give to my approach. Speed means, see, if I just take plot here and my best fit line is at this point, suppose, and where do I am starting at this point, and I have to move in this direction, this much gradient descent will know. It will not know that exactly here your best fit line is, but it will know that I have to go in this direction. That much idea it will have. And then what it does, Once the direction is given and once the starting point is given, then it will give a speed to it. What will happen with the speed? See, if I keep the speed very less, speed is actually given by this alpha value. If the speed is very less, then what will happen? A very small changes to the line will be happening, a very small updation in my theta. And with very, very small updations, I will start to move upward. Small updations. But if I keep the that speed higher, little higher, then what will happen? One line will be created like this, one line like this, one line like this, one line like this, like this, like this. And after a few iterations only, it may reach my best fit line. But can you think of any problem that will happen if I keep my speed too fast? Yes. So what problem might happen if I go faster? Because if I say I can go faster, then you will say that that is the best thing. If I can go faster, I can reach it uh, very soon. But in that process, it can miss the best fit line. It can miss the best fit line because the speed is too fast. So suppose the best fit line was here, but it will jump the best fit line. And then it will keep moving in this direction where my best fit line is not present. So it will be wasting the time. But that also does not happen with gradient descent. Suppose in a certain this speed, I'll tell you how speed is also something you can play with. But let's say we have taken a speed and my line jumps the best fit line. It misses the best fit line and then jumps beyond it. Then also gradient descent will do what? It it is going to ask this white line to come back in this direction. Okay, it will change the direction of approach and it will tell it to come in the backward direction. How gradient descent is telling everything, just in few minutes, I'll explain you that. But gradient descent will tell this white line to come in the backward direction. There your best fit line is. What we have said with the gradient descent, three things. It gives a starting point that start with theta 0 as 0, start with theta 1 as 0. And you have to reach to certain theta 0 and certain theta 1 values. I don't know what it will be, but it will be some value. Theta 0 can be 3.2 and theta 1 can be 0.57 or 1.76. Whatever it is, I don't know that. But I will be able to find it out by working with this gradient descent. So I start at a 0 point. First thing is that. Second thing, gradient descent will tell me that I have to go in this direction, upward direction. That it will know. When you're moving in upward direction, then third thing that gradient descent will give it will be a particular speed. Move with a certain speed. Now that speed is cannot be too high, it cannot be too low. So we have to play with it. So this alpha value that you see here, its range is from 0.001 to actually 1.0. Okay, the general range of alpha ranges from 0.001 to 1.0. That's big range, but you have to try the multiple values to get to a certain alpha because you will not know what should be the speed of this approach, but you can play with it. You have to do the experimentation in that part. So starting point, the direction and the speed, and by chance if it misses, my line misses the best fit line, it goes beyond it, that gradient descent will tell it to come back also. All of that happens with this formula, the gradient descent, the direction and the speed part. Take a look at it. So suppose my line has jumped past the best fit line. And when the gradient descent will tell it to come back, will that be with the same speed or it will be reduced? It will reduce the speed, correct? Because if it come back with the same speed, then it will just jump from here to here. And then it will jump from here to here. Then it will jump from here to here. Keep jumping between those lines. So it is obviously going to reduce the speed because it knows that I have taken a too much speed and I have to update that speed to come back in a reduced manner. That also will happen. Okay, so now when I'm saying that speed is faster, then it is making less lines. Okay, so why it is making lesser lines here? You should be able to understand. It's a very simple thing because let's say I tell you to go 100 meters. And in one case, I tell you that you have to take small steps. Okay. Small steps you have to take to reach 100 meter. But if I tell you to jump and reach 100 meter, so if you're jumping long steps, so obviously you will take lesser steps to reach the 100 meters. That is why here also the lines are less, because when the speed is high, it is updating the values very largely. That is the case. See, gradient descent is not knowing that here your best fit line is. This green was one is your best fit line exactly here. Gradient descent does not know that exactly. Gradient descent knows that your line is in this direction. It knows that. Where it does not know that at the start. It will be able to find that out in the process. But it knows that it is somewhere in this direction. But there is a mathematical formula, there is a mathematical concept which will tell the gradient descent if you jump past that line. How? Just wait 2 minutes. I'll talk about it. How? So this is the gradient descent algorithm, and updation of the theta happens with this formula. You can remember this formula later, but you have understood the concept. Let's move forward. Now, alpha is the learning rate that controls the speed of the descent. How fast you have to go in the direction of the best fit line, it will control the speed of that. Now let us understand here, how am I saying that it will know where the best fit line is? Because it does not know that green line is my best fit line. This green line I'm saying is line. It does not know that. But there is a mathematical concept which will tell that here my best fit line is present. And that is according to this curve. Let us understand what this curve is actually telling us. Understand this very carefully. Now, there is a curve which you create when you plot the theta and the cos function. Okay. So let's take a certain theta value. And by taking that theta, if you make a cos function, if you change the theta from this to say theta something, okay. If you are changing that, then what will happen? The cos function will also change. That is the case. Now, what we are doing here to this curve very properly in a very easy manner, make an assumption that our line is passing through the origin. What I'm saying is that our best fit line is actually passing through the origin here. This is an assumption made for us to understand how this curve is actually created. So if the line is passing through this origin, then it means that theta 0 is going to be 0. That is an assumption we take. And we just say that we will change the theta 1 and we will try to see how the things are happening, how that optimization is happening. So we keep an assumption, theta 0 is equal to 0. Because if I take theta 0, then it will be very difficult for me to explain or anyone to explain you this concept. They will have to make a 3D kind of line. That is not possible. So we are making an assumption that the line passes through origin and theta 0 is 0. It does not create any problem for you. You will be able to understand. Suppose I have taken a theta is equal to something. Suppose I say that my theta 1 is 0, where I actually started. Suppose. So when your theta 1 is 0, where it will be? Your theta is being plotted on this line, on the x-axis. So it will start from 0, then 0.1, then 0.2, then 0.3, something like that. It will just go in this direction. So when it is 0, it is actually somewhere here. Okay, there is a curve created by updating the theta. When you're updating the theta, automatically this curve is created. That is the property of a curve when you plot theta with j theta. That is a property of curve. Always this type of curve will be created. And this is called a gradient descent curve. Now, what happens here is we started with theta 0. And let's say I have updated the theta 0 by making a further line. And then let's say the theta 0 has become 0.2. I have updated the value, and now theta 1, which was 0, it has become 0.2. So this curve is actually going to tell me where your line is present. So this 0 point, say, falls somewhere here. If I take theta 1 is equal to 1.8. That will also fall somewhere here on the line. You see, on the x-axis, I have the values like 0, 0.1, 0.2, 0.3, 0.4, like this, moving in the forward direction. So any theta value I take will fall on this curve. Now, so suppose I have taken 0.2. Now, how will the gradient descent know that have I got my best theta or not? So to get your best theta, your dot should be actually here. You see this dot? This is the minimum of this curve. When you create a curve between, or when you make a plot between this theta and j theta, a curve is created. And there is only one minimum of this curve, which is actually this dot. So if you have to find out the best theta, your dot of that line will fall on this point, at this point. Okay. Every line that you create will be represented by a dot on this curve. Every line you make. So if you're making, let's say, this line, there will be a dot. If you're making this line, there will be a dot. If you're making this line, there will be a dot. If you're making this line, there will be a dot. So when you're moving in the direction of your best fit line, see, here your best fit line is, and when you're making the dots. So if the line is on the below side of the best fit line, so the dot will be on the left side of this curve. Understand? That suppose your line is here, the best fit line of any equation is represented by this dot that you're seeing here at the minimum of the curve in this one. This is the representation of the best fit line, and that will be created automatically once you plot the theta and j theta. And you have to reach this point. So what happens here is you started from theta 0, then you updated theta to something, then you updated it again. If your line is in the bottom side of this best fit line, so there will be a dot created on this left of the curve, this left side somewhere. If the line is on the right side of, or on the upper side of this best fit line, so a dot will be created on the right side of this curve. Okay, that is the property. Now, when a dot is created here, this curve will actually tell us that where I have to move. If the dot is here, I have to move in this direction. And if the dot is here, then I have to move in this direction. Okay. That is the thing. So take a look at it. Theta 1 is the slope. J theta is the cos function. I just told you that j theta is the representation of a cos function. So I am plotting my theta and the cos function. So according to any theta, a different cos function you get. See, I'm starting once again. What we said here, we said that to reach our best fit line, what happens? You start from theta 0 and theta 1 is equal to 0. You start from this point, which is this line, line number 1. And your gradient descent tells you to move in this direction, upward direction, to reach your best fit line. But gradient descent does not know where exactly the best fit line is, but it knows the direction. So I was telling you, how will it know that which is the direction? Upward direction, downward direction, how will it know? So see here, try to understand this with this concept. Suppose this green line that I have created is my best fit line. Got it? Start from here. So there is a curve which is called a gradient descent curve, and this is what you're looking at. It is called a gradient descent curve. And gradient descent curve is a property which when you plot theta and the cos function, when you plot their values, you get a curve like this. How I'm making this theta and j theta? I told you that suppose if you take theta 1 is equal to 1.4. Teja, I just told you that j theta is this cos function, right? Cos function, this equation. Let me simplify that. Okay. See, when I say a theta 1, suppose is 1.4. So for this theta, you get a cos function. Okay, you get a certain cos function. Let's say it is 78.6. That is what happens when you make a line. one line will give you this much error, another line will give you this much error. Cost function is nothing but total error made by the line. Simple concept. There's nothing more than that, right? So if I have, let's say, a particular theta, according to a particular theta, let's say this is the line I'm creating, and the cost function for this is 78.6. I'm plotting that with a curve. So on the j theta, there will be different cost. Yes, not in the real case. It will not be theta 0 in the real case. Just for understanding purpose, we are making with this. But in the real actual implementation, theta 0 will be there. But I can't show you because it's a 3D curve and you will not be able to understand the concept. That is why I started with an assumption that let's keep theta 0 as 0. So when you said that when you change a theta, let's say when you have taken a theta 1 is equal to 1.4, you got the cost function as this. So with theta 0, theta 1, you have got this line. Suppose I change theta. Let's say I make this theta as 0.8. So what happens? Another line will be created for another theta. And suppose the cost function for this one is 98.4. Suppose. So which one seems to you better? This 1.4 is better because the cost function, the total error, cost function is what? Total error made by a line. That is what cost function is. It is nothing. So when you take a certain theta, the cost function is this much. When you change the theta, cost function increases. It means that out of these two, which one is the best? The theta 1 is where 1.4 is the value. It is better because it has least cost function compared to 2. So that is the concept. I'm saying that when you change the theta values, when you try theta is equal to 0.1, 0.2, 0.3, 0.4, 0.5, when you're updating the theta from 0.1, let's say when I said that theta 1 is equal to 0, your line will be here. If I say theta 1 is equal to 0.1, your line will be like this. When I say theta 1 is equal to 0.3, line will be like this. Increasing the theta, it is going in the forward direction. Makes sense? That you should remember because we talked about this. So here, let's say we have created, you have started, I just said very simply, you started with theta 1 is equal to 0. So when theta 1 is equal to 0, what is the slope of the line? I just told you that it is flat. There is no slope of the line. It's a very flat line, completely flat. So where it will be, this line will be on the x-axis. There I'm starting. Then I updated this theta 1 to 0.2, suppose. I updated it. And now, when I updated it, then in this case, what will happen? If you updated the theta, then your line will be updated. For a different theta, a different line will be created in this concept, in this direction. Now, once you are moving in this direction, if I update it even more, let's say I make 0.2 to 0.3, then the line will be created according to 0.3 in the above direction. If I make it, let's say 0.5, then what will happen? The line will be increasing. The more you increase the slope, the line goes in the upward direction. That is the concept of the slope. A higher slope means the upward going slope. Now, so when we start updating, our gradient descent does not know that my best fit line is present here. It does not know. But it certainly knows the direction of this approach. How does it know? That is what I was telling you. That when you make a plot of theta and j theta, how I'm making a plot of theta and j theta is this. So suppose I have taken theta 1 is equal to 0. The cost function of this is, suppose let's say 240. When I took theta 1 is equal to 0.1, the cost function reduced to from 140 into, let's say, 203. When I update the theta 0.2, the cost function reduced again to, let's say, 195. Similarly, I keep increasing it. You see, till a certain point, the cost function will keep reducing. What does this mean, the cost function reducing? That we are moving in the direction of best fit line. That is why cost function is reducing. when I'm moving in this direction, when I'm updating the theta. So on this curve, if you take a look, if I say like this, 10, 20, 30, 40, 50, suppose by taking theta is equal to 0.2, the cos function is 98, 98.6. So somewhere here 90 will be there, and here a dot will be created representing this 0.2 and 98.6, right? A dot will be created here according to a theta, and be a cos function. And when you take a theta and that cos function, you plot a dot here. So very similar to that, when you make multiple thetas and when you make multiple cos functions, if you start to just plot them and when you connect them together, this curve is created. That is how this curve is created. And now, when this curve is created, this is the property of the gradient, that when you update the theta, there is a certain j theta attached. And when you start plotting them, theta 1 is equal to 0.1, theta 1 is equal to 0.2, 0.3. When you start putting the dots, it will be in this direction, and then you connect them. You get this curve. But I did not want to go into that. Basically, you understand simply that there is a curve of gradient descent, which is having the value of j theta on the y-axis and theta on the x-axis. Now, what happens, how my gradient descent knows where my best fit line is? Our whole agenda was to understand that. How does it know where it is present? So I told that there is a curve created and there is only one minimum of that curve. It is called minima of the curve. That's a mathematical concept, but you just understand for now. Minima of the curve. Always there will be just minimum. There cannot be multiple minimums, just one minimum. And this dot here at the minimum point tells us about the location of best fit line. This green line, it tells us about the location of that. Suppose my best fit line has theta 1 of 0.76. Suppose. I don't know. Where I started with theta 1 is equal to 0. Then I started updating the value. In the first case, this was my value. In the second, I updated it little. Let's say make it 0.1. In the third time, I updated to make it, let's say 0.18. In the fourth time, I made it, let's say 0.24. So slowly I'm moving in this direction. And when I reach this point where theta 1 becomes 0.76, my curve will automatically tell me, you need to stop here. You have got the best fit line. It will tell me. How does it tell me? Suppose I have taken a theta 1 is equal to 0.1. A point will be created at this, somewhere here. You see, theta is the values on this, 0.1, 0.2, like this. The values are on this side. So suppose you have taken theta 0, you started from here, you made a small updation. You made the small updation, that point will fall here. So it tells us that the line you have created, let's say this is that line number 2, which is with theta 1 is equal to 0.1. This is my line number 1. Are we close to that line? No, we still have to do updation. So my curve, this curve will actually tell me to move in this direction. Moving in this direction means move in this direction. You have taken a very high speed and you jumped past. You have jumped it. So this jumped line, there will be a dot on the right side somewhere here. When you jump the best fit line and when you move the upward of that, the dot will be on the right side of this minima dot, on the right side. So how did I tell you that it will tell my line to come in the backward direction? Is that a dot will be created on this curve on the right side, and your gradient descent will tell that no, don't go in the forward direction, come in the backward direction from here. So from here, my lines start to come in the backward direction. Correct? That is the concept. Got it? That is the concept. So this is the concept of gradient descent. If your theta is, suppose if your line is on the left side, if your line is at the bottom of the best fit line, understand this. See, I told you if your line is at the bottom of the best fit line, understand this. Then what will happen? For this bottom line, for this line, a dot will be created on the left of this dot, left of this minima dot. If my line jump past the best fit line, so a dot will be created somewhere on the right of the minima curve. That is the basic concept. So how will gradient descent tell this to come backward? Because gradient descent is backward, because a dot will be created on the right side, and where your dot is, it has to come in this direction to come to the minima point. My line has to come to the minima point. Any dot I'm making is representing a line. I told you that there are multiple lines are created in linear regression. A dot is representing one line. Is this line my best fit line? No. Which is the best fit line? At this point. If I reach this point, if I get a dot for any line at this point, that is my best fit line. That is what I said. So what is happening? You got the idea, and that is the whole concept of, that is the whole working of gradient descent. So, and the one last thing. See, one last thing I told that, yeah, this gradient descent is the standard. Every time the gradient descent curve will be created exactly like this, which will have one minimum and all the other points will be away from the minimum. One minimum means one minimum represents there is one best fit line. And this is the dot for a best fit line. And what is the value here? Okay, what is the value here? I told you, let's suppose that theta1 is 0.76. That is my best fit line equation. So that will be here, 0.76. Now you don't have to do the calculation of minimum, don't have to do calculation of this curve, anything, everything is done for you. You just have to understand this, how it is working, how updations are happening, how my gradient descent knows where the best fit line is. Everything is understood here. Everything is explained here. Regardless of the values of the data, your curve will always work like this, always. Just as a last explanation, as the very last explanation, how this curve is created, let me explain you that. If anyone has that doubt, how is that actually created? So j theta is nothing but my cos function. Understand this. How am I saying that a curve will always be like this? Why? So I said that you take a certain theta. Okay, you take a certain theta. Let's say, where do we start? We started at theta 0. And let's say this is my theta 1. You started with theta 1, 0. Then what we have to do, we have to update it. Let's say I made it 0.1. Then let's say I made it 0.2. So I made it 0.3. I made it 0.4. Made it 0.44, something like this. I made it 0.56. So it does not update like this, 0.1, 0.2. 0.1 will be there, and then 0.14, 0.22, 0.23. Random updations will be there. After that, let's say you started making all of these lines and you reach to a point where theta 1 is equal to 0.76. This is my best fit theta. I did not know that. Where did I start? I started here. Then suppose I other theta values also 0.84, then 0.96. Okay, I'm just going multiple values. If I take multiple values, see, I got some numbers, right? I have theta values, and according to every theta value, there will be a cos function, different cos function. What is this cos function? Total error made by the line. Cos function is nothing but the total error made by the line. Total error is what? It is the number. It can be any number. Let's suppose when you have created theta 0, the cos function is somewhere around 240. I said that. Then for 0.1, the cos function reduced. It became from 2 into this. Then for this, the cos function reduced a little more, 197. For this, the cos function reduced even more. And at this point, let's say it is 187. Similarly, for all of them, there will be a cost function. But what I'm saying here is when you get to this theta 1, the cost function for this will be minimum, and you can say that, let's say 57.9. There will be no other theta value for which the cost function will be lesser than this. No any other theta value. So how do you get that curve? You take the theta values, and theta values are plotted here, 0.1, 0.2, 0.3, like this. Theta values are plotted here. And the cost function, which is like 10, 30, 50, like that, it is here. So suppose I take theta 0 is equal to this, and cost function is 240. There will be a curve here. There will be a dot representing cost function is this, and the theta is suppose 0. I'm just saying that. So this will not be here actually. This will be on the line because the theta 0 is 0. So the first dot will be here. Second dot for theta 1, it is 203. So it has reduced a little. It will be somewhere here. Cost function and the theta value. Then a line will be like this. Then a dot will be like this. 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 For all the theta values, a dot will be created, and they will be always plotted like this, always. And how did I get that curve? We are doing nothing, but we are just connecting these dots. That is how that curve is created. Now, after this, there should be no doubt. That is how the curve is created. And I know that there is a theta value, which is 0.76, theta 1 value, which is giving me the best fit line. How it is giving me the best fit line? So see here, this point is my 0.76. Okay, this is my 0.76. And how is the best one? Because you see, the function of this is minimum. There is no other dot which has the cost function lesser than this. This is that point. They have a quadratic equation. How they have a quadratic equation? We already saw that. There is a quadratic equation. Why? Because you see, there is a square in the formula. Because of this, the curve is created like that. There is a square in the formula. But many people have no idea about that, so I'm not talking about it. But if you have the idea about that quadratic equations and everything, that is in the formula. Yes, you have to just understand the concept. No updations have to be done by you. It will be taken care by code. Code has already been written for you. You just need to understand the previous concept. Mostly it is on assumption, because a lot of people, of the things I can't show you. It is either 3D or it is a very bigger calculation. But if you explain it in this way that I have explained, that is more than enough. No one is going to ask you this. So suppose the speed I was talking about. So let's say I told that when your line jumps past the best fit line, and suppose it is here. Why it happened? Because our speed was too fast. So I said that when it has to come back, it will reduce the speed. How it will reduce the speed? It is like this. So see here, let's suppose it has jumped the line at this point. Okay. It has jumped the line at this point. Let me explain you how. So suppose this is my dot. This is the dot. It is on the right side. Why? I have explained that. If any line is beyond on the upper side of the best fit line, a dot will be created on the right side of this curve. Explain that. So how am I saying that it is going to reduce the speed if it is coming back? You see, whenever you are at the top, whenever you have to come down, the speed is very high. The jumps are very high. But when you start coming towards the best fit dot, it automatically reduces the speed. That is the property of this curve. It automatically starts to reduce the speed. That is the whole property. You don't have to do anything. It takes care of that. So at the top, when you are very far away from the minima point, the step will be huge. It will be jumping a bigger step. But as soon as you start to come closer to the minima, automatically the speed reduces. That is the property of this curve, of the gradient descent. Okay, make sense? That is something you just need to keep in mind. How that reduces according to this. Before talking about what are the advantages, what are the disadvantages of linear regression, there is a very important thing that you need to understand, that you need to know about. So you see here, in when you talk about linear regression, you have two types of linear regression. One is called simple linear regression, one is called multiple linear regression. So simple linear regression is actually a very old concept. When it was created for the first time, it was created format. So simple linear regression says that there is one input and one output. That is simple linear regression. But if you take multiple input and one output, it becomes multiple linear regression. Input is what? The input column I'm talking about. So suppose you are doing the house price prediction. Suppose. And for the house price prediction, if you just take a look at number of rooms and the price, then it becomes the case of simple linear regression because you are taking only one input into consideration for the output. But if you take the number of rooms, number of bedrooms, number of bathrooms, number of floors, how much is the land area, what is the location, how much it is far away from the railway station or airport. When you take multiple inputs into consideration, then you get multiple linear regression. So in the real world, actually, you will be using multiple linear regression. Simple linear regression, you're not going to use. But we have to understand this because with this, we will be able to understand the concept of all the working of linear regression. With multiple, no one can explain you that working of linear regression. Now, what changes? Everything we have understood now was according to the simple linear regression. X-axis, I took the marketing budget. On Y-axis, I took the sales. Simple linear regression. Okay, anywhere, if you watch the video of anyone explaining this concept, they will always explain with simple linear regression, never with multiple. It is not possible to explain with multiple. So explanation for multiple is also 100% same. What is going to change? Only the equation of that hypothesis function is going to change. Let's see. So the equation will now become this. Earlier, the equation was theta 0 plus theta 1 x because there was one x, only one input. So that is why it was theta 0 plus theta 1 into x. Now suppose instead of just one input, which is my x value, I take four input columns. The first input column I express as x1, x2, x3, and x4. x3 may be number of rooms, number of bathrooms, number of floors, and the land size. These are the four inputs I'm taking. So every input column is represented by the x value. x1 is my first input column, x2 second input column, x3 third input column, x4 fourth input column. So when you take multiple linear regression, the formula changes like this. Theta 0 plus theta 1 into x1, theta 2 into x2, theta 3 into x3, theta 4 into x4. Okay, so for four input column, your equation will look like this, as opposed to theta 0 plus theta 1x. That is one simple change that happens. Take a look at it. See, it is supposed to be difficult. If you run away, then you can never learn. Okay, now, so you have this input columns. And the multiple linear regression says that these are the things. Now, what will happen here? In the gradient optimization has to be done. Now, whatever best fit line is will be created according to all the thetas. How is that is not the concern of yours for now, because it will not be, we will not be able to draw it. It will be in multiple dimensions. So now it is not the actually slope. It is actually a certain weightage given to the columns. Okay, it is not actually the slope. It is a certain weightage. So let us see here, how will it work like? If you can see here, let's suppose We have to now find out theta 1 also, theta 2 also, theta 3 also, theta 4 also. Earlier, what we were finding is theta 0 and theta 1, because only these two things were there. We started with theta 0 is equal to 0, theta 1 is equal to 0. But now I will start this with 0, this with 0, this with 0, this with 0, this with 0. Okay, don't go into technicals. Just the way they were updated, in a similar way, this will also be updated. If you try to visualize it, it will be very difficult to visualize. That is why that explanation we are not doing. So we will start every theta with 0, then we will update the values. So now these are not actually the slopes, because you can't have multiple slopes. These are weightage given to input columns, different weightage. So see here, let's suppose I have taken theta 1 is equal to 0.1. Theta 2 I have taken 4, theta 3 I have taken 10, and theta 4 I have taken -2. So these are different weightages I am giving on the basis of this to understand. Now, when you take a look at these theta values, that is just the explanation, example to help you understand. Now, what we do with it? The weightage will be decided by the algorithm. Who decides these weightages? The gradient descent. The way it has found out the theta 0 and theta 1 for us, the same way it will find out these weightages for us. We don't have to do anything. Okay, don't have to do anything. So now what we do, we have this equation, and the equation will now look like this. Take a look at the equation. Now what we will do here, I told you that you use the linear regression line. Okay, what we have the equation like this. Now according to this equation, a best fit line will be created. So best fit line will be impacted by these weightages. X1 has how much weightage, X2 is how much weightage, X3 is how much weightage, and X4 has how much weightage according to theta. There will be just one line created, not multiple lines. These are not slopes. There will only be one slope. Don't have to go into that. There will be only one line created, like a best fit line. Exactly like how we have seen in the past, same way it will happen. These are just weightages given to multiple inputs. Got it? Now, don't try to visualize that according to it. I told you, you will never be able to visualize it. It's very complex. It's a multi-dimensional thing. So now, when you have this concept, what we do with this concept, we will use it for making a prediction. Suppose I'm doing a house price prediction. So what these weightages actually mean? These weightages have a lot of importance. See, I have given this theta 3 10 value. So higher the theta, higher the weightage. It means that when you go to a certain area, and when you look at different house prices, you found a pattern that the number of floors actually affect the prices a lot, the most. The size of the house does not affect it a lot. The number of bedrooms does not affect it a lot. How old it is not going to affect it a lot, but it is actually affecting a lot when you look at the number of floors. It's a very positive, strong indicator. And why I have given -2 to this years? Because the older the house is, the less important it becomes. So it is negatively important for us. The more the year of a house, the lesser importance it will be given. So if I have to, let's say, determine the house price of a house which is 50 years old, so the price will go automatically very down, because you are multiplying -2 into 50, that will go down. Okay, so certain advantages are. Now, what you have to do to find the house price, any house price, you take a look at the size of the house. Let's say you just took one house for which you don't know the price. You have to predict the price. So you know the size of the house, you put it there. You know the number of bedrooms, you put it there. Number of floors, you put it there. Number of years. When you put it and when you apply that, you will get a particular house price. Let's say it is $150,000. How is that identified? You just put the input here, input here, input here, input here. We'll do the task and it will give you the output. Now, how is that actually working? Let me show it to you. What is this x1, x2, x3? You don't have to worry about that. Let me show you. So what actually happens is every column that you're seeing here, this price column, area column, bedroom column, these are what? X1, X2, X3, X4, X5, X6, X7, X7, like that. And you multiply that. What you're doing, you're multiplying any particular column with a theta. Theta 1, theta 2, theta 3, theta 4, like this. What is this x1, x2? X1, x2 is this. The price column is my x1, area column is my x2, like that. Now, if I have to find out the house price, let's suppose the price of this particular house. So this price column is not my input column, that is my output column. So what I will do here, I multiply this theta 1 into area, theta 2 into this. Suppose I'm talking about this house. I don't know what this is the price of the house. I don't know that. So I will say theta 1. Let's say this is 0.1. So I'll say 0.1 into 8960. Let's say 4 into 4. Let's say 3 into 4, which is the bathroom number. Let's say 2.8 into this number of stories in that building. So I'm just going to multiply different numbers. And when I add them up, you will get this price of the house. That is how the predictions are. Okay. So just you have to for now understand that the equation of multiple linear regression changes like this. And every column now is attached with the theta value. And you multiply that theta with that input to get the output. That is how prediction is done. Make sense? Okay. No, you don't know the base price. You don't know anything. You will start the linear regression. When the learning happens, it will create the best fit line. When it creates the best fit line, then you will get the value of theta 1, theta 2, theta 3. When you created that best fit line, that gives you the value of theta. That is what we have seen in the previous example, right? You don't know at the start. Line will be created. It tells you what is theta 0, theta 1, everything. Let me show that with the practical example. Let's see the code. You will understand. Yes, all the variables will decide best fit line. All the variables combined will decide the best fit line instead of just single value. That is what it is. Let's move forward to our code. Let's do some practical. So a lot of things will be clear to us. So this is going to be something interesting. You're going to understand the first practical use case of the machine learning. How do we apply the machine learning algorithm? We are going to understand that. So the example that I've taken to explain you with the marketing budget and the sales, I'm taking the same data set to make it more clear for you. Let's see. So before applying machine learning, what we do our data manipulation, we do our data cleaning, we do our data. Those things you perform, and then you reach to a point where you apply machine learning. First, you study the past data, visualize the past data, then you do predictive analysis. So now, same case here we are doing that I have the data, I'm looking at the data. And in this data, we are looking at the head and tail of the data. And after that, see at the tail, I'm looking some missing value. So when I look at this missing value, I am just going to drop it using this drop NA function. We have already seen that. Checking at the shape of my data frame, it's a very small data set. Just for the example purpose, I have taken. I'm taking a look at the describe. Looking at the describe to understand if my linear regression has outliers or not. Sorry, if my data set has outliers. Because if my data set has outliers, my linear regression line is affected a lot by that. I'll be explaining you that how. So when I take a look at it, my data looks fine. It is not having any outliers as such. The data is properly compact. Now this is the basic cases, and then I'm visualizing the data to help you understand where the actual trend is going. So if you look at it, the trend is going upward, and your best fit line that will be created will be something like this, the best fit line. Now, you all must have understood by now that there can be multiple lines created in this area, but there is only one best fit line. And how the best fit line is created, that is according to a certain theta value, theta naught and theta 1. Then from here, our main machine learning part starts. Till here, we have seen a lot of examples, so I don't need to explain that. Here, the main part starts. Now, when you talk about the machine learning algorithm, before applying machine learning algorithm, there is some preparation of data to be done. Okay, preparation of the data. That is very important. So preparation of the data, there are 4 basic preparations. First, X and Y. What is X and Y? Identifying your input columns and the output column. That is the first task. All the input columns which are there, you put it into a variable X, and the output column, always there is only one output column. The output column, you put it into Y. Input columns in X, output column in Y. That is the first thing. Second thing is you divide your data into 4 parts, which is called X train, X test, Y train, and Y test. Have I explained you the training and test data, right? What if I take a data set, I divide it into training and test set? No, okay. I'll explain that. So first your data and input and output column. Then you divide into 4 parts. What are these 4 parts? We'll understand properly. Yes, 80-20 ratio I told. Then there is a process called as standardization of the data. Okay. And after standardization of the data, you convert categorical text values to numerical. These are the 4 basic preparations of the data you have to do. Then you apply, in step number 5, you apply ML algorithm. Now, what is this X and Y? Let's see. All the input columns, basically you just select. How do you select input columns? With the indexing and slicing we have seen. After this X and Y, we divide our data into X train, X test, Y train, and Y test. Then we do the standardization of the data and this. For now, let us understand what is this X train, X and Y test. Let us understand this little more carefully. So I'm just explaining you this with the example, then I will show for the multiple columns also. So what happens when you apply machine learning is that first you train the machine learning algorithm and then you test its performance. Why testing is required? Because you don't know how better that machine learning algorithm has learned your patterns. You don't know about that. So you can't just train it simply and leave it for the real world. That is not going to happen. To understand this, you take an example that in a university, in a class, there are multiple students. Some are good learners, some are bad learners. So how does a teacher know which student has learned the concept properly and which student has not? So the student which has learned the concepts properly, they will score high in the examination, telling that they are ready for the real world. They have a proper knowledge to survive in the real world. If anyone has not learned it properly, they are not ready to work or do any task in the real world. Okay. Your data is actually divided into 2 parts. One is training data and one is testing data. So this training and testing data is a part of the same data set. Now, what you do in that case, you divide your data into 80-20 ratio. Okay. 80-20 ratio means Out of that 100% data, you take 80% as the training and 20% as the test. Or other example, you can take 75% as the training and 25% as 85% as the training, 15% as the test. How is that decided? Should I take 80-20, 75-25, 85-15? You will tell me the answer. But first, let us understand. This is the very common one, 80-20 ratio. So 80-20 ratio means that 20% of this data will be taken as the test and 80% for training. What is this? Suppose this is my 20%. It is not exactly from the end. Any 20% rows can be taken and that can be made as the test data. But I'm for simple explanation, I'm taking this. So when you take a look at this part, the first, these examples are training and these are testing data. Whenever you train any algorithm, okay, any algorithm, you show them the training data. Training data means that, okay, you have to learn the pattern that for this much marketing budget, we have got this much sales. For this much marketing budget, we have got this much sales. So the learning of the pattern that happens will be done on this training data only. Once it has learned the pattern, if company has spent this much in the past, they have got this much, it will create a line. Now what it will do? What we do with the testing data? We use the testing data for checking how better my model is. So in this case, first, your model is divided into training and test. Then it is divided further into 4 parts. So for now, let us now go to the bigger data. I think this is clear that we are dividing into training and testing. Let us see here. In this case, what will happen if you have multiple columns? Same thing happens there also in the multiple columns. What will happen? Let's suppose this is my 100% data. I will say that take 80% as the training and 20% as the test. So it is not that only the last 20% will be training taken for test. It is a sampling process. Like 20%, if I say, let's say 20% of this is 5 rows. So 5 rows can be anything. This can be my test data, this can be my test data, this can be my test data, this can be my test data. Any 5 rows. But just for the simplicity, to understand it, I'm saying that let's say this is my test data. Okay, let's say this is my test data. This is the 20% and the above, this is my training data and this is my training data. Your model will learn the patterns based on these training data and it will be tested on this. How testing is done? Now we are going to talk about that. So when you have taken the training and test data, okay, when we have taken this, then what happens? This price column is my output column. This price column is my output column. Okay, so let me take the other one. Just a minute. When we take a look at all of these examples, I have said that we take the, this is % data and we divide my 100% data into training and testing. So suppose this is my test part. Now, when I say this is my testing data part, it is further divided into 4 parts. First into training and test, 2 parts, then further divided into 4 parts, which is, this is called X train. This is called your X train. This is both training data. And this is called Y train. This is called Y train. And this is called X test. And this is called Y test. Don't get confused. I'm not taking 2 times Y train. It is the same data. I'm just taking middle part into the testing. So don't get confused about it. This whole thing, this part and this part is all one training data. Now, what do you think is the X train? It is the input training data. Okay, input training data. And what is this Y train? Y train is your output of the training data. Output of the training data, and it is the input of the training data. What is this X test? It is the input of the test data, and it is the output of the test data. How I'm saying that? Because X is your input. Whatever input columns are there, you save that into a variable called X. All the one output column is only there. So output column, you save that into variable Y. So when I say X train, it is input training data. And when I say Y train, it is output training data. X test, input test data, output test data. So we talked about that we train the model, then we check the performance. How performance is actually test? We are talking about that now. So understand this, it is a very interesting process. See it. So what we do, we give the input training and output training for the machine learning to learn the patterns. That for these input, this was the output. For these input, this was the output. Learn the patterns. Once it has learned the pattern, then what we do? After learning the patterns, it will create the machine learning algorithm. It will create the machine learning model. Once has created the machine learning model, what will you get? You will get that theta 1 into x1, theta 2 into x1, x2. The values of theta will be given to you. Then what you do? After the training has been done and you have to find out the performance of the model, you give this X test value to that learned pattern. It has learned, it has created the hypothesis function. Then you give this test input. And then what our model does, it will give me Y predicted. Okay, predicted output it will give me. And what you have to do with this predicted output, you have to do it like this. So you can see here, this is my Y test. I'm deleting for now. It will give me a predicted value. See, the actual value that it should have predicted for my first training input is 20.4. But my model, let's say, has predicted 19.3. For 18.2, it has predicted 15.7. For 19.9, it has predicted 19. You can say 8. For 23.1, it has predicted, let's say, 25.0. And for 17. It has predicted 11.2. So this is the input of the test data. I only show the input of the test data. I never show the output of the test data to my machine learning model. You will never show this, never. This is kept reserved. But what happens is you will show the input. And once you have shown the input, it has to predict the output according to that, according to these inputs, because it has learned the pattern on the training data. It has understood that according to this training, what is the output? According to this input, what is the output? Pattern has been learned. Now what it does, it takes this new inputs, which is the test input. It is going to predict the value which it thinks that for this house, this should be the price. For second house, this should be the price. It is predicting that according to whatever it has learned the patterns. Now what happens is you compare these values. Okay, you compare these values. The closer they are to actual, this numbers, these are my actual information, actual prices that it should have predicted. And these are my predicted prices. So the lesser the variance between them, the lesser the difference between them, the higher the accuracy of my model is. The far away they are, the more mistakes my model has done, the better it is giving me a worst accuracy. So what it should do, according to this data, it should predict something which is closer to that. Okay, make sense? That is the whole working of testing part. See, if you don't show the output, how will it work? If you don't show the output, how will it work? I'm telling that when, let's say this is the house price prediction. when you have to train your model, what will you related to these features of the house? This was the house prices of the past houses, which I'm using for the training purpose. So this X-train is the input of the house. That this many rooms are there, bathrooms are there, floors are there. These are input, and you're telling that for this house, for this house, for this house, these were the prices. Learn the pattern. Once it has learned the pattern, then you give the training testing data, and you never show this value, which is y test. You never show y test. According to this x test value, it will do y prediction, and then it compares the y test with y prediction. The closer they are, the better my model has done. The far away they are, the worse my model is. So this is the explanation. Let's move forward to the code. The input column, that input column is supposed to be as a data frame, and the output column which is there, it is supposed to be as a series, because output column only has one column always, and input column has multiple columns, input data. So X is my input data. Since there is only one input column, so I have to forcefully convert it to a data frame. Okay, in this case, when I'm talking about linear regression. So this marketing budget is my input column. Since it is just one input column, this is actually being treated as a series. So when it is a series, and then you have to convert it to a data frame. Once you have converted it to a data frame, then you can move forward. The output column is going to be just one column. So you don't have to convert that to a data frame. You see here, don't look at the shape. After taking this, what we have done, we have divided our data into 4 parts. X train, X test, Y train, Y test. If you take a look at this, you have to divide your data into 4 parts, and you don't have to do it manually. There is a function in one of the modules which is called train test split. Okay, there is a function train test split. So what you have to do into the train test split. So this is the case here. What is this sklearn.model selection? It is one of the module from which you are importing this function. Like pandas is there, right? So when you say import pandas, it means that you are asking the Python to give you every function from this pandas library. But if you say that from pandas, import one of the functions. What can be one of the functions? Let's say group by is one of the function. No, group by, sort values. Okay, sort values. So sort value was one of the function, right? That is the case. So this is the sklearn.model selection is a very big library from which you are actually just calling one function. The other ones are not required. That is the case. So why I have called this function? Because this function will actually help me split the data into 4 parts, so that I don't have to do the selection of the data. It will do it in the best manner possible. So you just use this function, and in this you have to give some parameters. Your input, your output, and the testing size. Test size means 0.15, means 15% you want as the test data, and rest 85% you want as the training data. Percent test, 85% training. Once you have done this, automatically your data will be divided into 4 parts: X train, X test, Y train, and Y test. You will do this process. And after doing this process, you can check the shape and everything, but let's move forward to the main part, which is training the model. So in our case, only these 2 preparations were required: input and output, and then now here comes the main part where you actually train the model. So don't write it down, just understand for now. There is again a module inside of which there is a linear regression function. This linear regression function has the code written to implement that linear regression, which we have understood theoretically. If you want to write this code yourself, it will be very difficult for you because it's a complex code. It's a very big code. So the code is written for you, and it is this function. which is present inside this module. So we simply import this function and we do our task. So how do we use this? Is linear regression is the name of the function. And using this linear regression, what we do, we apply it on a training data. So we say take linear regression dot fit. And what do we give here? We give X train and we give Y train. And that apply the linear regression algorithm to my training data. My input and output training data, apply linear regression to that. And then we save it into my one of the variables linreg. My training has been done. So once your training has been done, you actually just break it down into two processes. So instead of saying like this, linreg is equal to linear regression dot fit, what basically you will be doing is you just call your linear regression function and you save it into one of the variable and then use that variable linreg to do this fit. That is just a basic process which you're going to do. Why is this done? You will understand in the further process, because we will be writing something in this bracket you see, we'll be writing something that we will do in tomorrow's session. When I have given this linear regression dot fit X train and Y trace, this learning has been done. When you get a message like this, it means that your pattern has been learned by the linear regression. Once your pattern has been learned, then what you can do, you can take a look at the coefficients. Linear reg dot coefficient. What is this now? And then linreg dot intercept. What is this coefficient? Yes, beta naught and beta 1 or theta naught and theta 0. So this coefficient is your theta 0, theta 1. And the intercept is your theta 0. So now theta 0 plus theta 1x. When we started linear regression, we understood that our equation of the best fit line looks like this. But value to theta 0, so it is here, the theta 0 is 3.77 plus 0.05 into x. Theta 1 is this 0.05. That is the coefficient. And intercept is theta 0 always. And that here our equation is ready. How it has found it out? The gradient descent is working in the background. It has found the best fit line. Once it has found the best fit line, it has automatically found the theta naught and theta 1 for us. That's the case. So once it has found this out, it will be used for the prediction purpose, this equation. So when the training has been done, what is the next task we do? We take the trained model. This linreg is the trained model. Okay, you can see here in this variable, we have saved the linear regression algorithm. Then we use this variable to train it. Then what we do, linear regression dot predict. And after that predict, what we give X test. And once we do this X test, where do we save it? We save it into Y prediction. Okay, dot predict X test and we save it into Y prediction. Now what we have to compare? We have to compare this Y test and this Y prediction. Okay, we have to compare these two things, Y test and Y prediction. Now what we need to compare? How do we know that our model has learned properly? That is according to this. So these are my actual values and these are my predicted values. So for 15.5, my model has predicted 15.30. For 12.5, it has predicted 14.11, and for 12.5, it has predicted 14.11. So it is not very bad. It is not very good also. Let's see how better it has performed. So there is a measure, okay, that will help us find out the performance of the model. There's a very famous measure called as R2 score. So R2 score again is a function. And what you do, you give Y test and Y prediction to this R2 score, and it tells us how better your model has performed. R2 score, why it is giving so bad? Yes. So R2 score is the actual performance of the model. And the performance of the model is 83, 0.83. So R2 score is a value whose range is from 0 to 1. 0 to 1. So to get a better performance of the model, you should be getting a value closer to 1. If you're far away from 1, like 0 or 0 point something, then you are having a bad accuracy. It should be going near to 1 to get a good accuracy. So this is actually telling me the performance of the model, which my machine learning algorithm has given on this data. Just I have given you an overview of what is happening. Everyone will get a different number. This R2 score will be different for everyone. Why? Because as I told you, when you take input and that training and test, it is a sampling process. Okay, so I explained you that this is my data. So in this case, I have divided into 80 and 20 or 85 into 15. So for me, let's say the training data is this and this testing data for me. For any one of you, it might be this, this, and this. It will be different. So because it is taking different samples for training and testing, that is why you are getting different answers. But don't worry, you will be able to understand how to get the correct answer, same answer for everyone. We will talk about that.
I have one more announcement for you guys. For dedicated learners like yourself who want to make a difference in their career, for the first time, we at Intellipaat have decided to offer a straightforward 20% discount on our premium data science course, which is in collaboration with iHub IIT Roorkee. If you want to take control of your tech career and do something extraordinary, do visit this link in the description box given below and fill the inquiry form. Promptly, a team of course advisors will reach out to you to activate the offer. So don't miss out this opportunity.
So the theoretical part was over. We will talk more about this. But before talking about that, let me just discuss about advantages, disadvantages of the linear regression. Okay, so just focus on this now. Let's see what is this. So when we use linear regression, it has a few benefits, it has few disadvantages. And talking about the advantages of linear regression, it is preferred in many cases because it is very simple to implement and easier to interpret the output coefficient. Because whenever you have fitted a line and you want to make a prediction according to it, you just have to take the help of a line, map the x values, map the y values, and you will get your answer. So it is very simple to implement also, and it is very easier to that interpret what is the output of that. Now, the second case is that when you know the relationship between the input and output is linear, this algorithm is the best to use because it is less complex as compared to other algorithms. Okay, so when you know that the uh, relationship is linear, but if the relationship is not linear, then you are not going to use this linear regression there. Only when you can see the scatter plot is kind of going in the upward direction, downward direction in a proper linear fashion, then you're going to use this linear regression. I'll show you example. It works very well irrespective of data size. So it is created in such a way that if you give 10,000 data points or 1 million data points, it is going to perform well in both the cases. Okay, it is able to learn the pattern very easily. These are the few advantages. Having linear behavior, you understand by visualization. Okay, by visualization. Now, you'll get to see the example of that. Also, when we talk about the limitations, how do we understand the limitations of linear regression and what basically they are? So outliers can have a very huge effect on the regression line. That is one of the biggest, you can say, problem with linear regression, which it suffers from in most of the cases. Because if you remember in the previous sessions I have discussed with you, that outlier is one of the data point which is extreme value, and it is going to be present in most of your data sets. So suppose in this case, suppose your most of the data points are like this, and your this best fit line is created in such a way. Now, in let's say some days after, in that data set, some updation is done. And when someone updated the data, they have added a that you can say an outlier point. Okay. So most of the data points were like this. So according to this, your best fit line was created in such a way. Now suddenly an outlier has come, and outlier is some data point which will be like this. Okay, far away from all the data points, or it is like this. So what will happen in this case? Your linear regression line has to be close to these data points also. So it will try to shift itself in the direction of the outlier. That same thing happens with the normal distribution also, if you have seen that when you have skewed data. So in the case of skewed data, the mean is you can say pulled towards the outlier value. Okay, as if you remember, if I have these data points 7, 10, 13, 12, so there will be some mean. But as soon as you give a outlier point, let's say 200, so mean value starts to go towards this 200, not very close to, but it will start to be pulled towards the this outlier. So outlier has this main big property that it is going to pull a lot of things towards itself. So similarly here also, the outlier is going to pull this line towards themselves, and now line which should have been like that, it will start to be something like this, or maybe something like this, just because it has to accommodate these two outliers also. So in this case, what happens now, if your best fit line should have looked like this line number 1, but it is shifting towards the outlier and it is making line number 2 or line number 3, then it is going to give a bad result. Okay, because it is not the optimal one. The optimal one we can see is this, and it is being affected by the outlier. So every value which is going to be predicted by this line will have a biasness kind of thing. So it will not be correct. That is one very big problem with linear regression. So in most of the cases, yes, there are two cases. In some of the data sets, you can remove the outlier and then work with it. But see, when you're making the linear regression, there is not possibility of neglecting directly. Okay, it is created to work in such a way that it has to accommodate all the data points which are there. It does not know that it is outlier, it is not outlier, does not know about that. It just has to pass through all the data points which are there, minimizing the total error. So the second limitations of linear regression is that first is this first problem, that it is affected by outliers a lot. That problem is going to stop you from using linear regression in many cases. So then you will have to prefer using the advanced algorithms for regression, which is like decision tree regression, random forest regression in that case, because it is very easily affected by outliers and most of the data will have outliers. Now, linear regression assumes a relationship between dependent and independent variables, which is not the case in the real world. So what it assumes that the data that you're taking is having a linear relationship, which is not the case in most of the data in today's time. So the relationship will be like this in many cases. Okay, it might be completely circle kind of thing. It might be kind of this zigzag spiral kind of thing, and then it can be a little bit curved. These are the different type of relationships you're going to notice. Okay, so in such a case, your linear regression can't work, because if you see here, I have fitted my best fit line through this data. I fitted my best fit line through this data, and I fitted my best fit line through this data. But is this the best approach to take for this data? No, obviously not, because it is missing most of the data points by a huge margin. Here also same thing. So for such cases of data, what should be happening? There should be another algorithm to be used, which creates maybe kind of a circle to identify the data points. So it will be done by the advanced algorithms which are there. You will be studying about them. And also, if in this case also you notice that the data points are not linear, it is kind of curved, moving in a curved direction. But if you try using linear regression in this case, even if you make the best fit line, that will also be giving you a very bad uh, score of the prediction, because this is not the data where you should be applying the linear regression. So that is a very big limitation, that rarely in today's time the data is such that which is having linear relationship. It has a very complex relationship. The data points are very zigzag, sometimes spiral, sometimes zigzag curved. A lot of things are there. You will see about them. Now the third very big limitation is that it is prone to underfitting. So underfitting and overfitting are these two very big problems that you're going to see a lot of time. Underfitting and overfitting. Now, we will try to understand them in little bit more detail in the uh, further sessions. But for now, if you have to summarize the underfitting and overfitting, it is very simple. Underfitting is not being able to learn enough, not being able to learn the patterns properly because of being too simplistic. So in this case, what is underfitting? Underfitting is a problem faced by the simple algorithm. Okay, in machine learning, there are some simple algorithms and there are some complex algorithms. The simple algorithm is this linear regression. And after linear regression, I'm going to explain you logistic regression. Then there are some complex algorithms. So there is problem with simple this algorithms, that they suffer from underfitting a lot. Underfitting is just the inability of an algorithm to be able to learn the pattern because it is too simple. Too simple in what sense? Let's say that if I don't take a very complex example of a data, if I just take a data which is curved, as you can see here, this curved data. Now, in this case of curved data, if I'm trying to fit a linear line, it is always going to be a linear line. It can't curve itself. It will be a linear straight line. That is very simplistic approach to follow on a data. So because of this simplistic approach, there are some advantages, but there are disadvantages also, that it cannot learn the pattern properly. A curve that can learn the pattern properly should be this kind of quadratic kind of curve. Okay, that should be created for this data. But linear regression, being too simplistic, follows the problem or faces the problem of underfitting, not being able to learn properly. Now, very similar to that, the complex algorithms are there. They have a problem of overfitting, that they become too complex after training them again and again and again. They become too complex that they start to mug up the data instead of learning the patterns of the data. Okay, they start to remember the training data. I'll explain more about it, which are the algorithms which suffer from overfitting. But these are two very big problems which you have to take care, which you have to keep in mind before applying any algorithm. So how do you know underfitting is happening? When your score is very bad. Okay, when you check the R2 score, as I told you yesterday, the performance measure. So when you have low R2 score, that tells you that you have underfitting problem. It is not being able to learn the pattern properly. Okay, and if you have the very high R2 score, like 0.99 it is going, that much accuracy also can't be there. So that tells you about the overfitting problem. We'll see more about underfitting. So these are three limitations. When you have to go to interview, you just have to go through the advantages and limitations. The three basic: simple to implement, it assumes the linear relationship, and it works very well irrespective of data set. Small and big, both, it will work very well. Now the main thing, they might not ask the advantages and disadvantages because they are too simple, but they always ask if there is any question to be asked on linear regression very frequently. This is the assumption of linear regression. Because if you're not clear about the assumption of linear regression, you're going to make a lot of mistakes while implementing linear regression. So let us understand, these assumptions are very simple. See, you will be studying more about that in the further sessions when the professors explain you the building of the major projects kind of thing. You will be understanding how do you treat these assumptions, how do you work around them. But I'm trying to give you some basic idea as of now, fundamental idea. So first assumption of linear regression line is that the relationship between dependent and independent variable should be almost linear. That it assumes. And I have told you that it is the one of the biggest disadvantages of linear regression that it assumes the relation to be linear, where it is not linear. Okay, in most of the cases in today's time, it is not linear, but it assumes the relation to be linear. It does not even try to see that is the pattern different than linear, and then I should take another approach. I should modify something maybe, but it just assumes and fit a line through it, whatever data you give. Second is the mean of residuals should be zero or close to zero as much as possible. It is done to check whether our line is actually the line of best fit. What is this actually saying is you have to check the mean of residuals, and that mean should be zero or close to zero. This is done to check whether if you're making a best fit line is what? In the current scenario, in the current data, this is the best I can make out of all the lines. But that best fit line is actually the best in that case. We have to understand what I mean by this is, let's see, taking this example, suppose this example. Now I have taken a data in which I should not be fitting a line. Okay, I should not be fitting a best fit line. It's a very bad approach to do here. But I have fit a best fit line. This best fit line tells me that on this data, this is the best I can do. But even if I'm making my best fit line with the proper understanding, proper, you can say, care and everything, then also is this going to be helpful for me? No, it is not going to be helpful for me. So it is not that if you make a best fit line, it is just going to give you the best accuracy every time. The data should be as such where you can fit the best fit line. It is not that you just forcefully try to fit a best fit line everywhere in every type of data. It's not something to be done. Now, what is this assumption telling you? How do you know that best fit line is actually best fit line, or I should have created the best fit line in this case or not? How do you know that? So what you have to do is, we have understood that for every data point, okay, let me show you. What we will do is, I was talking about the error, right? Error is the difference between the line and this data point. Okay, this white one is my actual data point, this white one. And if I match it onto this line, this is my predicted data point. We have discussed about it, actual, predicted. So the distance between them is called error, because the actual was this white point, but my line has predicted on the line the red point. So this is the error. Now errors are also called residuals. Okay, residuals. It is just a second name given to error. Now what you have to do is, the error will also be a number. Now suppose if you're having a data set of 50,000 data points. In the 50,000 data points, what will you get? You will get 50,000 error values. For every data point, the actual minus predicted, you'll get 50,000 errors value also. So you have to take that 50,000 error values and you have to make a distribution plot of that. Okay, distribution plot of that. We have already seen sms.kd plot, give the data, it will make it. You'll see again the example of that when you are working on project. But for now, just understand the basic, that if you make the distribution plot of that data, the data which is all the errors, if you get the normal distribution when you're plotting the errors, it tells that in this case, we should be applying the best fit line. Okay, in this data, for which the errors are giving a normal distribution, here I should be applying my best fit line. But if you get the skewed distribution. Okay, I think everyone should be clear about this, right? This is not complicated. So when it gives a skewed distribution, automatically it will give you. You don't have to do anything. Just SNS.kd plot, simple thing. So if it gives you skewed, it tells you simply that you should not be applying a best fit line on this data. It's a very simple approach. So that is the second point, what it is. So it is little complicated to read, but in a very simple approach, I've explained you what is this. The third assumption it takes is that there should be homoscedasticity or equal variance in a regression model. This assumption means that the variance around the regression line is same for all the values of the predictor variable. So when you start moving in the further sessions, you will see many terminologies being used. So you don't have to just remember all the terminologies. Give it time. With time, you will be reading many articles, many projects, a lot of things. You'll remember the concepts. You'll remember the terminologies. Most of the terminologies we have seen already, and we will be talking about the rest of them further also. So in this case, the terminology I'm talking about is a predictor variable. Predictor variable, as it is mentioned here, the input columns which are there, they are mentioned here as the predictor variable. So what it says that in a very simple manner, if I have to explain this third assumption, is that if you plot the data points, what you plot the data, training data, which has been given to you, then you fit a line through that. So it says that it should have a property of this homoscedasticity. What is this property of homoscedasticity? That your scattered dots should be equally distant at all the places from your best fit line. It should not happen that somewhere it is very much close or stick to the regression line, and when you go far away, your points are getting far away from the regression line. It should not happen such a thing. So let me show you a few more examples of this. It is a little complicated name to remember. If you take a look at this, in the first one, the data points are all properly scattered around the best fit line. They are at the equal distance. But in this second case, you see here it is very far away, but here it is very close. Here it is again far away. So this is a property of heteroscedasticity, that your data is not actually properly unbiased. It is little bit biased at for few of the data points. It basically talks about some bias. Now, this is also the case of heteroscedasticity, that here it is very close to the regression line, and here it is very far away from regression. So this should not happen. This should not happen. Your data point should be actually at a proper equal variance, equal distance from the data point, from the best fit line. This is the property of homoscedasticity, equal distant. Simple thing. And the last property is even more important than the other three, is there should not be multicollinearity in regression model. Multicollinearity generally occurs when there are high correlations between two or more independent variables. This is one point which you should remember by heart. Out of all the assumptions, if you don't remember other ones, this fourth point should be something that you remember very properly, because you have to get rid of this problem from your data set when you're making the project. You will see again. Don't worry about that. But the problem of multicollinearity says this. Suppose you have to find out the house price, and you are making a model for that. So when you take the input data, what will happen is you will have multiple input columns: number of bedrooms, number of bathrooms, the floor, the locality, the distance from airport or railway station, those kind of things. A lot of input columns will be there. But if there is this kind of column, let's say I have given the width of that land area on which the house is built and length of land area. When you multiply width and length, you get the area of this plot. That is a basic mathematics. Width into length gives you area of a plot. Now, in this case, if you have taken a column which which has the area information. So now this becomes a case of multicollinearity because this area column is also telling me the same thing, which I can get using these two columns. If I multiply these two columns, you don't have to do it manually. But when the machine is learning the pattern, it is actually trying to do those kind of things. So if you can get the area information with this width and length column, why is there a requirement of area column? It is the same redundant information, same information twice. So multicollinearity says that the input columns should not be highly correlated with each other. See, there should be very high correlation between input and output. Very high correlation. The higher the correlation, the better our prediction will be. That the better our data is. So there should be very high correlation between input and output, but there should be no higher correlation between two input columns. That is one very important case of multicollinearity. If this is the case, if any column is very highly related, correlated with any other column, one of the column has to be dropped. So either you delete these two columns, width and length both, or you delete the area column. Because you see, this is not important at all, this information. What would you do of the same information twice? It's just the wastage of the resources. That is multicollinearity. And how do we find out multicollinearity? There is a, you will again see, but I'm telling you the name of that. There is a concept of variance inflation factor. Okay, this is just a function in sklearn. So you will be using this variance inflation factor, VIF, it is called. So VIF will tell you whether your data has multicollinearity or not, and which column is highly correlated to each other. This variance inflation factor tells you that. So variance inflation factor is basically some numbers like 0, 1, 2, 3, 4, 5, something like that. If any column has a value more than 5, you will get to know that that column is very highly correlated with other columns, and you have to delete that. You'll get to see everything. Because to understand this variance inflation factor, you have to understand about the other things also, which we have not covered for now. Isn't a correlation grid also? Yes, correlation grid is also you can do, but what happens is when you have a bigger data, which has too many input columns, then it becomes little difficult to find out the correlation. So this variation inflation factor is a very small thing. In one single line, you can easily get the answer, which columns are related highly or not. Okay, so if you are checking the correlation grid, that matrix between the other columns, all the columns, so you can take that also, but there you have to identify that from what point I am taking it as a higher correlation. More than 0.6 or more than 0.7, more than 0.65, more than 0.8, where are you actually drawing that line? So there is not a single answer that above 0.7 correlation, you should say that this is having multicollinearity. So this variance inflation factor will give you some number to the column. Let's say to width column, it has given number 2, number 3. For this area column, it has given, let's say 5.8. So this number is more than 5 for VIF, and VIF will tell you that you should be deleting this area column very easily, just in a single line. You don't have to do anything at all. This will be done. Again, I'm not going into depth because it will be covered properly. Don't worry about that. It will be covered properly when you're making the projects. But I think you should, you are very clear about the assumptions of linear regression, all the data points. You don't need to compare. You just need to use the VIF. That's a function. You use the VIF, you give your data set, it will give you the scores automatically. That this column is related to this column, this is related to this, or this column has higher VIF score, that will tell you. Okay, multicollinearity is something, just as a brief. If there are two input columns which are very highly correlated. Correlated means what? You have seen that correlation value goes from the -1 to +1. Correlation value. So if any correlation value is very closer to -1 or it is very closer to +1, it is highly correlated. So if there are two input columns, okay, two input columns, remember this. If there are any two input columns which are very highly correlated with each other, either negatively correlated or positively, if they're highly correlated, one of them has to be dropped. So we saw that these two columns tell me the same thing which area is telling me. So this area is multi-correlated with this. Okay. So then what you do, you delete the area column, or you can delete the width and length, both the columns. It depends upon you. Whatever you want, there is no single correct answer kind of thing. Now, the last thing for this case is the regression model evaluation metric. Yesterday, when I was showing you the practical, I just very briefly have shown you the R2 score. So R2 score is, yes, kind of duplicate, you can say, in a very layman term, that they are telling me the same information. Not exactly duplicate, but giving me the same information. That is what it means. So regression model evaluation matrix is something which you are going to use at the end of the model to check the performance of the model. So the metrics which I'm showing you here, this is different from for regression model, and the metrics will be different for classification model. You don't use the same metric for both of the cases. So let us see what it is. The regression model evaluation metrics are, you have mean squared error. Then we have root mean squared error. Then you have mean absolute error, R2, and adjusted R2. So what is this mean squared error? Mean squared error we have already seen. When we were creating the cost function, during that time, we got this mean squared error. Now, mean squared error is not something, okay, so this mean squared error is not something which tells me the performance of the model directly. Okay, what it is actually something which compares different lines to tell me this is the better one, this is not the better one. Okay, so it is used for comparing. Whichever line has a lower mean squared error, that is better. That is the thing. Now, very similar to that, there is RMSE. RMSE is nothing but when you take the root of mean squared error, you get the RMSE. This mean absolute error is nothing but you take the absolute of the mean error. You'll get to see that. But most of the time, what are you going to use is these two metrics, because they tell you exactly about the performance of the model. The other three are comparing with each other. That this model is better, this model is better. You compare their MSE, RMSE. So whichever has lesser value of these three is a better model. So suppose if you're taking a data set, and in that data set, one, you're applying linear regression, okay, linear regressor. And second, there is a decision tree regressor. We will understand about that also. Now, let's say this is a better model. How would you know about that? You can first compare the mean squared error for linear regression and mean squared error for that. Whichever has less value of MSE is a better model. So use them for comparing the models. But the R2 and adjusted R2 actually give you the score between 0 to 1. So what this R2 score gives you is, it should be, the more closer to 1 it is, the better your model is performing. Again, so what do you consider as better? It depends upon domain to domain, problem to problem. In some cases, what can happen is, when you get 0.78 also, that is very good for you. Some cases. But again, there are some critical cases where you have to get something of a very high score like this. So it is not that you are always going to look for a very high accuracy. When you're making the projects for the learning process during this course or anywhere, just for the learning process, you will be aiming to achieve a very higher R2 score. Okay, that will be your aim. But when you go to industry, nothing like this happens in most of the cases. Okay, you will think that you have to achieve this accuracy, this much score, but sometime you will have to just satisfy yourself with this much score also, or 0.7 score also. That depends upon problem to problem, the best you can do on a data that you will get to see once you experience those kind of things. Now, the R2 score is simply that score. That is, gives you a number between 0 to 1. The closer to 1, the better the model. What is this adjusted R2? This is very important to remember because a lot of people forget this. Adjusted R2 is nothing but it is the, you can say, modified version of R2 score, which gives us a lot of good information. What? Let's see. There's a small problem with R2 score. The small problem is that, let's say I have taken 20 input columns in the data. And for 20 input columns, I suppose get the R2 score of 0.83, telling me that my model has performed this much, and I get this much of score. But in this case, suppose I increase 3 more input columns. So what R2 score will do, it will always give a higher score if you're increasing the input column. Okay, so what will happen? That your score, which was 0.83, it might go from 0.83 to 87. You will also think the same thing, that it is a very obvious thing that if you're increasing the input data, you are giving more information to the model so it can learn better. That is what you will also think. But in some cases, what happens? The person who is adding the input column, they might not have taken the input columns by proper care. They just have randomly added, let's say, 3 input columns, which are not contributing properly to the prediction of the output. They just have added these 3 input columns. It is not helping me much. If I take 20 input, that is also giving the same kind of information. The 3 extra is not helping me much. So R2 score has that one simple problem, that the more input you take, the higher the accuracy will start to go, this score. But adjusted R2 is one of the approaches which does what? If you add any input column, any extra input column, so it will first take a look at it, that is it helping me to make a better prediction or not? Is it actually helping or not? Or is it just 3 extra input columns which are nonsense? So once it has identified that it is helping properly, actually it is helping, then it will increase the performance. Otherwise, even if you take 23 input, it will still be 0.83, no changes in the R2 score. Got it? That is the difference between R2 and adjusted R2. So the theoretical part is completed in this case of linear regression. Let me show you one more problem question to show you again, but I'm just going through another example to show you few more information. See why I'm not telling you to do for it now, because this is not a major project. This is just the basic implementation of the algorithm. How do you apply it? What do you need to take care of? So let me explain it to you. When you have to do practical, it is very simple. You will not face any problem. It's the smallest code that you will see. So let us understand about it properly. You should not have doubt into that, because when you move into the project making part, you should at least be clear about this fundamental. So as I told you yesterday, that before moving to the machine learning process, you have to actually do the data manipulation and visualization part. The NumPy, the pandas, and the matplotlib and the Seaborn. You're going to take these things and you have to do whatever modifications you think you can do. So here, what I'm doing is, you all must have this file. You can go through it. If you don't have the file, I'll share with you. But for now, just take a look. You'll be able to understand. Now I have this Boston data. It is the house prices for a Boston city. Now, when I go forward, I'm just checking the basic things about it. The outliers are there or not, those kind of things, basic things. See, if you take a look at this column, it has the presence of outlier at the end of the data, because 75 percentile is 3.6 and this maximum is 88.9. So we'll see how we can get around those kind of things later. But for now, let's move forward with this. Now, what I'm going to do is, first, I will show you a simple linear regression on the same data. Then I will show you multiple linear regression. Simple linear regression is nothing but when I consider only one input column and one output column. And multiple linear regression is 2 or more than 2 input columns and 1 output column. That is the case. So for that reason, what I'm doing is I'm slicing out the data in such a way that I'm just taking two columns from the data. One I will make my input, one I will make my output. So I think everyone can understand this easily. When I'm saying Boston.log, by saying this, I'm telling my data to select all the rows, but for the columns, only select LSTAT and MEDV column. These are two columns I'm trying to take out of that. Now, once I've taken those things, I'm just visualizing that. So when I'm visualizing, you should see that the plots. Earlier we have seen different plots which were going upward, like in this direction. But now this is going downward direction. Why this is going downward direction? Because between these two columns, LSTAT and MEDV, there is a negative relationship. If one increases, the second decreases. That is the case. So that is why the plots are going downward direction. Now, what will happen with this? If there is a negative relationship between input and output, what will happen? The slope, the beta 1 value, which was the slope, that will be negative. Okay. This beta 1 value which comes out in this case will be negative now. So beta value is not always positive. It is going to be negative also in few of the cases whenever the relationship is negative. Then once you visualize the data, what do you start? You start the preparation of the data. In preparation of the data, you have to take the input columns into X and output column into Y. And after that, once you have done it, you have to just apply your split. Try to understand it. You just apply your split. And split, what you do, you just take the train test split function to do your split. And after doing the split, if there is any further preparation of the data required, you will do that. But in this case, a further, you can say, preparation is not required. Just these two preparations are enough, that you take the input columns and the output columns properly, then you move forward. Further prep means there is two or more preparations of the data. One is standardization of the data. And then converting categorical text value to numerical. These are two further things are there which has to be done. But our data is not as such which is requiring these two values. But in the further sessions, I will show you what is standardization properly and how do you convert categorical to numerical. We will see that. Okay, don't worry. Since our data has not that problem, so I'm not doing it in this case. See, don't worry about that pd.data frame part. Let me just explain you. Wait for a few minutes, you'll understand. Now, after preparation of the data, once you have done those 4 steps, whatever is required, then you move to the training of the model. This training of the model is very critical to understand because the process is very simple. First, what you do, you go to the module. This is the module from which you are using this function, linear regression function. And after that, what you do, you take the linear regression function and you save it in a variable. So this is the very common approach you will see everyone take. That when they have taken one of the algorithm, this linear regression is actually a function which is having the implementation of that algorithm. So you take that function and you save that into one of the variable. It can be any variable, whatever name you want to have. And then you use this variable and then you say dot fit xtrain and ytrain. This is the code where you're applying the algorithm on the data. Dot fit means you're applying the algorithm on the data. This is what dot fit means. So once you apply that, what will happen? Your model will be created. Okay, the process of learning the pattern, the creation of the model, the creation of hypothesis function, everything is done at this point. This is dot fit. So once you get an output like this, it is telling you that the learning has been done since it's a very small data. So it has learned the pattern very fast. Once it has done it, the training has been done. If you want to check the intercept and everything, that you can do, but it is not required again. The intercept is this, the coefficient is this. So I was talking about that beta 1 value will be negative here, and you can see this. The beta 1 is what? Minus 0.977. This is the beta 1 here. And beta naught, which is the intercept, which is 35.013. So you automatically get the beta values. You don't have to do anything. Once you have understood the background concept, you will be able to get the idea what is happening, how you're getting these things. But again, remember that when you go to interview, first they will ask always the mathematical part of any algorithm, then they will move forward to the implementation of that. In many cases, you might not have to do the implementation at all. Just the projects that you have created during the learning process, they will ask one or two things from that project, that why you have implemented this, why not this. But mainly their focus on machine learning will be the mathematics behind this. So that is why I have explained you very properly the linear regression. If you understood the explanation, you will be better with it. You don't need to know anything more than that, whatever I have explained. The cost function part is also clear. The optimization of cost function also we have seen. Both the things are clear to you. Now, once you have fit this model, taken the algorithm dot fit xtrain and ytrain, then what you do the prediction. You take the same variable in which you have loaded your machine learning algorithm. Then you say linear dot predict and you give the x test value. I've explained that thing yesterday also. Once you give the x test value, it will do some predictions. What does it think? What it has learned, on the basis of that, it will make a prediction. And that you save into this variable ypred. This is a very common name. Everyone understands this, so you can use this one. So once I've done this, it is going to give me some predicted value, some predicted sum. Once it has predicted this, what it has to do? It has to compare with the y-test. So y-test is the actual data and y-predicted is what it has predicted on the line. So once you get this y-test and y-prediction, the last step is to take the R2 score and check the performance of the model. So if you observe here, when I have compared the y-test and y-predicted, means the actual and the predicted, you're getting a very bad score. What might be the reason of getting such a bad score in this case? The 0.44. What might be the reason? Outlier is not that big a problem in this case. It is not that difficult. It is a very simple problem. The first problem is you have not enough inputs. Okay. Less examples of the input data. Of the training data. What is these 2 points? What is this case? If you take a look here, in this data set, there is just 506 rows. Means only 506 examples are there on the basis of which my model has to learn. And also this complete 506 my model is not seeing because it is going to be divided between the training and test. So maybe around 450 examples our model is getting to learn the patterns, which is not enough at all. So first, we have very less data. Second, we have just one input column. So what can you predict with one input column? If I just tell you that predict the house price by seeing the number of floors, can you do that? Not possible for any. So it is actually lacking in two things, that you have very less examples of training, means lesser data, and you have very less input, just one input column is there. These are the two main problems because of which it is actually underfitting, not able to learn the patterns properly. This is one thing. Now let me show you that if you take more data, will it fix this problem? Will the performance increase? It is a very obvious thing, but I'm going to prove that to you now by taking multiple linear regression on the same data. So everything will be same, just one place I'll make a change where I'm taking input and output. So let me run through it. And in this case, you see what is the change I'm doing? Only one simple change. In the X, I'm taking now all the input columns from here to here. Total 13 input columns I'm taking. In the simple linear regression, what I've done, I've just taken this as my input and this as my output. MEDV is the price of the houses, and just one input, one output. Now I'm taking all the inputs, total 13 columns, and the MEDV column in this. So now take a look at it, what you will do to split the data into X and Y. You have taken the columns apart from MEDV, from CRIM to LSTAT, all of them you're taking into X. And for the Y, you're just taking the MEDV column. Very simple. Now you're splitting your data into 4 parts. What is this random state? I'll talk about it. But the test size, I'm taking 20%, 80% training. After that, what we do, we basically start our learning process. We have fit the model, and I'm just going to predict it. This is my predicted values. If you want to see, you can see not required. And then if I check the R2 score, now you see from 0.44, it has gone up to 0.77 just by taking more inputs. So here you prove a point that if you take more inputs, obviously the performance of the model should go up. But I've not taken into consideration the adjusted R2 score. We will see about that again later when I take the complex models and I compare those things with it. For now, just understand that this R2 score is telling us about the performance of the model. Okay, this just was to show you that what we do in simple, what we do in multiple. And in this case, what we observed that if I have taken more data, it has performed better. There is a grid search CV. There is a process using which we can get the same answer, same samples. I'll talk about it. So what I'm doing is I'm not actually going and explaining the depth of machine learning. I'm just making you ready for the further concepts which are going to come. You will study maths, you will study these in more detail, whatever I've left. But my task is just to give you the fundamental overview. Okay. So don't worry, I'm not skipping anything. I'm not just avoiding anything. That is what has been given to me, and everything else will be taken care of. Don't worry. Random state, I'll explain. What is this random state? We will talk about it. But this random state is just nothing but kind of a seed value. That if you have taken these samples for my test data, then every time take these same samples only. See what we are doing basically is this. Let me explain it to you quickly. If you remember yesterday, I told you that you divide your data into 80 and 20%. So it does not happen that the 20% will be these last few rows. That is not how 20% test data is selected. Because your model is not going to see the last or first values, does not do like that. See, suppose the 20% of these many rows, how many from 2 to 27, total 26. What will be 20% of this? See, maybe a 5. Yes. So suppose it is 5. So it has to take 5 rows as the sample. And in this case, what we do, it can take these 5 rows for the first time. When I run the same algorithm again, it might take these as the 5 rows. On my system only, I'm saying that in the second time when I run it, it might take these 5 rows to be the test data because it's a random sampling every time I run the algorithm. So if you want that every time it should take on your system these black fonts, the same rows every time in you're running the algorithm. So you use the random state. Random state is just a value. You can give it 10,000, you can give it 1, you can give it 100. It does not matter what you give it. It is just a seed value. Whatever seed value you have given, according to it will select some rows, and every time it will be constant. That is random state. So here we have completed our linear regression. If something is left, will be covered later. Now let us move forward to logistic regression. Optimization and everything we'll see. This is a very important question. Like, how do you decide that the ratio should be 80-20 or 85-15 or 75-25 or 70-30? There are many ratios which can be used, or sometimes 90-10 also. So out of these many examples, out of these many things that you can do, which one will you use? Will you use the 80-20 ratio, 85-15, 75-25, 70-30, 90-10? What is the basis of taking any ratio? Suppose I just talk about these two cases where I'm taking this and this case. So it is a very simple explanation. It is not difficult. See, what is your main task? Your main task is to train the data properly, train the algorithm properly. Testing is also a very important part, but main important part is that training of the model. So if you have a less data, okay, if you have less data, just let's say 10K rows are there in that data set. So for this less data, what will you take? What are the splits you are going to do out of these options? Yes. So you would prefer first the 90-10 the approach, 90-10. And after 90-10, you will follow the 85-15. But first you will go to 90-10 approach because the data is very less. See, in the machine learning field, this 10,000 rows is considered to be a very small data, very small data. So if your data is very small, you have to give more examples for the learning part. So in this case, you would be following 90-10 split or 85-15 split. These are the two of your best options that you will take. You might take 80-20, it is not going to hurt a lot, but prefer 90-10 or 85-15 in that. But again, in the second case, if you have a lot of data, where I'm talking about 1 million rows, okay, 1 million means 10 lakh rows in Indian terms. If you have a lot of data, then what steps you can take? In this case, you can be little bit, you can say lenient in this approach. And the approaches you can take here is 75-25 is also okay. 70-30 is also okay. And 80-20 is also okay. But these are the things you will take. That you have enough data for training also, and you have enough example for testing the model performance also. So it depends upon how less data, how more data you have, and on the basis of you decide. If you have anything in the middle of that, let's say 100K rows. So the common one which everyone uses is 80-20. If you are somewhere in the middle of you don't have less data, you have too much data also, you can go with this. Right? This is the answer. So what we are going to start now is we are going to see our first classification algorithm, which is called logistic regression. Now it is a classification algorithm. So why it does have a name of logistic regression? Why it has a name regression in this? So there is a reason for that. We will try to understand that reason. Because this is something people ask when you go to interviews, that why it has a name of regression, even though it is a classification model. So it should be logistic classification. Got it? And the other classification models which you see, there is a decision tree classification model. So it is called decision tree classifier. There is an SVM classifier. They are for classification part. SVM classifier. Then you have random forest classifier. So there it has a name of classifier. But logistic regression, even though it is a classification algorithm, it has a name regression in it. So we will understand it. Everything will be clear by the end of the session. Let's see. Yes, it tries to uses linear model for that. We will get to see how and why. Let's see. It actually uses a linear kind of line like linear regression. We will see how it actually uses it. Maybe we're having regression line in it in this algorithm. Correct. So now before understanding how this logistic regression works, it is a simple one to understand. It is actually a very complex algorithm, but it depends upon the explanation given by the people. Something will be more comfortable to you, some explanation will be very difficult to you. There are many types of explanation that you will see for logistic regression. So I'll try to give you the easiest one to help you understand what happens. Now, in the logistic regression, before saying that, we will try to understand why can't I use linear regression for classification? Why is there a need for creating any other algorithm if I have one algorithm already created? So whenever you create something new, you take a research paper, you do some modification on that. You take a code, you do some modification on that. So you always ask this question, why am I doing it? Can I not solve the next problem by taking the same code, or in this case, the same algorithm? Why we need to create another algorithm? So that was the question put first, and then they try to understand what is the problem if I use linear regression for classification. What problems might come? So there are two big problems because of which I can't use linear regression for classification. The first very big problem is that outliers can have a effect on the best fit line and thus the decision boundary. In the case of logistic regression, we'll try to create something called as decision boundary. Like in the linear regression, there was a best fit line, and here something called decision boundary will be important part. Now outliers affect the best fit line. So when outliers affect the best fit line, whatever prediction we get, that is also going to be affected. And the decision boundary that has to be created in the case of classification data, that will also be affected. I'll show you what is decision boundary. The second big problem is that in the classification, your output is these kind of things, yes or no, or 0 or 1. Yes and no and 0 and 1 is same thing. See, yes is encoded as 1 and no is encoded as 0. So when you will move forward, we will be seeing a concept where if your data has any column which has these text categorical data, yes, no, or fraud, not fraud, fraud, not fraud. If these type of things are there, we convert them into numbers. So yes, I can encode as 1, no, I can encode as 0. So 1 is the positive case, 0 is the negative class. That is the general idea about it. But we'll see the other approaches are also there, using which I can convert the text to numerical. Because any of the machine learning algorithm does not work with the textual columns. In your data set, you will have textual columns, the normal text columns or the categorical text columns. These things will be there. But before applying machine learning on that, you have to fix that. You have to convert into some numbers. That's a very important. So when the values predicted by linear regression is actually continuous, but the expected result in the classification task is discrete. So what linear regression does, it predicts the house prices like 27.4 million is the house price, suppose 1.2 million is the house price. There's a continuous value that can be that you can get as an output when you use linear regression line. But the answers which we require in classification is supposed to be 0 and 1 only. It should not be like 27.4, 1.2. That's a not required answer. That's a very different from what we want. But it was seen that some kind of modifications could be done on the regression model, and we can get the answer as 0 and 1. Okay, so we will now try to see how can I convert a continuous answer given by the linear regression and turn it to classification answer. So we are going to talk about the steps we can take to get around this second issue. So let's see. Whenever you plot the data of classification, it will not be like the scattered dots we have seen in the case of regression. It was a continuous value, so you got a scattered dots in those cases. Here the data will look something like this. So for simplicity of understanding this algorithm, what I'm taking is a patients of brain tumor. Now, if there are patients of brain tumor, what you will have a tumor size that from this much tumor size to this much tumor size, it is treatable. But if it goes beyond this much tumor size, it becomes very critical case. So we'll try to understand that if this is a data And as you can see here, the plot that has been created, you have some data points on this x-axis and some data points belonging to 1. Because there are only 2 type of data. These patients are, these all dots are patients. Patient number 1 has some tumor size and they don't have tumor. On the y-axis, you have yes and no. Is it serious or not serious? So yes is serious case, no is not serious case. This patient also does not have tumor. This patient also does not have tumor, not tumor. But when you go to a certain point, there is tumor size mentioned. Let us suppose that if I cross the tumor size of 150, below 150, if any patient has tumor size like 137, 142, 146, they don't have tumor or critical case of tumor. But when you go beyond that, it starts to become critical or serious. So that kind of thing is there. And this I have created is called a decision boundary. In the case of classification data, you create a boundary that on the left side of this boundary, this is one type of data. On the other side of boundary, there is another class of data. Class 0, class 1 means not serious, serious. What we are doing here is we take a data, and before making that decision boundary, how do we make that decision boundary? And what is the use of that? I'm going to explain you that. So suppose your data looks like this. Some tumor size is there, and it is showing that what is not serious and what is serious. Malignant is a serious tumor. So in this case, if I fit a straight line through it, if I try to fit a linear regression line through it, what it is going to actually do? It is going to make the best fit line. And how it is making the best fit line? It is trying to be close to all the data points. This data point also, this data point also, this also, this also. Trying to maintain the distance. Here also it is trying to maintain the distance from all the data points. Now you can say it should be a little more tilted, leave that. This is the best fit line it is trying to create. The problem with this best fit line is that it gives you continuous value. See, you have the one value here and your linear regression line is crossing that one value, which means that the output it will give may be more than 1. And here also you see it is crossing the line of 0. Means in some cases, the output it gives is the negative value. What I'm saying is, let's see. Suppose that for this data point, what will be the predicted value? Just above on the line. This will be the predicted value. Is it crossing 1? Is it more than 1? Yes, it is more than 1. Similarly, if there is a data point here, okay, what my linear regression line will tell me, you just map it on this line. It will tell you this is the value. What is this value? Less than 0, it is something negative. So the prediction for this dot is negative, which is lesser than 0. Prediction for this data point is more than 1 in a continuous manner. So if I just use a linear regression line to get the output, I should be just getting an answer as 0 or 1, but I am getting an answer more than 1, less than 0, that too in continuous format. So I won't be able to use it properly. How can I say that this person belongs to negative, this number? It does not make sense. I won't be able to interpret the results. So that is a problem. But the people who were studying this, they said that let's do something, let's add few things so that we can solve the problem of this. We should not be getting an answer more than 1, less than 0. Let's do something on this. So what they did to solve the problem using the linear line only is they created a 0.5 point here. In the middle, they said 0.5. And what we have to do with this 0.5 line is just make a linear regression line and then connect this. Start a line from here and connect the line just to this point so that it matches to this line, just touches the line. And once you have touched the line, what you will do is you will make a decision boundary straight according to it. So we don't randomly make a decision boundary. We have taken a 0.5 point. That is a common one. You can take 0.6 also, you can take 0.3 also. We'll understand about that. But the basic one given by the people, the people who created this, is you take a 0.5 point, touch it on the linear regression line, and make a decision boundary according to that. Now, what is the purpose of decision boundary? Let's suppose this is the value of 150. You take this 150 and you say that if any patient is having tumor size less than this 150, you say they are not having the tumor, brain tumor, or not critical in brain tumor. And beyond 150, you can say critical. So what we have done, we just took the linear regression line and not taking its output. We just took the 0.5, we touched this line, and I'm now just using this decision boundary point to say that don't look at the output of this. Don't take a look at the output which is given by the linear regression line. Just see the tumor. If the tumor size is less than this, say the patient has not critical case, and if it is beyond 150, say it is critical. So you solve the problem that below this class of 0, above this class of 1. That is one way they have thought they could solve this problem. Make sense? But there is a problem. The problem with this approach is the first limitations. I took a linear regression line. I have said that the linear regression line gives a continuous output, but we want the output to be 0 or 1. So we touched a line to the linear regression line. We made a decision boundary supporting through it. And then we said that take that as the boundary. Below the boundary, class of 0. Above the boundary, class of 1. So in linear regression, not using linear regression, we are creating that boundary. That is what it is. So once we have done that, it feels like it is going to be good for most of the cases, because once I have trained my model according to this, once I have found this 150 as the decision boundary, let's say a new patient comes tomorrow and I have to predict whether this patient is going to have tumor or not. So I checked the patient and I found out that the patient has tumor size of 167. Where this patient falls? On the right side of the decision boundary, and I will say that this patient has critical case of brain tumor. I can easily do this. And if I take any patient who has 135, it is less than 150, which is falling on the left side of it somewhere. So I can say that it is not having critical. So it feels like I have got a easier solution and I'm able to use linear regression line for the prediction of the classification data also. Feels like that. But again, the first problem which is there, the outliers can have an effect on the best fit line, thus the decision boundary. This is very interesting. Now let's understand this. Okay, so you were happy that I have found the solution and I'm able to use the linear regression for this also. Yes, so I'm now going to show you the outlier problem. So outlier problem is this. Let's suppose you take a data or you updated the training data and now it has an outlier. So when the outlier is there, then what will happen if in any data has outlier? So in this case, first you are making the linear regression line, then we use the linear regression line to make the prediction. Now you see, just because a patient came into the hospital, this patient actually came into the last stages of their brain tumor. He or she can't be saved because they have done too late to come to the hospital. And nothing could be done. They are not very highly critical. So just because of this one data point, you can see which is very higher tumor size value, my linear regression line, which should have been actually something like this, it is now shifting from here to here. Same property of linear regression, that it draws itself towards the outlier. So the problem is this. The important point becomes that if I take the same approach of 0.5 here, if I take that approach, what will happen is I was doing this and previously I made the decision boundary somewhere here. But now what is happening is I am going to use this 0.5 and the decision boundary now will be created somewhere here. So you see, now the decision boundary has shifted from here to here. And just by looking at the decision boundary, you can understand how dangerous this is. For this type of classification I'm doing, the patient into critical and not critical, you can see how dangerous it is. Because now, according to this line, these three dots you see is on the left side of this newer decision boundary. And you'll say that if a patient has earlier, let's say it was 150, now you're saying, let's say it is 175 decision boundary. So you're saying if any person has less than 175, they are not critical. But is this the actual case? Obviously not. The actual is 150 is the proper boundary, but because of shift in the regression line, the approach we have taken is going to be destroyed. That is the biggest problem by following this linear regression approach. Got it? Everyone can see that it is the problem. It is a very big problem. So what we do in this case, we understand that we can't use linear regression. You can say that if I'm having the balanced data, I can still apply the linear regression, but why take the pain of doing that? So they created logistic regression using this approach. So they found out that it is working well for the balanced data. Let us take that balanced approach and create the logistic regression. So logistic regression is having a name in regression because a regression line is used to create this logistic regression. So what is done and how you get the output in logistic, I'll explain it now. Because of outlier, not underfitting, because of this outlier. No questions, right? Till this point. So what we should do, instead of having a decision boundary like this, using the linear regression, if I use linear regression, I'll get a decision boundary, something like this. But if I use the logistic regression, I'll show you what is the formula of that. A decision boundary like this will be created. And the decision boundary in this case, in the case of logistic regression, will be a very popular, you can say, proper one, which is not going to be affected by the outliers present in the data. How that happens? So that happens according to this. Let's go through it. Let me explain. By the end, I'll summarize everything. You will have the complete idea. Let us see what happens. Can we change decision boundary dynamically? Not directly using the linear regression. We can't do that. But I'm going to show you something which will take care of that. Changing the decision boundary dynamically, it will take care of that. So what happens in that? To solve the problem of the linear regression or to solve the problem of logistic regression with linear regression, what we have to do is we will do this. So we understood that this was a quite good approach. When the data was balanced, I took this case and I just made a decision boundary. Felt good. So we will try to move forward on this point itself. And what happens in logistic regression, instead of using this linear line, which is affected by the outlier, what we do, we give this linear line to something called as sigmoid function. And once we have given this linear line to the sigmoid function, I'll show you the formula. What it does, it converts this linear line into something called as S-curve, which looks something like this. Don't have to go into mathematical detail, so don't worry about it. The sigmoid function is a very popular mathematical function, which is used in a lot of domains, in finance also, in geopolitical cases also. So it is a very very common or a very famous formula, you can say. You'll be studying about that in deep learning also, where you have to do object detection, those kind of things. What it does, that we saw a problem with the linear line, that this linear line is easily affected by the outlier. So let us give this linear line to sigmoid function, and it converts this into S-curve. So what will happen? The same linear line will now be converted into S-curve like this. Now, the property of S-curve is that it gives the answer in the terms of probability. I'll explain everything. It does not give you the answer like a direct answer about the performance of something. It gives in the term of probability. Now, it has a property that its value is always between 0 to 1. It will not cross 0. It will not cross 1. Means its value can't be less than 0. Its value can't be more than 1. But it is not 0 also. It is not 1 also. Something between 0 and 1. So when you make the S-curve, it never touches this line of 1. Okay, you see there is this line of 1. It never touches this. It will go maybe very close to that, but never touches it. Similar is the case of this. When you see the tail of it coming towards the 0 side, it will not touch the 0 line. It will be very close to it. How are we going to use it? Well, everything will be clear. But what I'm doing now is just taking a linear line, passing it through the sigmoid function, getting the output. So let us see how things will happen. So what I've done here is I took the, I'll do the recap properly, don't worry. I took the linear line, I passed it through the sigmoid function, and I got a curve like this. That is what we do in logistic regression. So the name of logistic regression, it should be clear to you because we are at the end using a linear line and converting it to S-curve, but we are using a linear regression line. So because of use of regression line in create, let me show it function or our logistic regression curve. It has a name of regression. Now, this is the basic use case. Why are we doing such a thing? We did this because we know that this sigmoid curve has a property that its value is between 0 to 1. It does not go less than 0. It does not go more than 1. Because of this one main property of the S-curve, we have used it. And S-curve has always this property since it is a mathematical formula, it never changes. Has this property. So we did this, we took a linear line converted to S-curve because we wanted the output to be between 0 and 1. Okay, we did not want that I should be getting a negative output or more than one output. I wanted something to be between 0 and 1. Now, actually, I want it to be either 0 or 1. The actual answer. Is this patient? No. This patient? Yes. Critical, not critical. I want actually 0 and 1. But what this sigmoid curve does, it gives me a value between 0 and 1, which we can map to 0 and 1. You'll understand. So if I want the output to be between 0 and 1, not crossing less than 0, more than 1, we use S-curve for this. And how do we get S-curve? We use sigmoid function for this. Now, sigmoid function has this formula. It is called 1 upon 1 plus e to the power of minus z. Now, this e is what? It is an exponential term. It is a mathematical term, exponential. Again, you don't have to worry about it. This is just the formula. The interesting thing about this formula is how do you actually convert a line to a S-curve using this formula? How that is done. So take a look at this. This is the interview question. This whole thing. Sorry. From here to here. So I've just represented that as g of z. This is a mathematical way of representing things. Again, no need to worry. So when I have taken this formula, I'm saying that the value of this formula is always between 0 to 1. I've written 0 greater less than 1. I'm not written is equal to, which means that the value given by this sigmoid function is never exactly 0, never exactly 1, but something between 0 and 1. Maybe it can be 0.001, but it is not exactly 0. That is the property. Now what we do? Now this z that you see here, this z is actually going to take the equation of a linear line. So this formula now becomes like this. 1 upon 1 plus e to the power of minus z. This formula is now going to take the form of 1 upon 1 plus e to the power of minus beta naught plus beta 1 into x. This is what it is. So this z that you see here we give the linear line. So we are taking a linear line passing through this equation and it gives me S curve. This is y. So in the formula of the sigmoid function, I've taken the equation of the linear line, regression line. And once this equation has the formula of linear line, it will take that linear line, convert to S curve. So this formula will take care of that. Let's move forward. Let's understand this. What are we going to do? So what are we going to do is we will talk about the first case that I said I will be able to convert my answer into 0 and 1. Let us see how. So why are we converting that linear line to S curve is because of this reason. Let's see. So suppose I have used this here and I have to convert it to S curve. How we are doing it is this. So see here, suppose there is a data point here. And this data point belongs to class 1 or class 0. I don't know about that. Okay, this data point. I should put it here or I should put it into the class of 0. I don't know that. So suppose that this is belonging to class 1. Suppose this is belonging to class 1. And what will be the predicted value of this according to my line? This will be the predicted value. And what it will be? Suppose it is something more than 1. Suppose it is 10.8. Got it? So this is what my linear line will do. It will give me a prediction value more than 1. According to this data point, it is telling me it is 10.8. Just I'm using the same property of linear regression, nothing else. So I get a 10.8. What I do about this 10.8? So I do this. Let me go ahead. And using this equation, what I will do, I will write the formula again, 1 upon 1 plus e to the power of minus 10.8. What it will give me? It will give me some number. Let's suppose it gives me a number like 0.2. Suppose, not going into exact. There's a calculator using which you can calculate the value of e to the power of minus 10 to the power 8. See why I'm telling it to be this 0.2? Because when you have this e to the power of minus 10.8, it will become a small negative number, and 1 minus negative number, it will be something. And if you divide 1 by that small number, sorry, if you divide this by a bigger number, it actually will give you a bigger number. I'll show that calculation. So just think of it like some division is happening. It is going to be giving you some number and you're adding with this. Now, once you get that, what will happen? 1 upon some bigger number, you will get 0.2. What do we do with this 0.2? What do we do with this 0.2? Before understanding this 0.2, how has that 10.8 come? I think you understand. I took one of the data points, I mapped it on the linear regression line, I got a linear output. That is what linear regression does. I gave the output of the linear regression line into this formula, sigmoid function, and it gave me a value between 0 to 1. It can be any value, but it has given me this. Now, what do we know about the concept of decision boundary? We have understood that we take a decision boundary of 0.5 in many cases. That's a general one. You can change the decision boundary also. So suppose following the common approach, I have taken the boundary to be 0.5. Now, if I get the 0.2 value, where it is going to be in the case of left side or right side. Actually, I've taken a value this. Sorry. It should be actually something around 0.8. Sorry. Okay, it should be actually 0.8 because it is on the higher side of that. So where it is 0.8, 0.8 is actually falling on the right side of this 0.5. Means if the decision boundary was this according to 0.5 we have created, it is on the right side of it. So once it is on the right side of it, this 0.8, I can easily tell that that patient is having critical case of brain tumor. Very similar to that, if I take a patient which is this. Okay, suppose I take a patient here. Wait again, I'll explain it again. I'll summarize it again. Let's take a patient is here. For this patient, what my linear regression line will tell me, it will actually give me a negative number, something. So let's say it has given me a prediction of minus 5.8. Okay, this is the output given by my linear regression. What I will do with this output, I will actually go to my equation. And now I will say now the sigmoid function will, for this data point, it will tell me minus of 5.8. So it will actually become 1 upon 1 plus e to the power of plus 5.8. And what will be the value of it? According to it, whatever output you're going to get, maybe it is 0.2 or 0.1, something like that. Now, where is it falling? It is falling on the left side of this boundary. So I can very easily say that this person is not having critical case of brain tumor. Okay, this person is not having critical case of brain tumor. See, where did I start? I started, can I use linear regression for classification? I started here. Before starting to use this, we saw that there is two problems with linear regression. That outliers affect the best fit line, and the values predicted by linear regression will be continuous, but our expected result should be discrete, 0, 1, 0, 1, yes, no kind of thing. So we started here to get a turnaround to this second point. Can I just do something where I am able to do or turn around the second point? I can do something even if I'm getting continuous output. So in this case, we said that let's make a 0.5 point and touch it on the linear regression line, make a decision boundary, simple. Beyond decision boundary, my output is this. On the left side, my output is this. We solved that problem. But the problem faced was another one, is when your data has outlier. Let's suppose it does not have extreme outlier. It has outlier here also. So if your data has not very big outlier also, then also if your line was supposed to be this, it will still be a little bit tilted to this. If your line is tilting or shifting towards right side, your decision boundary will also be shifting towards right side. So the problem we observed here that for this case, if our linear line should have been this, my linear line is actually shifting to this. Because of this shift, what is going to happen? The decision boundary, which should have been actually here, is now coming somewhere here. That's a very big problem. I can't let this happen. This is a very dangerous issue. That if my that decision boundary is shifting, my answer will be incorrect. So this is the point that was causing a problem. Now what we did, we said that okay, for a balanced data it is working very fine. So why not take the advantage of this balanced approach? And what we did is we actually created an S-curve. We took this line, we created an S-curve from the balanced data. And now we are using that S-curve for our prediction purpose. Let's see. So the mathematical explanation I've given, let me show you the intuitive explanation also. The visual explanation of the same thing. I have created an S-curve according to my linear line. So what will happen now is, earlier you were touching the line, now you are going to touch the S-curve middle point. With 0.5, wherever it touch, you will touch the curve now. So according to the curve, it is actually just making here. The decision boundary is created. Decision boundary is created. Now what you do with this is forget about the linear line. The S-curve is not going to work like a linear line. What it will tell you now? The S-curve tells about probability. Whatever output it gives us, if it is 0.2, if it is 0.8, this is something called as probability. Probability of what? Probability of this thing is that suppose I have this data point. Suppose I take a data point here. Now where I will map it, not on the linear line. Forget the linear line. I just use it to create my S curve. I got my S curve. So now I will touch this on my S curve line. Once I touched on this S curve line, what is on this side? On this side, now you have this probability. Okay, probability. Suppose this probability is 0.15. There is a value here 0, 0.10, 0.15, 0.20, like that. From 0 to 1, there are multiple values. When I took this data point, which is suppose the tumor size of 132. According to this tumor size, if you take a look at it visually, you'll see that when I touch it on the S curve, it is coming here. Means it is giving me some number 0.5, which is actually some probability. Probability of what? Can you tell me? If I've, according to this data point, if I've got a probability of 0.5, I took a patient of 132, I got a probability of 0.15. What do you think it is? Probability of what exactly? So it is, this probability is actually telling me that yes, of being non-malignant. This 0.5 is not malignant, actually not. You say that the probability, let me write it down, of this person falling in class of 1 or having critical tumor is 0.15. That is the proper statement to be read. The probability of this person having critical tumor is 0.5. So you can see this person has a very less probability of having a critical tumor. That is what we represent in this case. Now, once I've trained my data, then I will be creating the S curve and I'm checking for a further future data, making a prediction. Suppose I take this data point. Okay, I take this data point and I don't know I should put it into class of 0 or class of 1. I have to classify this data point. I've got a patient who has got 163 of the tumor size or something like that. So what I will do, I will just map this on the S curve. What it will do, it will also give me some probability. Let's say this probability of 0.8. So now the probability of this person having critical tumor is 0.8. Means 80% is the probability of this person. See, we are not saying that this person is going to have the tumor. We are giving a probabilistic approach. So now, once I have got this 0.15, once I have got this 0.8, then what I do, then this 0.5 comes into picture. That if any patient has more than 50% probability of having a critical tumor, we mark them as critical case. If any person has less than 50% probability or less than 0.5 probability of having a critical tumor, we mark them as not critical. With this, everything should be clear that what we do in logistic regression, you have seen visually also, and you have seen with that case of sigmoid function also. So if I have to show you the sigmoid function approach, what we have done is, if I took a patient of 163 here. So for 163, I would have got a regression value of 10.8 for this person if I use the regression approach. So I should have got a regression value of this. Then I give this regression value into this model and it gives me a value. When I take this value, what is this? This is now the probability.
I have one more announcement for you guys. For dedicated learners like yourself who want to make a difference in their career, for the first time, we at Intellipaat have decided to offer a straightforward 20% discount on our premium data science course, which is in collaboration with iHub IIT Roorkee. If you want to take control of your tech career and do something extraordinary, Do visit this link in the description box given below and fill the inquiry form. Promptly, a team of course advisors will reach out to you to activate the offer. So don't miss out this opportunity.
When people have created logistic regression, they have tried it also. So that can be take the advantage of linear regression for the classification purpose also. So when they tried it, they actually found these two problems, which was outliers affect the best fit line, and thus the decision boundary and the continuous value, right? Continuous output, correct. These are the two problems, and you should remember that these are the basic problem because of which we were not able to use linear regression. But what we said, we started with the second point that if my linear regression line is giving continuous output, let us see, can I map it to one or zeros by doing something? So in this case, we went to an example, and in this example, as you can see, we have the tumor size. We have on the left side on y-axis, we have either it is critical or not critical. So yes is all the example of critical cases, and no is all the example of non-critical patient. So in this case, what we said that the linear regression, as you can see, it is crossing the one boundary and it is crossing the zero boundary. So that should not happen. We expect the output to be 0 and 1, but the output we get with linear regression is more than 1, less than 0. That's a small problem. So we said that take a 0.5 line, make a decision boundary, and once you have decision boundary, you say that right side of it is the patient for critical case and left side is not critical case. That was a very simple solution that we found to it. But the problem happened here. Okay, so we found a turnaround. We found a way to use linear regression even after having the second problem. But then came the first problem and it destroyed everything. So when we found a solution to the second problem, it felt like it is a very good approach. We can use this for a lot of examples, lot of use cases, we can use it. But when the outliers came, it told us that uh, it just simply destroys our use cases. That if I have taken 0.5, then decision boundary is here. But actually, the decision boundary should have been somewhere here. Okay, and now it was here. So that was one big problem that happened. And because of this one big problem, it is actually giving me wrong assumptions, correct? Now this new line will tell that after this number, after this point, actually the cases are critical. But what is correct? That after this point only, the cases are critical, the patients are critical. So just because of outliers present, my line shifted, and because my line shifted, my decision boundary, as I told, this is a decision boundary. So my decision boundary also shifted. So what we do in that case, we were trying to understand that. So we said that, okay, these two problems are there, and to find a solution to these problems, there is a concept of sigmoid function. So sigmoid function says that take any data. If that data has outlier, no outlier, take it. But we will start with a balanced data to understand what we do. So we said that let's create a S curve. Now I told that S curve is actually a type of curve which is going to be like this. So first you create a line. Okay, you create a line for yourself. You give it through the sigmoid function, and then you get an S curve. That is what we saw. Now this S curve that is created, that can also be of different type. One can be this, one can be this, and one can be this very flat. There can be different S curve. And what we have to do, we have to optimize this in such a way that we get the best S curve. Out of multiple types of S curve which is possible here, we need to get the best type of S curve. That is also very critical in this case. Like we were looking for best fit line. Is this my best fit line, or is this my best fit line, or is this my best fit line? Very similar to that, there will be different type of S curve. And we have to find that out, that which is the best S curve. I will show you an example of that, what we actually do. Yes, just like the best fit line. So now, you need to understand one thing, that the creation of S curve that you're making is dependent upon this line. First, we are making a linear line, the regression line. Then we are converting that to S curve. So that is actually dependent upon my line. If line changes, the S curve changes. If the line is this one, suppose the S curve is actually created like this. If my line changes from here to here, then S curve might be more flatter kind of this. Okay, changes. So if the S curve changes, then the output will also be affected, the probabilities that we were getting. So we'll understand what we do in that case. But here we took the example of a line and then we did what? We converted this line into S curve. And I told that this S curve is such that it is created in the area of like this, zeros and one. And the very famous property of this S curve is that the first property, its output is between 0 and 1. Output between 0 and 1. That is the first characteristic of this S curve. And second characteristic of this S curve is that not affected by outliers. Okay, when not affected by outliers, once you have created an S curve, after that, if you bring in any outliers in the data, then my S curve is not going to change. Okay, but what we have seen with the best fit line, once we have created a best fit line and we bring in outlier, so best fit line shifts towards that. My best fit line changes. But there is a very good characteristic of this S curve that once you have created the S curve, then it is not affected by the outlier. But before creating the S curve, if outliers are there, then it is going to be affected and we have to fix that. That one problem will be there. No, I'll tell you, it is affected by the outliers before the creation. After creating that S curve, if outliers come into the data, then it will not be affected. That is why we took this S curve in this case. Otherwise, what we would have done, otherwise we would have just taken the linear regression if it was affected after creation also. Because linear regression line is what? It is affected after creating the best fit line also. So that problem will not happen with the S curve. Before will be affected, not after. Let's see. So in this case, what we observe is this. It has very two important properties. The output that we get is between 0 and 1 and it is not affected by the outlier. Then, what is the use case of this? We have created, suppose, the S curve for this data. How do we use it? So I told that you take the same way, the 0.5 measure. You touch it on the S curve now. Forget that this line is there. We have taken that line and we have now created S curve according to that. Now we touch from 0.5 to this S curve and then we create a similar kind of decision boundary. Now our answer which will be there, it will be in the terms of probability. So let's see what it is actually. Suppose this is my S curve. Now what we saw is this, in this case, here we have taken, suppose, the 0.5 line and this is my decision boundary. What we do with it? So earlier that what we were doing, if I use a linear regression line, then what we would do with this linear regression line, suppose I have a data point here and I have to classify this data point, okay, where it belongs. So I will have to map it, don't see that line for now. What is the purpose of the line? What we did with line actually is, let's say I have taken a new data point. Okay, I have taken a new data point. What is the value of it? It is 1, it is 0. So we actually mapped it on the line. So it gave me this output, but actually it should be output of 1 in this case, but it gave me output more than 1. So we converted that to 1 from that output, which was, you can say, continuous. Let's say the output was 10.8. So 10.8 is not something meaningful to me. So what we did in that case, We took the 10.8 and we passed it through the sigmoid function, and we were able to get uh, the class of 1, that it belongs to class of 1 with some probability. Now, what is this 10.8? 10.8 is the value that you get with a linear line. So the value that you get with the linear line, you pass it through the sigmoid function, which is a curve, and that curve gives you the output of 1 or 0 with some probability. So we'll see that example also. But for now, once we have created the S curve, then what we do? Suppose a new point comes up, and I have to find out what will be this S curve. So in this case, suppose this curve is here. So I have to map it on the S curve now. After creating that S curve, how do we do the prediction with this? I'm talking about that. So in this case now, what we will do is we will just map this point on the y-axis. So y-axis is nothing but the probabilities. It is nothing but the probabilities. So here, if you see, it is just very close to 1. So the probability might be 0.9 or 0.85, something like that. Now, what is this 0.85 telling you? This 0.85 is the probability related to this data point, which has come into the future, a new patient. So suppose this patient is what? This patient is now having the tumor size of, let's suppose, 175. And 150 was our decision boundary. So I told you that if something is beyond the decision boundary, we can easily say that that patient is having a critical case of tumor. But our algorithm does not see this thing visually. Our algorithm has to take help of some mathematics so that it can decide where it belongs. It belongs to critical case or non-critical case. Okay, so understand this. The visual part that you're saying, it is for your understanding of what is happening in the background. But machine does not see things visually. Machine always takes help of some mathematical uh, calculations to do these kind of tasks. So machine does what? Machine takes a data point. It finds the probability of it. How does it find the probability? So suppose the data point started from here. Okay, this data point started from here. We first found out the number. What number? The linear regression line, what output it will give. So it will say, let's say it gives us 27.2. Okay, mapping it on the line, it gives us some continuous output, let's say 27.2. But that 27.2 does not help us. So what we did, we give this to our sigmoid function, which is 1 plus e to the power of minus 27.2. That was the formula. Let me show you. 1 plus 1 upon 1 plus e to the power of minus z. That is the thing here. Now, so what I was saying is I have the 175. So I took the output which was given by the linear line. So I took the output given by the linear line because I don't understand this. And then what I did, I actually applied this formula. So what it will do, it will give me some probability which will be closer to 1. Okay, which will be closer to 1. So let's say it has given me a probability of 0.9. So this 0.9 is not actually 1 for now. We wanted output to be either 0 or 1, but this is not 0 also, this is not 1 also. It is between 0 and 1. So we started with a data point, we get an output with the linear regression line, but this output is not helpful for me. What we did, we passed this output through the sigmoid function, and it converts that between a value of 0 to 1. Then we take a value. Now this 0.9 is what? This 0.9 is the probability attached with this data point. What probability? So this patient has a 90% probability of having a critical case of tumor, this patient. If this value was 0.8, then we would have said that this patient has 80% probability of having a critical case of tumor. So the number that you get is the probability. Now, what we do with this number, still it is not clear that it is 0 or 1. Should this fall into the class of critical patient, or should it fall into the class of non-critical patient? Still, it is not 100% clear to me. So then the last point comes up, which is the 0.5 I have taken here, this 0.5, the decision boundary part. I first explained you through visually. Now I'm showing you through mathematics how things happen. So in mathematics, you take a data point, you take the linear line, you convert it, you get the number, then you bring in your decision boundary point. Now beyond decision boundary point, if you get on the right side some number, that is a critical patient, on the left side, non-critical patient. So where does this number fall? This number falls on the right side, 0.9. So we will say that this person belongs to class of 1. Means, yes, this person has a, you can say, malignant tumor, critical tumor. So what we have done now, we have just taken a condition of a patient, not knowing whether that patient is going to have tumor or not in the future. We just took the conditions. We just did a test, we got some results, and then we passed it to our machine learning algorithm, which has created this S-curve. And using that machine learning algorithm, we are getting an output. And that output is now classified into class of 1, or you can say class of ES. And this, any person here on the left side of the decision boundary will have a value less than 0.5. Now you will say that if I get a value of 0.5, then what? Should it fall into the class 0, class 1? That is upon you to decide. There's no correct answer, there is no wrong answer. If you want that 0.5 also you want to put into the non-critical, you can put it. If you want to put that into critical, you can put that. This is the easiest explanation you are going to get. That is the thing. So always you need to remember that what we need to remember is this. The interpretation of the value that you get in logistic regression is in the terms of probability. That should be clear to you. So what we have seen here, that if my linear line gives me a value like this continuous value, then we convert it, it gives me some probability. So always that is a probability. It is not the final output, that is a probability. And you take that probability and then you interpret that. So suppose I have got the value. So the output as the probability that the class of the data is 0 or 1. That probability is the main thing to remember here. Okay, so that is the main point. It is common and force that we will pass to the y signal. Now, I was talking about that how do we get that best S-curve? Because if you see here, we have understood the working of that. First, you have created the S-curve by converting linear line to S-curve. System understand, system, you give that decision boundary point. Whether it is going to be 0.5, 0.6, 0.4, you have to decide that. But in most of the cases, a very popular decision boundary is taken with the 0.5. It will do that. The code has been written. I explained you visually what happens. So by default, we take the value as the 0.5 and it touches the line. That way it understands. Don't have to go into that technical because it will be too much mathematical. But again, you don't always take 0.5. You can take lesser also, like 0.4, you can put the decision boundary, or you can go higher also, 0.6, 0.7 also. It depends upon how critical problem you are trying to solve. That way you increase it. So critical problem means, suppose you are trying to have cancer patients, you're trying to classify a cancer patient, whether a patient is critical, not critical. So you want that, I don't want 50% probability or higher than 50% probability. I actually want higher than 65% probability. So you put the data point as 0.65. Now, whatever probability comes up, that should be at least 0.65 or more than that for that patient to be classified as cancer patient. Before that, you will say that non-cancerous, or you can just, in some cases, go below 0.45, 0.4. Depends upon criticality of the case, what type of problem you are trying to solve. But if it is a very normal kind of business case study, then a 0.5 works well in most of the cases. Okay, so you will get to see this when you're making the project. You will be changing it some places. Okay, the last thing to understand is, suppose if this is my data point, let's suppose, and this data point has no outlier, then what we do, our curve is created like this. Make sense? Curve is like this. Now suppose my data point is like this. My data point has some outlier, the data set that I've taken. And now for this one, I have to create a S curve. Now, if you look at this, you will say that obviously the S curve that is going to be created with this line is not going to be correct. Because if my linear line is not correct, if it is shifted towards the outlier, so the S curve that this line is going to give obviously will have that fault. That will also not be correct. So how do we make sure that our S curve becomes better over time and it is not affected by the outlier? So we are trying to understand that. Okay. So what I said is, before showing anything, let me show you this. Just the formula. See, the formula works like this. You have beta naught plus beta 1x. I'm not taking multiple linear regression for now, just this simple case. So first, what we take, this equation. This equation is the equation of what? A linear line. We take this equation, we pass it through the sigmoid function. And then what happens? Sigmoid function is this, 1 plus e to the power of minus z. So z here is nothing but this, the equation of the line. So minus of beta naught plus beta 1x. So you see that if any S curve will be created, the S curve is created according to this formula. And now if you see, this formula is highly affected by the beta naught and beta 1, which means that the slope of the line or the way the line is created affect the S curve. Why does it affect the S curve? Because our formula itself, the S curve formula itself has the equation of the line. So it means that this thing here says that if we change beta naught and beta 1, S curve also changes. S curve also changes. So what we need to do, we need to first find out optimal value of beta naught and beta 1 because of this probability, because of this concept that our beta naught and beta 1 decide how the S curve will be created. So to get a very balanced, very popular S curve, which is not affected by the outliers and it gives the best result, we need to take care of beta naught and beta 1. We have to find that. So in this case, where do we start? It's a very simple explanation. Understand what I'm trying to say. Okay, right. So here, if I have this line and if I take this line and convert it to S curve, it will be a wrong case of S curve. Maybe like this. But actually the S curve should not be like this. Maybe it should be like this. But my S curve is more flatter, you can see. I don't want this pink one to be my S curve. It should be actually this black one. So how do we convert it from this S curve to this S curve? How do we go to that point? Changing the value of beta naught and beta 1 values. That is the only approach. So one very easy solution that I can take is that I remove the outlier first. Okay. Before going to the machine learning part, I take my data set, I do the data cleaning, and that in that data cleaning, I remove the outliers completely. Then it will be automatically balanced, no problem about it. But in some cases, suppose you can't remove the outlier. It is a very important part of the data, which is giving you very important information and you can't delete that. So in those cases, what happens is we are going to talk about that. So how do we get the S curve is according to some maximization. So let us quickly draw that to understand. Let me show you one more example. Okay, suppose I take an example here, which is like this. And in this, I'm going to take an example of the blood sugar level. We have blood sugar level. And on this side, what we have? The probability of diabetes. That is my y-axis value, and x-axis value, I'm taking a blood sugar level. Now, in this case, let's say I have some data points, okay? And for that data points, first, let me take the 0 point here, 0.00, and here I have, let's say, 0.25. I have 0.50, 0.75, 1.0. These are the probabilities. Now, if these are the probabilities, let's say we have 150 blood sugar level, then we have 200 blood sugar level, then we have 250, then we have 300, these kind of cases. To understand it better. Now, suppose I have a line here, and there are some data points which are, let's say, critical. Suppose from this point. And here I have a line. And suppose these are the data points. Here, let's say here. Now, what we do with this, we are going to create an S-curve to solve this problem. Let's say our S-curve is something like this. Not exactly very correct, but see, but you will be able to understand what this S-curve is actually doing. So in this S-curve, what we do is we try to do some likelihood maximization kind of thing. There's a concept of that. Not good at drawing, so you can adjust for now. See what we are getting here. Now we are getting here that there will be some probabilities. If I talk about these data points, if I talk about, they will have some probability, they will have some probability, they will have some probability, they will have some probability. And if I talk about these data points, they will also have some probability, sorry. Okay, so now if I'm talking about these data points, how have they come to the class of 1? They have come to the class of 1 because we had some probability like this. Okay, we had some probability like this. So let me explain it to you in a very little more simple manner. Just 1 minute. So suppose I have the probabilities of say 0.1 here. It is also 0.1, 0.15. It is 0.18. It is 0.22. And very similar to that, we have for these data points, if I talk about, this might have a possibility of 0.90. This will have a probability of 0.92. Something like this, you understand. Now, what we do is this. Let's suppose this is my 0.1, 0.2, 0.3, 0.4, 0.5. There are 5 points here and 4 points here. Now, in this case, what we should do, these are probabilities. That for this point, take a look here. For this first data point, what is the possibility? We touch it on the line and we get a probability of that. That for this patient, which has been actually classified by this data point, which is actually represented by this data point, the probability of this patient having diabetes is 0.1. So if any patient has a probability of 0.1 of having diabetes, is he going to be critical case? No. It is very simple that this person is not going to have diabetes. The second patient also, third patient also, fourth also, fifth also, they are not going to have diabetes because their probabilities are very low. So with low probabilities for non-diabetic patients, we are able to identify very properly. So what will be a very good S curve? A very good S curve will do what? It will go, it will create the S curve in such a way that the probability of these data points are very low. Okay. The patients who are non-diabetic, their probabilities should be very low. That is how you have to create a S curve. And the probability of these data points, this one, this one, this one, this one, it should be as high as possible. Because they are all belonging to class of one. If I have a very high possibility, so it is very easy for me to decide that this patient is a diabetic patient. And if they have a very low probability, it is very easy for me to identify that this patient does not have heart disease, does not have the case of diabetes. So what we do basically is we do this maximization. What maximization? Let me draw this thing. You will be 100% clear after this point what we do. Okay, how do we get the best S curve is represented by this, is given by this. So what I just told you, what will be considered to be a best S curve, a very good S curve for us. A very good S curve will have a very higher probabilities for these data points, which are telling me that the person is diabetic, and very low possibilities, very low probabilities for the patient who are non-diabetic. If I'm able to achieve that, I get my best S curve. If it has outlier, no outlier, does not matter. So suppose for creation of this one, I have taken, let's say, beta naught was minus 15, suppose, and beta 1 was, suppose, 0.065. I started with this. It was a line. Now, why I have said beta naught is minus 15? Because if you see here, whenever your line is created, linear regression line, into this case, they always cross the one part, and they go beyond that. They go into negative direction. That is why the beta naught that you're going to get, okay, that is what the beta naught you're going to get will be negative. So suppose I started with this point. I started with a line, and in my line there was some outlier, suppose. So I created this, and it will give me a very bad line. Suppose my line should be like this. Okay, my line should be like this, but my line is like this. So with this line number 2 and line number 2, what will happen to the S curve? Let's suppose for this line number 2, the S curve is actually created like this. But if I change it to my line number 1, if I'm able to change the beta naught and beta 1 values to come back to line number 1 by changing it, if I'm able to do this, then what will happen? The S curve, which actually look like this, then it will start to look much better, and it will start to take a proper form of this thing. This is the S curve of line number 2, and this is the S curve of line number 1. And you can see out of these two, which one feels better. The one that feels a little better is the line number 1. And this is all visual. You can make it little better also. To just show you much better comparison, let's say the S curve that is created is something like this. Does not feel good. But my line number 1, the curve given by line number 1 feels good. So what we did here, let's suppose this curve number 2 we got with a beta naught. Suppose it was minus 13 and beta 1 was 1.2. Suppose this was our line, and according to this line, I got a shifted line, which is my line number 2. And what happened with this line number 2? I got a very bad S curve. And how do I know this is a bad S curve? Because we can see visually, but how will my system know? So what it will do in this case, it will also make multiple S curve and then compare their performance. Let us see how. So you take a look at this S curve that I created. This is my good S curve, the best S curve that I have got. But how will it come to this point? it should be doing some comparison that this curve is better, this curve is not better. So suppose it has created one more curve, which is like this. This is also an S curve, and the above one is also an S curve. Now, which one do you think is giving me a good answer? According to the probability maximization that I've told you, which one feels good to you? These both are S curve. Is the first one better or is the second one better? In this case, the first one is better. Because what I have said, you have to do this probability maximization, that the probability of this data point is higher, is very high. But according to second line, what is the probability of a data point just falling on this line? So that is the case here. The S curve, which is giving a higher probability to the data points which are in the class 1, that is very good. Otherwise, you see, if for these data points, I'm actually assigning the probabilities here, that the probability of this data point, which has been classified into class 1, is, you can see, around 0.5. So that will become very difficult for you. Okay. The probabilities are around 0.5. So you will be in a confusion. Should it be in the class of non-diabetes or should it be in the class of diabetic patient? You'll get confused. But if you see the probabilities are 0.9, 0.92, 0.95, like that, you will be able to easily decide that, okay, these patients belong to class 1. Okay, these green lines are C. I have classified this data point, right, into class 1. the blue ones. Everyone understand this carefully, that these 4 data points I have in my class 1. Class 1 means diabetic patient. So all of these patients are diabetic. What I have done with this, I have given a probability. When I said to my machine learning algorithm, to my logistic regression, that you learn the pattern. What pattern it is actually learning? That the patient who had diabetes, they had the higher probabilities according to the curve. So it will create such a curve that gives higher probability to these data points. Okay, these data points, which are actually the patients of diabetes, it will give them higher probabilities. So if it gives them higher probability, if I get tomorrow a new data point, I will map on this curve, I'll be able to get a better answer. See, if suppose a new patient comes tomorrow, a new patient is here. I don't know whether this patient is non-diabetic or diabetic. I don't know that. So there are 2 S curve for me. This is the second S curve. This is the first S curve. Where do you think you will be more confident to classify? One, I will map it on this line because this is the S curve I have created by learning the patterns. And one, this is the S curve I have created. Now in the line number 1, in the curve number 2, if you see, it is giving me a probability around 0.5, 0.52, 0.53, around that. But here, according to this S curve, I'm getting a probability around 0.9. So where you will be very confident and you can easily say that this person is diabetic. Using the curve number 1, you will be very confident. So how did we get this first curve? This is happening during the learning. When I said that logistic regression dot fit X train and Y train, when I do this, then this S curve is being created. And how this S curve is being created, it actually creates multiple S curve, and it sees that whichever S curve is giving me maximum probability. Okay, whichever is giving me the maximum probability of this. Let's see, just 1 minute. Let me explain you the last thing. So this is, let's say, your point number 1. This point you see is the point number 1. This is the point number 2, or not here actually. Point number not, let's say the probabilities. So this point you see, it is probability 1. This is probability 2. It is probability of 5, probability of 4, probability of 3. Just 1 minute. And probability of 2. What is this P2, P3? For this data point, what is the probability of it falling into a class? It is represented by probability of 3, P3. And what is the value of P3? 0.15. So it means that for this data point, we are giving a probability of 0.15 for this data point, third one. Similarly, this is my point number 6, and this is my point number 7, this is my point number 8, and this is my point number 9. So what we do in this case, if you see this is the probability, what will be this green line in this case? If this line from the dot to this S curve, if there is a distance, I'm telling that as a probability, what will be the green lines in this case? Will it be 1 minus P1? Will it be 1 minus P2? Will it be 1 minus P3? And will it be 1 minus P4? And will it be 1 minus P5? So I am telling that this data point has a probability by this much distance, correct? This much distance. So if this is the probability of a data point, this is 1 minus probability of that data point. So let me write this final thing for you so that you get the 100% idea. So the final thing is that to get the best S curve, okay, out of all the possible S curve, to get the best S curve, what we do is the maximization, which is actually written by this. So what we do in this case, see, what we have to minimize. Tell me what we have to minimize here. We have to minimize the probability 1, probability 2, probability 3, probability 4, and probability 5. We have to minimize these. The minimum they are, the better my S curve is. So if I have to minimize this, what I will have to maximize? 1 minus P1, 1 minus P2, 1 minus P3, 1 minus P4, 1 minus P5. I have to maximize these for the first 5 data points. And for the last 4 data points, P6, P7, P8, P9, what we have to maximize? The probability, not 1 minus probability, this green line. This I have to actually maximize. So let me write down for you. So the 1 minute, I'll summarize it. Don't worry, I'll not keep it complicated. So the best fitting S curve will be the one that maximizes the this product of this, or let me just write 1 minus P1, 1 minus P2, 1 minus P3, 1 minus P4, and 1 minus P5. We have to maximize this, and then we have to maximize P6, P7, P8, and P9. We have to maximize this. If I'm able to maximize this product, I'll get a best fit S curve. Now, whichever S curve has these maximum, that will be my best S curve. So that above figure was little complicated. Let me show you a small example. So suppose one S curve is like this, the final explanation. Suppose one S curve is like this, and one S curve is just like this. Which one will be better? This one will be better in these 2 cases. Why this one is better? Because we have to do the probability maximization. Probability maximization means if there is a data point which is actually falling into the class of 1, so that data point should be given a very high probability. So suppose a new data point comes up here. If I match it, this is giving me a very less probability of around 0.5. That is not good. So I should be aiming for as high probability as I can. So which curve is giving me that? This curve. Suppose there is a third curve also, like this. Out of these, which is still better than curve number 1? Because for the data points which are actually belonging to class of 1, it has given them higher probabilities. The data points which are belonging to class of 0, it has given them minimum probabilities. That way, the curve is actually identified. So how would you get this 1 minus P1 maximum? You will get 1 minus P1 higher when your P1 is less. Okay? See, what I told you, that this distance of this data point, see this data point. What is this data point? This data point has a probability of 0.1, correct? Now, what should be my best fit S curve? I told you that my best fit S curve should be in such a way that it gives a very less probability to all the data points which are non-diabetic. We have to minimize the probability of these data points which are non-diabetic. Okay, these patients. So if I'm trying to minimize P1, P2, P3, P4, P5, what is the opposite of that? If I maximize 1 minus P1, 1 minus P2, you automatically get the minimization of P1. Because if you see, if P1 is suppose 0.1, then what will be 1 minus P1? 0.9. If my P1 is 0.3, what will be 1 minus P1? 0.7. So in which case 1 minus P1 is maximum. If my P1 is less, if the probability 1 is less, then 1 minus P1 is maximum. So we say a common formula that we maximize 1 minus P1, 1 minus P1, P2, 1 minus P3, P4, P5. And for these data points which are in class 1, we should maximize P6, P7, P8, P9. This, the green lines that you see, for the non-diabetic patient, the upper ones, the upper line, and for the diabetic patients, the probability that we are touching on the S curve. We have to touch the S curve. No need to create the linear line. The linear line is not created in this case. That was just to explain you the concept. But once the concept has been created, once the sigmoid algorithm has been created, the logistic regression, then again, line is not created again and again. You just change the beta naught and beta 1 values. And once you change the beta 1 and beta naught values, according to this equation, automatically the curve will start to change. The data points which are less than 0.5 probability, we try to minimize that. And the data points which have 0.5 and greater probabilities, we try to maximize that. We try to give them as higher probability as possible. So just look at it. Just look at this curve. You will be clear that the green lines I have created, I'm trying to maximize those green lines, all the green lines. See, there are two cases. First is the case of a training data. When you're taking a training data, you are using that training data to create an S curve. So you need to identify that you're saying if there is a patient of a blood sugar level higher than 250, but they belong to non-diabetic patient. See, sometime it can happen that a person is not having diabetes. Suppose there can be one case of this data point also. Okay, this data point also. Now, what is this data point actually telling you? This data point is telling us that there is a patient who is what? Diabetic. Okay, this patient is diabetic, but they have a very actually lower blood sugar as compared to other diabetic patients. This patient is diabetic, but they have a lower blood sugar level. This happens. See, if a patient came to the hospital for checking that does this patient have diabetes or not. So maybe they were doing exercise, they were not eating anything which is having sugar. So their sugar level went little down, but still they have diabetes. So there can be some cases like that also, but that is going to make the explanation little difficult for now. Leave that for now. Yes, so how are we actually solving the case of outlier? That is one thing to understand. How do we solve the problem of outlier is still might not be clear. So the case of outlier is that suppose I took a line which was having outlier. Okay, understand this. If I had a line which is having outlier and I'm converting that line into S curve, that S curve will not be good. So suppose according to this S curve, we have got, sorry, according to that line which was affected by the outlier. So I get an S curve like this, which is not a good one. S curve like this. So what will happen? My linear, the logistic regression which algorithm which is there. What logistic regression will do, it will not just create this one line. One line it will create, one S curve it will create for the line which was there. But what it will do, it will change the line also. That let us see, if I change the line from best fit to this direction and this direction, how curve changes. If this is my line and this line has the outlier problem. If this line is there, the first curve that will be created, suppose it is like this, does not look like S curve. It is very bad. Why it is happening? Because outlier are there. So I took this green line and I created this curve. Then what my logistic regression will do, it will not stop here. It has to do optimization of the process also. That it will change the line. It will change the line in what way? First line is this, so it will try to shift it in this direction, and it will see. It will create an S curve for this line also. It will create an S curve for this line also. It will create an S curve for this line also. It will create an S curve for this line also. So it is going to create multiple S curves. You don't have to visualize that, but this is what is going to happen. So for multiple lines, it will create multiple S curves. And then it will see the S curve for which line is actually giving you best result. What best result? What is the best result we are trying to see? This maximization. Which line or which S curve is actually giving me this maximization? The product of these things is maximized by whichever curve that is my best fit S curve. S curve is not dependent upon best fit line. It is actually dependent upon linear regression normal line. Okay. If I say this is my linear regression line and this is also my linear regression line, but only one will be best fit line. So my S curve is not dependent upon best fit line. Best fit line is the concept of linear regression. Here I am just using a linear regression line. It can be best fit, it cannot be best fit. But what I have to find out is I have to find out a line which is giving me best sigmoid curve, best S curve. I don't have to find best fit line. Got it? So what I said in this, that if you take a data point, obviously according to this data point, first line will be created like this. That is a very obvious thing. Because my line is affected by the outlier. So first line which I create, that will be a best fit line in this case. It will be created. But we will not stop here. What we will do, we will create multiple lines in this case. And when we are changing multiple lines, then what will happen? Our S curve will change. So we stop at a line which is going to give me best S curve. So this was my first line, second line, third line, fourth line, and fifth line. So when we came to fifth line, we saw that it is giving me a S curve, which is maximizing the product. Which product? This product. That fifth curve. So we will take that fifth curve is the best S curve. And whatever is the beta naught and beta 1 attached to that, that is what your final answer is for that equation, for that beta naught and beta 1. Now makes sense to everyone? Got it? Selection of curve you see is according to this. I told you that this selection of best fitting S curve will be the one that maximizes this product. Remember this. How do we take which is my best fit S curve? Like this or this or this? Is whichever maximizes this product. Remember, this is the answer you will be giving in interview to tell that how do you identify this is the best fit S curve or this is the best fit S curve. If you take a look at this example, is my line number 1 best fit or sorry, curve number 1 or curve number 2 or curve number 3, which is best fit? How do you decide that? You can see it visually, but machine does not see it visually. So to decide it that the curve 1 is better or curve 2 is better or curve 3 is better, this product has to be maximized. The product will obviously give a number. Probability 1 will be, let's say it is 0.1. So what will be 1 minus 0.1? 0.9. So very similar to that, you will have just some numbers between 0 to 1. And you will be getting some probabilities, some cases like 0.003. Okay, in some cases, see, all the probabilities that you're going to get will be between 0 to 1. So you're not going to get a higher value. It will be lesser than 0 itself. Okay. So the maximum it is, the better it is. If you take, let's say, this S curve, point number 2, the curve number 2, for this, let's say I have got 0.00005. That is the final product I have got. So is this one better or is this one better? So this probability, the final answer of this product has come out to be the 0.003. It does not matter what is the value, just you have to do the comparison that what is the final value of this product. And the final value of this product will be some number like this. And whichever curve has the higher probability, whichever maximizes the probability of this or the product of these probabilities is the best fit estimate, which in this case, suppose is curve number 1. That is the final answer. So the logistic regression that we have studied, you just save the file in your notebooks. In the Jupyter notebook, you make a folder and you can just put these files. Or you can just drag and drop into the homepage, both the data set and the notebook file. But for now, you can just run the code with me. I'll explain you wherever it is different. How do we approach that logistic regression and what else? What are the things that we are going to do? Let's understand it. Now we have a data as such. I have read the libraries. I'll explain what these libraries are. You must have seen some of them. Import numpy as np, import pandas. We have seen the trend test split. Also, you have seen sklearn.model selection. Now we are using two new ones. One is sklearn.linear model, inside which our algorithm function is there. Then we have sklearn.metrics, which will be something as accuracy score. So if you remember, I told you that the metrics to check the performance of the model will be different for regression and will be different for classification. For regression, we saw it was MSE, RMSE, R2, adjusted R2 score. But in the case of this classification dataset, classification problem, it will be accuracy score, precision score, classification metrics, confusion metrics, those kind of things. So we'll understand about their metrics also. So what we have is I'm just reading the libraries, then I have the data set. Checking the data set, we have this. Now this is for a heart disease prediction. We have to learn the pattern and then we have to classify, we have to learn the pattern basically in this case. So you can see we have the inputs from age to this thal and the target column is there. So target column is 1 and 0. 1 means that patient has heart disease, 0 means that patient does not have heart disease. So we check the data, it is very simple. You can check the shape of it, info of it, info to check the missing values are there or not. But now something new comes up here. There's a new use of info in this case. What you have to see is this, all the columns which you are seeing, the column number 0 to column number 13, all the columns which are there, when you check their data type, it should be either integer or float. If it is anything other than that, if it is object, other than that can be what? Object. So if it is an object column, any column, if it is showing object, you need to make it integer or float. You'll have to do it that. We will see that in next week. So what should be there? That every column should be either integer value or a float value. That is only allowed in machine learning. Machine learning does not work directly with the object data. So object data has to be converted into numbers. And where we will do it? We will do that in pre-processing step. So what we do, we check the missing value. There is no missing value. So there is no need to clean the data for now. You will do that. You can check the outliers and everything that is upon you to check. Now in the classification, the main part starts from here. The main understanding of how to apply a machine learning algorithm, which is for a classification data, starts here. So what is this? This is a pandas function dot value. Now what is this dot value count actually tell you? you have to always check the value count of the output column. The target column is our output column in this data case. What does it do? In the target column, it is just nothing but 0, 1, 0, 1, 0, 0, 0, 1, 1, 0. These type of values are there. So it tells us the unique value, right? How many times 1 is there, how many times 0 is there. Because if you see here, you will say that there are total 12, 13 data points, but actually they are not 12, 13 data points, just two of the values being repeated multiple times. So that happens in categorical columns. So you have to check the output column. And why do we check the output column? Because we get the idea about the data. So what idea? If you see here, there is 1 written 165 times and 0 is written 138 times. Total 303 rows are there in our data set. The example that we're taking, out of which 165 times 1 is written, 138 times 0. Now this tells that 1 means defective heart, the person who has a heart disease, patient. So we have information about 165 patients who have heart disease, and we have information about 138 patients who don't have heart disease. Now, why is this important to check? We check this to check whether the data is balanced or not. The data is balanced or not. This is what we need to check. Because if the data is balanced, we don't have to do a lot of things to take care of that. But if data is unbalanced, imbalanced, so we have to take some extra measures to solve that problem. Otherwise, it will give you a very bad result, very bad information. There are some problems attached with imbalanced data. I'll explain that also. So can you tell me any example where you get very highly imbalanced data? What kind of cases? Yes, the data to be balanced, these two should be closer to equal. Okay, these two should be closer to equal. The number of 1 and number of 0 should be equal, like 165 it is there, 0 might be 150, 160, 170, but not lesser than that. So this is kind of a balanced data, not exactly very balanced, but you can't say that it is very highly imbalanced. Customer analysis, yes. Churn analysis is one imbalanced data, or everyone can understand the fraud detection. Okay. Fraud detection is a very classic example of imbalanced data. See, suppose if I go to Amazon.com and if I ask Amazon.com that how many transactions were fraud. So let's say in 1 month, they are doing 100K transactions. Okay, in 1 month, they are doing 100K transactions. So what will happen? The no fraud in this case will be 99.5K. Okay, and fraud transactions will be maybe 0.5K. That is the kind of data always you will see if you're working on a fraud detection, credit card fraud detection kind of things. If you're studying, you'll always get this type of data. Always the fraud is very less in number, very less in proportion as compared to the non-fraud transactions which have happened. So you can see this is a case of very high imbalance in the data. And when we have this kind of imbalance, we have to take some extra measures to do those things. We will talk about those measures. Okay. For now, I just told you that this value count tells us about the balance or imbalance of the data that you have to check for every classification problem. Every. So I have seen that it is not very imbalanced, not very balanced. So you can take both the approaches, considering it as non-balanced or considering it as a balance. It will not harm in both the cases. Let's see what we do. So I'll give you one example or one process that you will have to perform if your data is imbalanced. So once we have found that out, we start into the process of machine learning. When we start into the process of machine learning, that is called data pre-processing. In that, the first pre-processing which we do is X and Y. identifying all the input columns into X and the output column into Y. That is the obvious thing. And after that, what we do, we divide our data, or we split our data into 4 parts: X train, X test, Y train, and Y test. This is what we do. Now, in this case, what we are looking at the split, which is 20% test, 80%. Because if it is imbalanced, we need to take some extra measures. I have explained it many times. Okay, I have not shown you what measures, but I'm going to talk about that in further session. Yes, so that the result is not biased. That is why we have to check the imbalance. And also we need to do some extra processes, some extra things we will have to take care of to make that data balanced, or do some of the things which does not affect, which is not affected by the imbalance in the data. We'll see about that. But one of the thing is, if the data is imbalanced, in the case of train testlet, you bring in stratify. What is this stratify? We will talk about this. But you have to now use this stratify, which you were not using earlier. If the data is balanced, you don't use this stratify parameter, but the data is imbalanced, you use this stratify parameter. And in stratify, you always have to give the y. Y is a variable which has the output column. You always give y. What does this mean? We will talk about that. So once this is clear, once the split of the data has been done, then you have the standardization of the data. What is this standardization of the data? It is very important to understand, but let me just wait for a few minutes and then explain it. That we divide our data into X and Y, and then we have a split. Okay, we do that in the linear regression also. Here I'm also doing the same thing, nothing changes. So till here, everyone should be clear. Himani, I said that if this is the data, you can see this data is not very balanced also, it is not very imbalanced also. So I said that in this case, you can treat it as both the ways, treating it as balanced, treating it as imbalanced. So I just took an extra measure that I took it as imbalanced and I applied that measure. It does not harm anything if you are treating as a, it will just make it better anyway. What is the stratify? I'll explain about that. Then you do the standardization of the data, what it is, why it is important. Wait for 2 minutes, I'll talk about it. But after splitting your data into 4 parts, what we do? We do the model training. In model training, we have seen we bring in our machine learning algorithm and we apply that. So my machine learning algorithm is this logistic regression. And in this case, we have log reg. I'm saving into this variable. And then what we do, we take this log reg and we say dot fit. Very similar process to what we have seen in the linear regression examples. We give X train and Y train. Now, as soon as I run it, you will all notice there will be a this kind of warning given to you. Now, why this warning comes is one very important thing to understand. Because here now you're going to understand the topic of hyperparameter tuning or making your model better. How do we do that? I explained when I was talking about the machine learning concept. I told you there is a concept of tuning your model to make that model better. So how do we tune that model? It is called hyperparameter tuning. Okay, that we will do. How do we do that? See, I use the logistic regression. It is nothing but a function. And whatever function is there, always function takes some parameters. So similar to that, this logistic regression is also a function and it also has some parameters. And because of this, one of the parameter only, you are getting this error. You see, the error is increase the number of iterations or scale the data. This is the problem because of which it is giving us this warning. It is saying that total number of iterations reached limit. What is this? Let's see. See it carefully. Don't write the code for now. Understand it. So when I go to the documentation page of this logistic regression, you'll notice one thing which is going to help you get rid of that warning. Now the logistic regression that I've written, I've just given an empty bracket. I've not written anything inside the bracket, but actually these are all the default values which are working in that bracket, which are there in that bracket we are not seeing, since these are default values. So in the pandas also, in NumPy also, in visualization also, we have seen that there are some default values which are there. We don't write the default values. But if I have to change the values, then I need to mention it. So we'll talk about them one by one, and a lot of things you will see in the further classes also. For now, I'm getting a warning, which is this. So this warning is telling me the total number of iterations reached limit and increase the number of iterations max item. It is guiding me also that what I should do. I should increase the number of iterations. What is this? What it is affecting? We'll explain. But if you see here, there is a max iter parameter here. And max iter parameter is 100 by default. Now, can anyone tell me what is this max iter 100? What does this mean? What it is doing? It is by default 100. And when we have this 100 value, it is telling me it is giving me a warning that total number of iterations reach limit. So increase the number of iterations. What is iteration? Repetition of something. So now, can you identify what is this about? I'll tell you what is this about. What is this iteration? Iteration of what? So this max iteration 100 is talking about there are 100 S curve or 100 changes in or 100 pairs of beta naught and beta 1. 100 pairs of beta naught and beta 1 has been taken and 100 lines have been created. According to 100 lines, 100 S curve has been created. Now, by default, logistic regression creates 100 S curve and then it compares which S curve is giving you maximum of that product, which we have seen. Now, what is this warning telling me? That 100 is not enough. I think I can do better. So some code has been written which is actually talking about this. So how does it know that 100 is not better? Because the only task it has to do, it has to compare how many S curve it is making. So how does it know that 100 is not enough for this? For logistic regression also, there is a gradient descent concept working. What is this gradient descent? Gradient descent is an optimization algorithm. It tells you whether you have reached the best S curve or not. We are not seeing the concept of it for now. It will be explained to you later if it is required, but it is not required for now. So it tells us that this gradient descent tells us simply that by creating the 100 S curve, we have not been able to reach the best S curve possible. It can be done better. So what I do now to remove this warning, I need to just give it more iterations. Let's say 400. Is it working? No, not working. 700. Still not gone. 900. You see, after 900, this iteration gone. This error has gone. 800 still there. 850 is still there. 880 is still there. But now it is taking 900 iterations. So once we have given 900 iterations, we are able to solve this problem. And the other thing it is suggesting us that you scale the data. What is scaling the data? You see, this is the scaling of the data. So we'll observe you have to do one of the things. Either you increase the number of iterations or you scale the data. That way this warning will be gone. Now I have not done the scaling of the data. I'm just following the approach that I'm increasing the number of iterations. So this process that I have done is called what? This process is called. Now anything you write inside this bracket of the algorithm. Okay. Logistic regression is the algorithm. And in this logistic regression, if you see there is a bracket. And in this bracket, you see max iter. What is this? I have given on something now. In the linear regression, if you remember, we left this bracket as it is. We did not write anything. So whenever you write anything inside this bracket, this is called hyperparameters. And if you change the value to make it optimal, it is called hyperparameter tuning. Okay, when you are making it optimal, it is called tuning, but just this parameter is called hyperparameter. Okay, this thing you should remember. Now, there are multiple hyperparameters you can change. It depends upon what type of data you have, what type of accuracy you require. Yes, for you, it might be 1000, it might be 800. For now, you can just see that it depends upon different samples it has taken for the training and test. That also defines the number of maximum iterations. So once you have trained the model, then what is the next process we follow? So for now, focus on this code. Try to understand this. Once we have done the training of our algorithm, what has happened? It has found that one best S curve. Now we are using that best S curve to predict the X test value, the further values which comes. Anything that you write inside the bracket of this function, that is called hyperparameter. Okay, this max iter is called a hyperparameter. Now this 900 I have done some experimentation. I tried 100, then 200, then 300, then 400. When I reached to 900, I just tried a lot of things. So when you're trying a lot of things, that is called hyperparameter tuning. Tuning means optimizing that. But by itself, this max iter is called hyperparameter. To optimize this hyperparameter, it is called hyperparameter tuning. See, why are you confused about this max iter? It is just very simple thing. See, what is this max iter? I told you that I explained many times that what happens, my logistic regression does not create only one S curve. I told you it will create many S curve. So this max iter is telling me that for this data, we had to create 900 S curve. Then we were able to find the best S curve out of them. By default, this number was 100. So by default, logistic regression does what? If it takes any data, it makes 100 S curve by default. But in our case, 100 of them was not enough. So what we did, we changed it to different numbers. It is not that always 900 will work. In some data set, 200, 300 will also work. We'll see about that. But this is according to data. This is all pure experimental. This is not a single number. Hyperparameters are never a final value. It is depending upon different data sets. If you're trying to do this data set, it will always be different from that. Okay. So this is purely experimental. If you're working on this thing, then you will have to keep changing it, which is giving me how much accuracy. You will have to check, increase it, decrease it, check the accuracy. Got it? So once we have done this dot predict X test, what we do, we save that into Y prediction, and this is the value. And what we do with this Y prediction, we have to compare. Now, in this case, I will not be using R2 score. There is something called as accuracy score. And in accuracy score, I just need to give the two same things, Y test and Y prediction. If you have gone through the code of the linear regression, you should have all gone through it. You will understand it is the whole same process. Just only two things I changed. I changed this and I changed this accuracy score. In the case of linear regression, this function name was linear regression. And here to check the performance of the model, it was R2 score, but now it is accuracy score. Just these two small changes we have done. Apart from that, everything is same. So I'll not run the standardization of the data. I'll explain it in a few minutes. So we have got an accuracy of 0.85. That is a good enough accuracy for the starting time. We have got that. Suppose I run this for 200 iterations. Now you see what is happening. If I have taken 200 iterations, what is happening to my accuracy score? It is being affected. Why it is being affected? Because I have taken only 200 S curve and my logistic regression told me that 200 S curve is not good. I am not able to get the best S curve out of these 200 curves that you have created. You need to make more curves. So what we did, we increased this from 200. 900 was the optimal. Once we got it to 900, you see the accuracy automatically increased. So what we did hyperparameter tuning. When we did the hyperparameter tuning, what happened? The performance of the model boosted. Now, it is not that every time if you change the value of this, your performance will be boosted. Maybe if I tried 1300, 1400, maybe it goes down. So you need to search, you need to try different values, and you just search where it is doing best. So let us understand how we have got this accuracy score. Okay, it is not accuracy test, it is accuracy score. How have we got it? This is very important to understand. But for now, try to understand it. It is not a very difficult code. Most of the things you have already seen. We are trying to do something new. Now let us take this data. Let us take this data and let us understand what is that accuracy score. If I've got 0.85, how have I got that? So take a look. Let's say this is my 100% data. This completely. Out of that, I'm taking 20% as my test data. So suppose I have taken this much. Suppose this is my 20%. What we have seen, this is my X train. Understand this carefully. This is my X train. And this is my Y train. And this is also my Y train. And this is my X test. If this is my X test, what is this? This is my Y test. What we do, we train our model on this X train and Y train, X train and Y train. These are my training data. And what we do after training, dot fit, when I do, I train the model. When I say dot predict, I give the X test value. When I give the X test value, what it does, it gives me some prediction result, which we save in this file thread. Now you see, it is doing what? It is predicting the outcome for these data sets. What does it think about these patients? It will tell me about them, what it has learned. So let's say for this patient in row number 164, for this patient, it has said that 1. For second patient, it has said 0. For third patient, said 1, 0, 0, 1. Now, what we do? How do we get an accuracy? Accuracy is the performance of the model, that how better it has learned the pattern, how able it is able to predict. So now we compare these two things. We are comparing the results. This is the actual, and this is what my model has predicted. So we compare them. Now you see here how many mistakes I have done and how many times I have classified correctly. So one mistake I have done here and one mistake I have done here. 2 mistakes we have done. So what is the mistake here? The patient was actually having heart disease, but my model said that this patient does not have heart disease. This place, if you see this one, the patient did not have heart disease, but my model said that this patient had heart disease. So to get the accuracy of any of the model in the classification, we compare their results. So comparison will be like this always in the classification. So how many data points are there? 6. So we have made 4 out of 6 classification correctly. Okay. And what is this? Around 70%, you can say. Not exactly 70%, but you can say it comes to be 0.7. So accuracy score is also between 0 to 1. And this number tells me that the performance of the model, the accuracy of the model is 70%. This is what it is. Okay, 70% accuracy. See, as I told you, what happens here? In this case, it is making 900 curve. Why it is making 900 curve? It is dependent upon lot of reasons. First, we have very less amount of data. Since we have so less data, just 303 rows are there in our data. So because of that, it is causing a problem to my machine learning that it is not able to learn properly. Since it has a very less amount of data, so it is trying to create a lot of S curve to become confident, to be sure that it has learned it properly, since it has very less examples to learn. If I increase the amount of data, if instead of 300 rows, if I give it 300k rows, then you will need lesser iterations. Maybe 100, 150, that will be enough. That is the first problem, that we have a very less amount of data. In this case, we need to make a lot of curves because it is not confident, it has not learned properly since the data is very less. The second problem is the scaling of it. The scale is not good in the data, and we have to, and that is causing one problem. I think everyone is clear about this. Accuracy is correct. How do I identify whether my model is underfitting, overfitting, good, not good? We have to see. One by one, everything will come. See, now what we did, we started our process of machine learning. And in the case of machine learning, what happened is that what did we do? I explained you that there is a processing of the data. The processing of the data is nothing but you divide your data into X and Y, then you split it into 4 parts. And if you split your data into 4 parts, these are two basic things which is required in all the data. But there is this standardization of the data which will be required in some cases and not required in some cases. Where it is required, let's see. So if you come here to your main data set, for 1000 I'll show. Wait. See, what do you think is the standardization problem? What do you think is the scaling problem? Can you just tell me intuitively if you look at this data? I'm saying that I have to scale the data. And there is a problem because of which I need to scale the data. Why standardization needs to be done, why scaling needs to be done, we need to understand. Okay, order of the number or the scale of the number. See, if you observe this column or this column or this column, what they have numbers which are very high. Okay, cholesterol level in this case. So we have the cholesterol level which are in the number of 200s, 100s, very high number. These are 3 columns. But in comparison, if you look at this column, which is old peak, this column has a data whose scale is very less. The numbers are like 0.6, 0.2, 0.5, 2.3. So if you observe here, this column, this column, this column has a very big scale of data, and this has a very small scale of data. These numbers are very small as compared to these number, these number, these number. Now, what problem happens with this? You might think that it is okay, the way the data is, that it should be like that itself. What is the problem here? The problem with most of the machine learning is that it will actually give this column, and this column more importance as compared to this column. By just looking at the data, since these values are higher number, these values are higher number, and these values are higher number, it will give these 3 columns more importance. Okay, without even checking the pattern, without even checking the data, are they even important or not? It will actually assign them higher importance. And it will be affecting the accuracy according to them. What it will do, the old peak, the slope column, the X-ang column, the CA column, TAL, CP, all of these columns, it will give lower priority, lower importance because of their scale in the data. So what we do, we take the complete data set and we give a common scale to every data, a common scale. And for that purpose, what we do, we use the standardization process. So for the standardization process, we'll see the code tomorrow since we are above the time. Some of you have to drop now. So we will see about that tomorrow. But that is the one problem. And if any data set has that kind of problem, the scales are different for different columns, you will have to take care of that. But it does not happen for every algorithm. Some algorithms are affected by the scales of the data, some algorithms are not affected. So the linear regression, logistic regression, these are 2 algorithms which are lot affected by the scales. But in the further session, we'll see the decision tree, random forest. They are not affected by the scales of the data. There we don't need to do standardization. 0.85 means 85% accuracy. Simple. It is not 80%. In coding also I'll talk about. That is what the conversion of yes and no into 0 and 1 that I was talking about, that is what encoding is. So if there is any column which is having the value of yes, no in a text format, machine learning does not understand yes, no in the text format. So you have to encode yes into 1, 0 into no. That is the process we will talk. That data comes, we will talk about it. We can do it by mapping. There are two different processes. We can do it by simple mapping also, and we can just do it by a function also, which is one hot encoding. Both the processes are there. No, it is not that if I increase this from 900 to 1000, it is not always going to increase the accuracy. Because what is happening here, when I took 900 curves, it has actually found the optimal curve by running it for 900 times. So if I am taking 1000 iterations, 2000 iteration, it is not going to affect it. Since I've already got my best S curve, so if you can't get anything best than best, it is already the final maximum, the best one you have got. So even if you run for 1300 times, 1400 times, it is not going to affect. It will make sense when before reaching the optimal. So from 200, if I have taken, for 200, you see it is 0.81. But if I reach from 200 to 400, it might be little. So it was earlier 0.814 something, but it is now 0.8196. Little bit it has increased. So it will increase before reaching the optimal number of S curve here. But if I have got 900, 900 is the maximum. After that, changing anything will not making any difference. Okay. Regex. Regex is a part of the data processing actually. If there is a natural language, you convert that into this. So regex you will study later in NLP, natural language processing.
I have one more announcement for you guys. For dedicated learners like yourself who want to make a difference in their career, for the first time, we at Intellipaat have decided to offer a straightforward 20% discount on our premium data science course, which is in collaboration with iHub IIT Roorkee. If you want to take control of your tech career and do something extraordinary, do visit this link in the description box given below and fill the inquiry form. Promptly, a team of course advisors will reach out to you to activate the offer. So don't miss out this opportunity.
So in this case now, if you look at it, the standardization of the data, you can open up your code, you can run the code with me, but try to understand it for now. See, we were talking about that we started with the data. And when we started with the data, we have a data something like this. Now, in this case, what we see is there is a age column, thread BPS column, cholesterol column, phthalates column. These are four columns which has actually the very higher values, very big values as compared to any other column which is there. So what we need to do, we need to bring these scales down. We need to reduce these numbers to come into this range of numbers, like 0, 1, 2 kind of numbers should be there in these columns. 4. So what we do for that case, we have to do the standardization of the data. Now remember, standardization of the data. Now in this case, what we require is we have to do this standardization during the data processing part. So where the data processing starts? The data processing starts here. When we take our input and output column and we save that into X and Y, there our data pre-processing start. That is called data pre-processing. So once we have done this X and Y, then we split it into 4 parts. After splitting into 4 parts, then you are going to do the standardization of the data, not before splitting. Now in this case, only the that input data is actually scaled, not the output data. Output column you don't scale, just the input column. Now, how do you scale the input column is this thing. So let me just run this. So very similar to that linear regression function was there and logistic regression function was there in one of the modules. So there is a sklearn.pre-processing module as you can see here. And this module is actually helping us to do the scaling of the data so that we don't have to do it manually. It will take care of that scale. We don't need to give what will be the scale, it will manage from its side. Now, for that purpose, what it does is you write the standard scalar, it is a function, and very similar to the reading or loading of the machine learning algorithm, you just load that standard scalar, you load that into a variable called scalar. Then what we have to do is this main thing. What I'm doing here is I'm saying scalar dot fit xtrain. So I'm saying that take the input training data, and from the input training data, try to understand what should be the scale of the data. There were actually 4 columns for which we have to change their scale. We have to bring down their scale to smaller numbers. So what we say that in this scalar variable, we have actually stored this standard scalar. So we are telling to the standard scalar that learn the pattern from the training input column. Okay, training input columns, learn the pattern. That is what it is doing here when I say scalar.fit xtrain. Once it has learned the pattern, then what we need to do? We need to transform the xtrain and xtest both. So while we are making it learn the pattern, we will just give xtrain, not ytrain. Ytrain, we don't do it. Y is the output column. We don't scale the output column, just the input column. So I'm saying take the standard scalar, apply it on the training data so that it can understand what should be the scale of the data. And then I say what xtrain is equal to scalar dot transform xtrain, scalar dot transform xtest. So what I'm doing now, instead of using the xtrain and xtest, original xtrain and xtest, what we are doing is we are transforming it, then we will use that xtrain and ytrain into the further cases. Toby, you have forgotten standard D. In the standard spelling, you have written D. Okay, right. So what we have is scalar dot transform. So transform is transform the xtrain and save it back to the variable. Transform the xtest and then we save it to the variable. We are scaling it here, right? Nikhil, I said that here we are just learning the pattern of scaling. Got it? Here we are saying that learn the scaling pattern, how much they should be scaled. Like if any column has 230, 221, 240. So I'm just taking the xtrain input training data to help us understand what should be the scale. Once I have understood the scale, then I'm applying it to the training data and testing data to transform. For just the learning pattern, I don't need to learn it from the xtrain and xtest. Both are the same. So xtrain I will take for understanding the pattern, what should be the scale, and then I'm transforming it here. Now, in some cases, if you watch some videos, you will see this kind of thing also. So you don't need to get confused what it is. So at some places, what they will do is they will say xtrain is equal to scalar dot fit transform xtrain and xtest is equal to scalar dot transform xtest. So in this case now, what will happen? See, we will not have to do this scalar dot fit and then scalar dot transform. What I'm doing here, I'm doing something in 2 lines. I'm learning the pattern of xtrain in one, and then I'm transforming it into another line. But if you write scalar dot fit transform xtrain, then what it will do? What you're doing is you're learning a pattern of scaling and applying it at the same time to the training data. So you're actually doing this line and this line in the one single line. So once you have done this, you will see this kind of thing also. Fit transform is nothing but the combination of fit and transform together. But if you want to do separately, fit separately, transform separately, that is also fine. Both the processes you can take. There's no issue about it. The next thing is that in this case, what we have seen is uh, that we don't need to actually transform all the columns. There is only this stressed BPS and phthalates and this cholesterol. These are the three columns only we have to basically scale. The other columns which are there, they already have a very small values, and I don't need to transform all of the columns. So when you have done this, x train is equal to scalar dot transform, you have actually scaled all the input columns. But what you can do is you can just say x train and you can select those particular columns. Say trust BPS, and then you have the cholesterol column, and then you have, so we have this thal, and we have cholesterol, we have trust BPS, and then age column also. We have the age column also. And then what I will do, I will just do scalar dot transform, and in this case, I will give it here. So I can do this thing. Okay. And in this case, I am just doing fit transform both the things together. So you can do something like this. You don't need to transform all the input columns which are there, because all the input columns are not into that scale. So you can transform these few columns also. And what you should be doing out of both, should you be modifying all the columns or just few columns? You should be actually taking this approach where you're only transforming the columns which are having bigger scales. Focus on that. So what is happening here? It is actually the process of, so why are we doing this? I explained yesterday that we are actually doing this so that the input columns which are having bigger numbers, they should not be given more priority by the algorithm. I don't know if they are important columns or not, but because of bigger values, what my logistic regression will think or what my linear regression will think is they are important columns because they have bigger numbers. And then it will just make a biasness out of that, that I have to give this more priority and I have to give other ones not that much of priority. Okay, importance. So it will be a very bad thing to assume about the data because we don't know that yet. So when we do this, then we use this X train and X test for the further machine learning process. So before applying the algorithm, you have to scale the data, then you move to this. And this is called input, and that also when you have a lot of columns and lot of rows are there, then you will notice a little bit of difference, but not as such as big difference. So what is happening here when I'm doing the standard scaler? It is actually doing the standardization. And how it is doing the standardization, it is actually taking the data and it is passing it through the Z-score formula and scaled data. So we have studied about this Z-score formula, right? What was the Z-score formula? Does anyone remember? X minus mean upon standard deviation, right? So we have X minus mu. Mu is our mean upon standard deviation, which is actually given by sigma. So sigma is standard deviation and mu is mean and X is our data point. So if we have to scale the data, we take every data point in that row, in that column. We take a value, we subtract the mean from it and divide by standard deviation of that complete column. So what has been happening in standardization? This is the thing. Data is equal to Z-score formula, and then we get the scale data. So why we are taking the Z-score formula? Because this Z-score is also called standard score. Okay, another name for Z-score is called standard score. That is what we are actually using this. Not to centralize, just mainly to have a common scale. Centralization is a different thing. We want to have a common scale. That is the idea. So this was about the standardization of the data. Mainly you see cell number 7, 8, 9, and 10. For now, you follow this. And later I told you that you can do this also. and you can do this also. These are two extra things that I told you. But for now, 7, 8, 9, and 10. These cell numbers you need to see. Stratify, I think I should explain when we have imbalanced data. Okay, stratify, you will not be able to understand completely at this point because our data was not very much imbalanced. So I will try to explain it in the next practical that we do for decision tree. In that case, we will take data which will have imbalanced, a very huge imbalance in the data. There I will explain the main importance of stratify. This data has 165 examples of class 1, 138 examples of class 0. So it is not a very heavily imbalanced data. You can leave it. You don't need to treat it as an imbalanced data. And you can treat it also as imbalanced. It is not going to harm anything. Okay. If you treat it as imbalanced, it is not going to harm, but this is not the case of imbalance. The case of imbalance would have been something like if I had 165 here and only 50 examples in class 0. So there is a huge difference between both of them. That is where you will actually start to think of it as a imbalance. Now, what is this stratify? Yes, basically stratify is the sampling process. The stratified sampling that we have studied in the statistics part, this is the same process. So what does it do? Wait for some time. We will be talking about that when I take the imbalance data. Okay, so this practical part is clear, and also the confusion matrix I'll explain in few minutes. Let us start fresh for a new topic. Now, what are we going to talk about? We have already discussed about linear regression, logistic regression, their practical use cases, and also some of their performance metric. We have got some idea that how do we run the machine learning algorithm now. Some basic idea is clear, but I'm not saying that you should be 100% clear. Some idea you have got. Now, after that, what we are going to do is we are going to talk about one of the very powerful algorithm, which is called decision tree. So before talking about decision tree, let us understand what that is all about. So in this decision tree, we actually talk about tree-based algorithms. Okay. So in machine learning, there are some tree-based algorithms. Tree-based algorithm means the structure will be created like this. So in linear regression, we have noticed that we were creating a best fit line, which was kind of a straight line. Then in logistic regression, we created an S-curve to do the classification of the data. And now for the tree-based algorithms, what you will be doing is you will be making a tree structure. Now, whenever you make a tree in this case, it will be inverted tree, where this will be your root. Okay, whenever you take a look at the root starts from the ground, and then the tree grows up, then it has a branches, it has a leaves. So these kind of thing will be same here also, but it will be inverted, that the roots start from the top, and then you see there are the branches, and these branches will again go out into another branches, and then we will have something. And these last circles you see, after which I'm not making any further branches, these will be called your leaf nodes. We will talk about the terminologies in few minutes. But leaf is what? If you take a look at a tree, leaf is the last thing. After leaf, there is nothing. When you have branches, from branches, there are another branches broken out. Then on the branches, you have the leaves. So this thing that I'm doing, this split on two different directions, this is a branch. And the end of a branch, I'm having a leaf. And using these leaves, we'll be making decisions and we will be making our predictions. That is what tree-based algorithms are all about. I'll explain more terminologies here. So when we talking about this tree-based algorithm, the tree is created something like this. We will talk about its terminologies, but there are a lot of very powerful algorithms, tree-based algorithms. The first one is decision tree. Second one is called random forest. Then we have gradient boost. Okay, these are the five very famous or very powerful algorithms which are there in the tree-based algorithms. In all of these five cases, a tree-like structure will be created, not the linear line, not the S-curve, but a tree-like structure will be created. Tree-like structure means this. All of these five algorithms which I have written, they are created in such a way that they are very powerful. And because of them being so powerful, they are actually they work in most of the cases very well. So there is a platform called Kaggle.com, and when you go to Kaggle.com platform, you will see there are multiple competitions happening on global scale related to machine learning, data science, data analysis. Okay, a lot of competitions happen. So whatever data sets are given into those competitions, and they have to perform their prediction, they have to do something. So if you use these algorithms, random forest, gradient boost, XGBoost, ADA boost, it is most likely that your model is going to give a very high accuracy automatically. Okay, automatically it is going to give you the answer very high. Because of the way they are created, they are very powerful as compared to the logistic regression, linear regression, they are very powerful. If you go to industry also, and if you have to perform the classification task, you will see that you are using one of these five algorithms very frequently in many cases. Logistic regression is also there, SVM is also there, naive Bayes algorithm is also there for classification, but you will be using them a lot, these five algorithms. Now we will understand why they are so powerful and everything. I will explain you these first two algorithms. Now, these algorithms which are there, this decision tree, random forest, these algorithms are created for both the purpose, for classification also, and for regression also. We mainly use them for classification tasks since they were uh, actually created for classification. But now some modification has been done, and now you can use them both for the regression task also. So if there is a requirement, we'll be using them for regression also, but mainly for classification. This is a decision tree. Now, what is this all about? Let us see some of the terminologies before understanding the working of the tree. Okay. So tree-based models are said to be most used supervised learning algorithm. They can be used both for classification and regression problem. We can create highly accurate and stable predictive models with these tree-based algorithms. And tree-based models are decision tree, random forest, and the all others, the boosting also follows that. Now talking about some of the basic terminologies, let us talk about them. So tree structure in our case will look something like this. Okay, see here. So suppose I have a data set, and using that data set, I have to create something which will help me do the prediction of the values. So from that data set, we will take the name of the columns, the input columns, and taking the name of the input columns, we put it into these nodes. Okay. Now what I have done here, I have created a tree which is asking few questions, and based on those questions, we are making a prediction. So when you have done making the decision tree, your final decision tree will look something like this. The actual one will be little difficult to understand, but for simplicity, for now, you take a look that this is what it will look like basically. So what we are doing here, we have taken a data set which has these three columns, age, weight, and smoker. Now we have to find out what the risk to prevent a heart attack. So which patient has high risk of heart disease, and which patient has low risk of heart attack. We want to classify that. So we are taking an input data, and using that input data, we have created this decision tree. So we are starting with our first question, that age. What is the age of the patient? If the age of the patient is less than 18, we go in a certain direction. Age 18 to 30, we go in a certain direction. Age 30 and greater than 30. So we go in a certain direction. Now we have understood that from the training data that if the age is less than 18, then we need to talk about the weight of that patient. when the age is less than 18. If the weight is less than 60 kilogram, then that patient has a lower risk of heart attack. If the weight of a patient less than 18 years of age is more than 60 kilogram, that patient have high risk of what? Heart attack. Very similar to that, if I have any patient of age 18 to 30, from my input data, we have found out that any patient from 18 to 30, they have a low risk of heart attack. Low risk means we might not have, suppose there are 300 patients input data have. Out of that 300 patients, I have, let's say, 56 patients who are of the age 18 to 30. Out of this 56, I'm saying a final answer as low risk because maybe only out of 50 out of this 56, sorry, 50 out of this 56 are having no problem in our input data, and only 6 were found to have a problem. So majority of them were found to have no problem, low risk. So we said that the final answer is low risk. Very similar to that, when we come to our the next question, is the age greater than 30? So if the age is greater than 30, then we go to the smoker attribute, smoker column, and we check whether that patient is a smoker whose age is more than 30. If it's not a smoker, there is a low risk. If he or she is a smoker, high risk. Now, once we have created this decision tree, this is created with the input data. Okay, always remember, whenever you create the best fit line or the best fit S curve or this decision tree, all are created with the input data. Now, once we have created this input data, what we need to do, we will be using this for the prediction purpose. If there is a new patient who was having the tumor sizes this much, so we were mapping it on the S curve to get the output. In this case, what we will do, let's say I have a new patient whose age is 44, and what I can say, and he's a smoker. Yes, this patient, and weight of this patient is, let's say, 67 kilogram. Now, these are the information I have for a certain patient. For that patient, age is 44, he or she is a smoker, and weight is 67 kilogram. I'm talking about a new patient. I have to identify that whether this patient is going to have high risk or low risk of heart attack. So I come to my first decision tree node, which is my root node where my tree starts. So when I come to age, I will be checking the parameter, age parameter, age 44. So where will I go? I will go into this third direction, greater than 30. Age is greater than 30, I go here. And in this side, I don't have I don't have to check the weight of that patient. What is required? I need to check the smoker column. I need to check the smoker parameter. So is this patient smoker? Yes, this patient is a smoker. So that patient is going to have a high risk. How are we saying that? Because this is something we have understood from our training data. The input training data that I have got, we done the study of a lot of patients, and we have found out that this is the pattern being followed for the patients. So any patient who was having age of greater than 30, in this case, their weight does not matter to identify whether they have low risk or high risk. What matters more is the smoker column. So how do I know that if I have age greater than 30, I should be checking whether they are smoker or not? And why not we are checking weight here? Okay, why not we are checking weight here for more than 30? Why are we checking smoker? How do we know that? So this everything will be given by our input data, and we will try to see how. Everything has to be decided. And if you see here, I have started my tree with the age attribute. Why not I have started with the weight attribute? Why not I started with the smoker attribute? Is there a certain reason? How do we decide that? We will talk about that. So if you see anything that I have taken the age attribute here, not weight, not smoker, it has been decided by some mathematical process, by some mathematical formula. It has been decided that taking the age attribute is the best to start the root, to start the tree. Then how are we deciding that I should be checking less than 18, then 18 to 30, greater than 30? Why not? Why not less than 25? Why not 25 to 40? Why not greater than 40? Why not this? Why just less than 18, 18 to 30, and greater than 30? That also will be decided by the mathematical formula. Then here, if the age of the patient is less than 18, why did we check the weight with this? If a patient is younger than 18 years, then why are we checking the weight of that patient? Why are we not checking the smoker parameter? So that has to be also decided that with the age of less than 18, the weight parameter works very well, goes very well. So that also has to be decided. So when you're creating a decision tree, we don't randomly create a decision tree by taking anything at any place. We have to do a lot of proper calculations for doing that. I'll be explaining you those calculations. And once you have done the calculation, you will be getting a very optimal decision tree, which you can use to find your answers very properly. So I've given you just a basic idea of the decision tree. Now we will move forward to the technical details of it. Okay. If he is a smoker or not, age, no smoker, and where is I in this case. This decision tree has been made. Now, if you're taking any patient who is of age greater than 30, that patient is not a smoker and weight is higher. Let's say weight is 75 kilograms. So this decision tree says that with for that patient who is greater than 30 years old or older than 30 years, we just check the smoker, uh, you can say, attribute of that patient, whether he or she is a smoker or not. We don't check the height information. Sorry, we don't check the weight information for that patient. That is what this decision tree tells us. Why it is telling us that? Because it has studied from the past patient that if a patient is older than 30 years and he or she is a smoker, that gives us the whole information whether that patient is having low risk or high risk or not. We don't need to check the weight attribute for this patient. Not required at all. Because the answer that you're looking for, you get that using this age and smoker only. Weight you can ignore. So that is why I am saying that this is called what? See, you can create a tree in a different ways. How can you create a tree? You can create one of the trees where you can start with the smoker parameter here. And with the smoker parameter, you can check the age here. Then you can check the weight here. One can be like this also. And one is like age we are checking first, then weight we are checking, then smoker in different directions. So how do we decide that? This has to be decided, and there is only one optimal decision tree, but there can be many trees which can be created for a data. Now I'm showing you a tree which is very small because I'm just considering 3 columns. 3 columns what? 3 input columns. Now suppose I take a data set which has 70 columns. Now for a data set which has 70 columns, there can be a lot of possibilities how a tree is going to be created. Because for deciding what will be the root node, which input column will be taken at the root node, which input column will be taken here, which input column will be taken here, how will you decide? If you are trying to decide that manually, very randomly, then you are going to make a tree which will be very long and very inefficient. You will be asking random questions which will not lead to the proper results. But there is only one most efficient decision tree that you're going to make, which will be asking correct questions. And asking correct question, you read your answer very easily. So when you're making an optimal decision tree, it will be short and efficient. This is our main task. Short and efficient. Because if our tree becomes long, then what happens? Our tree will start to suffer from a problem of overfitting. Now, this decision tree is a very powerful algorithm which will give us a very high accuracy for most of the data. But if you make your decision tree very long, we'll see what is very long, what is very short, and how do we cut down the tree. These kind of things we'll be talking about. But if you make a long decision tree, then what happens is decision tree very easily suffer from a problem of overfitting, overlearning the patterns. Overlearning the pattern means it is not trying to generalize the information. It is trying to remember the input data. So when it tries to remember the input data, then it becomes a very bad decision tree. It will start to suffer from overfitting. It should learn the general pattern, not learn the input data by heart. So this is the case. Now let us go into the technical details of that, and we will understand a lot of things about it. Everyone just leave anything else that you're doing, the practical and everything. Let's try to understand these technical things in this, and you will be clear what we do in a decision tree. A lot of things are there. So what I've done, I have actually created some information for you, using which we will be creating our decision tree. Now, how is the decision tree created? Decision tree, as I told you, will be obviously created with the input data, learning the patterns from the input data. So I just told you, I've just shown you this particular tree, how it has been created. Now we are going to see the background working of that. Because this was just an overview I was trying to give you, that when you take a decision tree, when you're going to make it, this is how it will look like. And how we can use that information from the decision tree, that also I have given you the idea. But now let us see the technical details of it. The technical details are going to be like this. Now, in this case, what I have taken a example where a person has to be given a loan or not, that a bank has to decide. So, whenever you go to any financial company, banking sector, non-banking financial sectors, companies are there. So they have to give loans to a lot of customers. They have to give loan to the individual customers also, small businesses also, bigger businesses also. But to decide which person has to be given loan, which person should not be given loan, which company should be given loan, which company should not be given loan, they have to decide. Now to decide that, what they can do, they can create a decision tree. They can take the data set and train a decision tree on that, using which they can decide that this person having this thing should be given a loan or not. We're deciding two input parameters for a individual. So in the past data, what we have seen, we have some information about the past customers to whom we have given the loan. We know about the age of the customers, and we know about the annual income of those customers. You can take different information, like the education of the customer, is that customer married or not, and in the previous they have defaulted or not. A lot of things you are going to take. So what I have here is I have taken the information about the past customers and I have plotted it. Now all the red dots you see are representing a customer who has defaulted in the past. Defaulted means they were not able to pay the loan back. Okay, they took the loan, but they spent it and they took so higher loan that they were not able to pay. So the company, or this you can say this bank, lost the money. Suppose they have given a loan to small startup, and the startup took a lot of loan, but they were not able to be successful, and they had to shut down. So bank lost their money. They will not be able to recover all the money they have given to the startup. That's a risky thing, but all the financial companies do this. So the red dots represent all the customers, individual or companies who have defaulted, and the blue customers have been able to pay their loan back. Now, what we do in the case of decision tree is we have to identify the, you can say, the boundaries, which will help us decide which customer will be able to pay the loan in the future and which customer do not. So what we do here, we will split this complete data into multiple parts. That is what we do in decision tree. Split means if you take a look at this decision tree, which we were talking about, we started with a data set and we have basically split it into multiple directions, taking multiple questions into picture. Age is less than 18, age 18 to 30, age greater than 30. Then weight is less than 60, greater than 60. So we are actually taking just one single data set and we are splitting that into different subset of that data. And we are splitting that into different subset of the data. We will be able to make predictions properly. So how are these subsets being created? We are going to understand that technical details. So take a look. Now what I will do, I have to start from somewhere. And what I need to do, I need to divide this data into such a way that I will get homogeneous answers. What is homogeneous? Let us see. So suppose I start from this point. Let us say this. Now I have created a boundary. And now what you are saying with this boundary is, if you take a look at this left side of this boundary, then you have only the red dots. If you look at the right side of the boundary, you have red dots and blue dots combined. Now, what your task in the decision tree is to same data we will be splitting into different subsets, same data. So what we have done here, what we basically do in a decision tree, we are going to divide our data into different subsets, as I told you. So how do we divide that data into different subsets is something to be very clear about. So we divide our data into different subsets such that we get homogeneous answers. Homogeneous answers means I should be able to say something with proper confidence. Now, if you take a look at this thing, what I have done here, I have taken a data, and in this data, I have the information of defaulted and non-defaulted customers combined. So I want to understand specifically which customer is going to default and which customer is not going to default. I want to identify that. So what I've done, I have made a line here. Why I did make a line here? Because if you take a look at this line, on the left side of this line, I have all the red dots, and on the right side of this line, I have red dots and blue dots combined. On the left side, according to this line, I have homogeneous information. What I can say with this, in a normal statement, if I show you this graph and you have to interpret something, what will you say? So we have identified that the customers who are having annual income of less than 23K. Okay, the annual income of less than 23K, then all the customers, they have defaulted. Correct? They have defaulted. So we have a very clear information on this side and we can decide that very easily. So what we will do now, once I have just created this one boundary, I will start to make my tree. And in this tree, I will say that I have my all data, and I take my all data and I go into two different directions. One, I'm going into this direction where I take the income is what, less than 23K, and here is greater than 23K. Less than equal to I can say, and I can say greater than 23K. Now in this case, what will you get? You will get your two answers here. Okay. So one, we are going into this direction where the customer has less than 23K and greater than 23K. Take a look. I've created the first decision tree. I've started the decision tree in this case. Yes, Ajay, I have not said that I have made the complete homogeneous. I will have to do a lot of things still. I'm just coming to that. So for now, once I have to make a decision tree, I have to start somewhere, right? I started it. So let's say I started with the notion that let's make a boundary here. And with this boundary, I'm getting one homogeneous information and one non-homogeneous. This non-homogeneous part, we will be breaking it into further blocks. Don't worry. But in this case, I am actually clear on this side that the customers who are having less than 23K salary, they're actually going to default. Okay, so this patient, I can say no loan. all the sorry, if these customers who are there, I should not be giving them loan if they have salary of 23K or less than that. Clear? But on the right side of more than 23K, can I say something at this point? No, I can't say anything at this point because more than 23K people have defaulted also and not defaulted also. So the right side of this decision tree, I can't still make a proper decision about. Got it? So I have to do something more. So now what we will do, let us see. Wait, I'm adding that. We are going to add the age. So suppose here also I don't decide something. Let me keep that. I don't decide something here. I'm confused. Boundaries created. Is it imaginary or decided? Ajay, we are going to obviously decide it on some parameters. I told you, you don't decide anything randomly. I'm just saying to you that where do you start? So you actually started from this point. Why did you start from this point? Saying that because you can see easily that on one side, actually, I'm getting a confident answer. One side. Second side, I'm going to fix that. But at least one side, I'm getting a very proper answer that here the customers are all defaulting. Where the customers are defaulting, I can get an answer that easily annual income is less than this. So it is obviously going to be divided by a certain parameter. Not we are not deciding that randomly. Okay. Yes, Lakshman, no problem. Okay, no problem. Now, so we got this answer. If I have created that line, I would be creating a tree, something like this. On the left side, I can say no loan. And here we still have to decide. But that is also something you are saying that I can look at the data and I can decide. So let us go little bit bad than this. We will not try to do that thing also. Let us start from here to get you little bit more understanding. See, let me split that from the middle. We have 40, 30. Suppose I'm going to split my data from this point. Suppose here. I'm not talking that also. When I took that, you might think that I would have looked at the data. I'm trying to do some biasness in that. But let's say when I'm starting to decide my data into homogeneous part, which customer is having default or which customer is not defaulting, I start from a very basic idea, split it from the half. Now, when I did split it in the half, what I'm looking at is left side also non-homogeneous and right side also non-homogeneous. So how a tree will be created according to this? A tree will be actually created according to this in such a way. You take your complete data, all data. And now what you do with this all data, you will just go into this side and you will go into this side. What do we have here? According to this line, we have suppose 37K or 38K I can take. So if income is less than equal to 38K and if income is greater than 38K, I have made a line in such a way. Now you're splitting our data according to this and you come to a point. Now, can we decide according to this line here, which person will be given loan or which person will not be given loan? Still, we can't decide because the split that I have done here on the left side also, if you see, it is non-homogeneous. Some customers have defaulted, some customers have non-defaulted. On the right side also, if you take a look, some customers have defaulted, non-defaulted. So I'm taking this as a different example. The previous one I took, for that a different tree was created where the income I took somewhere around less than 23K. But in this case, I'm taking another example, another way of splitting the tree according to this. Now, when you look at this, you are not clear about anything. So we will have to do the split even further. Let us see. Don't worry, you will be clear about everything in few minutes. Now, what can we do to make this little bit more homogeneous? What can we do here? So can I just go according to age information also? So what I will do here, let's see this. If I take a line which I'm going to make from this point, which I create like this. Okay, one line I'm making like this. And one another line I'll be making, suppose what is something we are going to get when we have made a line here. Does it feel to be better than the previous case when I just had one single line? With this one single green line, what we were knowing, we were having actually two sides of it. On one side, there was also homogeneous information, and on the right side also non-homogeneous. So there was no clarity on both the sides. But I said that now we have the age information also. Now let's split it on the age. Now, what is this particular part? This part number one, part number two, part number three, and part number four. I've just broken my data into four different parts, four different subsets. So where we started with one bigger data set, split it into four different parts according to some different parameters. So what is happening here? How would you create a decision tree according to that? So we will just make this little further. And what we will say, for the people who have salary less than equal to 38K, let us see. People who have salary less than 38K, then what are we checking? We are checking age. Age is less than what? 29. Okay, age is less than 29. Let's see. I'm going to say age is less than equal to 29 and greater than 29. Correct? Now you see, if you take a look at just the left side of this and right side of this, the left side of this boundary which was there, I have divided that into two parts. And the right side of this boundary also I have split it into two parts. Now, what is this part number one? Part number one says that a person who has a salary of less than 38K and the age of less than 29. Is that person defaulted in the previous cases? The example data input data we have. What do we see? Are these person defaulted? Now we can see in this box, all the proper blue points are there, right? All the points are properly blue. So can we say that this box number one is properly homogeneous? I can say something very confidently that a patient who have less than 38K salary, but age of also less than 29, they have not default. That is what we have seen with the past data. So how will this convert into my tree? I'll say that age less than 29K and greater than 29K. And I will say that not defaulted. And in this case, if you take a look at the upper one, where the age is more than 29. So in this case, can you see more of the red dots? There will be one single blue dot, but it is one just customer. So I can say in total, the customers who have salary of less than 38K, but age of more than 29, they have defaulted. So can we say that? Yes, they have defaulted. Got the idea? Now we have to check for the customers who have salary of income of more than 38K annually. Let's see. So when I go on the right side, now I have to decide that. If I take a look at my box number two, what I'm seeing in my box number two is first we have salary of 38K and greater. Then what we have age of, I can say, let's say 45 we can take, okay, 45. So what we will do here, for the people who have salary of greater than 30K, I am going to split into two different parts. Less than equal to 45, what they have? They have defaulted or not? Not defaulted, right? And when we take a look at this, they have defaulted, which is greater than 45. Greater than 45. So now you can take a look at this point to get the proper idea that what has happened. Now, this is the way you're going to take a data set. This is the way you're going to make decisions, dividing your data into multiple subsets. So this is the visual part of that. And if you take a look at this visual part, what is happening to the data? This kind of thing will happen in the background. And what are you going to see at the forefront? You're going to see this tree being created in the forefront. Because what you actually need just this thing, this tree. So once we have created this tree, let's say I take a new customer. I've read my input data. I have made my decision tree. Now what I'm going to do, I'm going to use it for the prediction purpose. So for the prediction purpose, how will it look like? It will look like something as such. Let's say I have a new customer whose salary is, let's say, 47K. Okay. And age of that customer is, let's say, 35. Okay. So if I have a customer whose annual income is 47K and their age is 35K, are they going to default or not? We can make a prediction very easily according to this decision tree. So where do we start? We are actually checking the income first. So what we have here, in this box, I'm checking income. Now income less than 38K, greater than 38K, we will move into two different directions. So is my income greater than 38K or less than? Obviously greater than, so I move into the right side. I'm going to ignore the left tree. It is not for our case. So salary is greater than 38K, I go here. Then what I'm checking? I'm checking the age parameter. When I check the age parameter, is age less than 45 or equal to 45 or greater than 45? So the age of this person is 35, which is less than equal to 45. I'll come into this direction and our prediction will be not defaulted. So what is bank knowing? If this person did not default in the past, we can give this person a loan because he will not also default in the future. That is a basic prediction you're going to make. He may default in the future, may not, but according to the past data, we are studying that he has not defaulted, so we can give them the loan. Is this clear to all of you? So I'll show you another perspective of that. In this case, we started splitting first with the income parameter, then we split with the age. I'll show you one more case where we will start splitting with the age first, then with income. And we will try to see what happens, any changes are there or something like that. See, if a person is found to be defaulted in the previous case, many of the companies, they will try avoiding giving them the loan. Or there will be some companies which can give them a loan, and they will be basically asking for some extra information like is they married or they have any dependents upon them like their children, and uh, about the other information like if they have land or something which they can give it as a, you can say, collateral to the bank. They can ask few of these things. But even if they don't have any collateral to give, then what bank will do, if that person should be given a loan, they will give them a loan on a higher interest rate. Because you see, this person has defaulted in the past, so it is very risky for that bank to give this customer a loan. So whenever the bank feels it is risky to give someone the loan, they increase the interest rate to take the money out of that. Okay, that is what will happen basically. But again, what we have done to create this decision tree, we just talked about two parameters of a customer, their annual income and their age. We did not take other parameters into consideration for now, for the explanation part. You can have their educational qualification, what they're working, blue collar job or uh, self-employed. They have dependent, they have spouse. Are their spouse earning or not? Do they have any medical conditions for which they have to spend a lot of money? There are many information to be collected, and according to that, a decision tree is created. For the explanation part, so that you understand the working of decision tree very properly, we just took two parameters, so it is easy for us to get an idea about. But again, we just don't decide something based on two smaller parameters. We have to decide a lot of things. So now let us talk about this case where we have when we start splitting from the age parameter, not exactly from the income first. So tell me from where I should start splitting the age. What do you think should we start splitting from the age? See, one very basic thing you can do is just split it from the middle, not taking into consideration a lot of things. You can split it from the middle. But also what you can do in this case is you can have you can split it according to here. Suppose 30 to 40 you're saying, right? In somewhere in the middle of that. But let's see. If I say I just split it from 30 itself, then what is going to happen? Suppose this is the line I have created. Now, according to this line, which I have just now created, what will happen? I will be starting to make a decision tree. When I start to make a decision tree, what is the age parameter? We get an age parameter. No, it is not very bad. We can say that it is quite good to start with. And I say I will be taking age parameter here. See, earlier in the past tree, where did we start? We started with the income of a person. We started with the income less than 38K, greater than 38K. We moved in this direction. Then we checked the age of this person. But now I'm saying that let's not see the income of the person first. Let's see age. And we will try to see which tree is better. Starting from the age is better or from the income is better, which gives us a good information about that. So when we are starting with the age, what we have seen here is less than equal to 30 and more than 30. That is the age I'm taking. Now, when I take less than 30, I can decide something very easily because I can see a lot of blue points and lesser red points. So what I can decide, a person who was less than 30, from our input data, we have seen that they have not defaulted. Or there were just one or two customers who have defaulted, most of them not defaulted. So I can just make an answer here. But let us suppose in my data, it is not like this. It has some more of the points to make it little confusing. Let's say I have some more points which are there, just making little complicated. So in this case, I can decide still there are more blue dots and red dots. It can still decide, but let's see few further implementation of that. How can we split it further? So when I come to age of 30, what I will do now, first I will see for the people who are less than age of 30. What I will do is I will make a line again. Can I make a line from here, starting from this point? Okay, starting from this point. And now what we will have is, yes, so we have this, right? We have created this. Now, once we have made this boundary, what we will notice according to this boundary is that the people on this side are all defaulted, and on this side we have properly non-defaulted. So what I will do, the split that I have done according to age less than equal to 30 and greater than 30. What I will do with this, you can see I'm now talking about the income. Let's say 23K is the income I'm taking here. So income I'll take at this point. So we have the income. And income of what? Income I have basically two parts. Which portion I'm talking about? See, this red line that I've created, I'm just talking about below of that. The below of the red boundary, we have two different boxes. The box number 1 and the box number 2. In the box number 1, we have all the defaulted. In box number 2, we have all the non-defaulted. So salary less than equal to 23K. Less than equal to 23K, we have defaulted. And greater than 23K, we have non-defaulted. Okay, not defaulted. Similarly, if I go above now, okay, to the above section, where should I make that split? We need to get that idea. So it is going to be little difficult for us to decide. In the bottom part, it was quite easy because all the red dots were this side, all the blue dots were this side. But here it is little complicated. So what should we do here? Let's have a line here. Let's have a line here. Got it? Or I can make it little inside also. It should be little on this side. I try to shift it. See, from here, I can just do a split, which is on the two sides. Now, if you take a look at now on the upper side of this age, which is, what is this age? Greater than 30. So for greater than 30, if the income is less than this 37K, suppose. Okay. So what I'm deciding now for age greater than 30, I'm now deciding according to income. So let us say income is what? Less than 37k. Okay, less than equal to 37k defaulted. Correct? See, if the income is less than 37k, all are defaulted. But on the right side, I can't still decide something. Okay, still it is not possible for me to decide because I think equal number of red dots and equal number of blue dots are still present here. To make it little more complex, if I add few more red dots, to just make it little more complex, then now we have equal amount of red and blue dots. So what we have to do, we have to just do one more split again. What I will do here, I will make a line starting from exactly where. Can I make one more line from here itself? Here itself, I can make a line. So once I've created this line, then what are we seeing that on the upper side of this line, I can see more red dots are there, and the bottom side of this line, more blue dots are there, few red dots. It is not completely homogeneous, but still we are achieving a lot of homogeneity in this case. There are two customers who are non-defaulted, but most of the customer defaulted. Here, most of the customers have not defaulted, few default. So let us see what will happen with this. So what I'm taking, let's say age I'm taking as 42, 42 greater and lesser. For what? For salary greater than 30k and income more than 37k. Okay, now we have two things. Salary more than 37k. So here I can't decide something, so I have to make split further. Okay, what I have to do, I will not say defaulted and non-defaulted. I will just put up a age parameter once again. Correct? Age parameter once again. And once I put the age parameter once again, then what I'm doing is I am actually deciding 41 and upper and less than 42. Sorry. Less than equal to 42 and greater than 42. So less than equal to 42, what we are seeing here is non-defaulted, and what we are seeing here is defaulted, greater than 42. Now you can see here, according to the split, when we started to split according to the age parameter, then what has happened? Our tree has become smaller or longer. That is what we need to see. So we have observed here that when we started to split our tree according to the age parameter first, then our tree actually became longer than we expected. Longer than we expected. So see here, I have taken the same data set. The same data set. What I did first, in this case, I started to split with the annual income first. The first question I asked about the data is the annual income of the customers. So when I started with the annual income, you can see the tree has become this much longer. We checked the income, we checked the age, and we got the answer here. But we take a look at this tree where we started with the age parameter first. You see the tree has gone to much depth. You see, this is called layer number 1. This is called layer number 2. This is called layer number 3. And still at layer number 3, we did not stop. We have actually gone to layer number 4. So see here, we have gone an extra layer. Our tree has become little longer when we started with the age parameter. Here also we have got the answer. And in the upper case also we got the answer. So which of the tree you think is more efficient? Okay, which tree you think is the most efficient? The first one, not the second one. What I told you, you have to make a tree which is shorter and can give you the answer. As it is short, why would you make a tree which is longer and it is giving you the same answer, which is the first one giving? In first one, you are asking lesser question, and in lesser time, you can decide something, whether a person is defaulted or not. So always you have to make sure that the tree when you're making, it should be as short as possible. Because the tree as short as possible will give you answer in a lesser time, and it will also not suffer from an overfitting problem. If a tree becomes longer, it suffers from an overfitting problem. That is what we have seen. Correct? Now, So we got this. Now you can see one idea that when I started and when I decided that I will take income as my root node, I got this tree. But when I went to the next case and I decided age should be my root node, I'm making a tree which is not efficient, not short. It has become long. So how do we decide that I should take age parameter or the income parameter at the root node? How do we decide that? Then here, how do we decide that here should be income parameter, here should be age parameter again taken? How do we decide that? So in this case, I have shown this thing to you visually. And here also, there are only two things into consideration, annual income and the age of the customer. But if I take many things into account, not just two things about a customer, you will not be able to make a tree. Okay, you will not be able to make a tree. That will be very difficult. So we don't do this manually. We just have understood the working of it. If anyone asks you to explain decision tree working in interview or somewhere, you can just make this, explain them very properly. And you also understand the working of this with this example properly. Solid foundation you make. But as the previous cases, as we have seen a lot of time, that machine learning algorithm can't do this visually. They have to take a help of some mathematical formula. With that mathematical formula, they can be 100% sure that the split we are doing, the value that we are taking at root node and different nodes, that is proper and that is going to give me optimal decision tree. Correct? No, not it is not going to give us good accuracy. If you're saying that I'm just doing more investigation, I'm asking more questions, so it will give me good accuracy, not the thing. What your answer is to find out whether a person has got that default or not default. See, some of you might think that I have created the second one. So it might be more accurate because I'm creating a better tree. I'm creating a longer tree. I'm asking more questions in that. So more questions should lead to more accuracy, isn't it? But no. What we need to find out is we need to find out which customer defaulted, not defaulted. So what we are doing, we are just have to make this homogeneous boundaries, right? Where I can properly say with 100% confidence, or if not 100% confidence, with a very high confidence, I can say that this person defaulted, this person did not default. So to be confident in that, I should be just making these boundaries properly. And if I have been able to make this properly boundary here, you can see in the block number 1, block number 2, block number 3, and block number 4, we have the proper homogeneous information. We are not confused anywhere. That what should I decide here, what should I decide here, here, and here. In any case, I'm not confusing. Same is the case here also. But you see, I'm dividing into 5 blocks. So why would you want to do extra work with when you can get the same information there also? Same information you can get there. You can say with confidence in the first tree also and in the second tree also. But second tree takes more time to give you the same information, which first tree can give you in a shorter time. That why don't we use the second tree? It is asking more questions, so it should be more efficient, it should be more accurate. But no, that is not the case. That does not happen. So in total, what we have observed, see, what are we observing here? That if I take starting from this point, if I take this, okay, now is, sorry, starting from here, and we are going here, and we are going here. So if I just color all these things here, this whole part, can I say this complete part is where a person has not defaulted, where the bank can give loan very easily? Can we say that very easily? So in this case, what we have done, we have created a boundary kind of thing where we are able to decide that at this point, we have been able to make something very easily, make a prediction very easily. And that is what we have done. Same case if we talk about the first also, there will be a boundary where we are able to decide very easily. And in this case, suppose the boundary is state. What is the place here? Starting from here and going here. All this area which we have in the shaded portion, that is for non-defaulted customers. Correct. So in total, it has made this boundary. Starting from here, it has made actually this boundary, which we can take for our understanding. The boundary is like this. The boundary goes from here and here. So this is the main beauty or advantage of decision tree, you can say, that it can make such a complex boundary. If I apply logistic regression here, logistic regression is also a classification algorithm. So it will not be able to make such a kind of boundary. Logistic regression does what? If it has to make a 3D data, if it is taking a lot of input columns, it will make a boundary that will be kind of just one single line. On the left side, some data point, on the right side, some data point. Because logistic regression in total is a linear kind of algorithm. It is working in linear fashion. But you can see here, if I'm creating this linear line, it does not help me very properly. But if I'm able to make such a complex boundary, then I'm able to decide a lot of things with 100% confidence. This is the beauty of decision tree, that it can take a very complex data and make fine-tuned boundaries to help us understand where our answer lies for class 0 and where our answer lies for class 1. Correct? Now, sigmoid function, what it does, see, sigmoid function actually create an S-curve, but after creating an S-curve, when we have to visualize the decision tree, it is actually a linear boundary. You will not be able to understand for now because it is kind of a plane concept, 3D kind of concept. But this, when you have to visualize it on a larger scale of data, the logistic regression, linear regression, they both kind of create this tree, this line to you can say separate the data points. They only create a line. That is why they are called linear algorithms. They all are linear, they both. But decision tree is not very linear. It can make a very complex boundary, and that way it can become very powerful. Whatever is tried to identify, it can make a proper boundary for that. So very quickly, let us see some mathematical concept. Whatever you can understand for now. I'll explain it again in the next session also. It's a very simple calculation. Try to understand. Now, whatever I've shown you visually, I'm going to show you the same thing with this mathematics. How do we decide from what variable we should split the tree and with what value? If you see here, I have taken this, talking about the first tree that we created. I took the income parameter. This income is what? This is an input column. Okay, so if there are 70 input columns are there, suppose, so a tree will be created in such a way that there will be many of these nodes created, and we will have these inputs. So for now, talking about the terminologies, this is called the root node. Just a minute. The first place where your tree actually starts to create, this is called the root node. And after that, once you break down your tree into different directions, this is called splitting of the tree, because you're splitting the tree into different directions to create that property. If you come into left side, you again have a decision node. Decision node means you're checking age is less than this or greater than this. It is a decision node. So the first node is called a root node, and the others are called just simple decision nodes. And the last node from which you're not splitting further. From this point, you're not splitting anything further. So this node is called a leaf node, because there we have our final answer, defaulted, not defaulted, final answer. That is called leaf node. And this particular thing, you see this box here on the left side, is called a subtree. It is also a tree in itself, but a small tree. So that is called a subtree of the bigger tree. This complete thing also can be called as a one subtree. This inner thing, this can also be called as a subtree. Correct? So that is the thing. We have the tree in this case, starting from the root node. The first node that we have, the first circle that we create, that is called the root node. Then we split our tree into different directions, right? On one direction, there will be something like this. There will be a decision node. So decision node is what? You see, if you take a look at this point, this is my root node where we actually start. All the trees start from root. So this is your root node. And you see this weight and the smoker, these are called decision node because we are deciding something. Then what we have is, if I talk about this particular thing, this is called a subtree because this is also a smaller tree in itself. We have a node and we are just splitting into two different directions. It's a smaller tree. You can say that as a subtree. This is also a subtree in itself. The final boxes which are there, after which we don't split anything. From here, we are not splitting, not splitting. From here also, we are not splitting. So these places where we have the final answer, high risk, low risk, they are called leaf nodes. Leaf is the final point of a tree. So here also it is the final point of a tree. From this, there is no further split done. Okay. Now, in some cases, what we will be studying about, we will be studying about a concept called as pruning. Now, pruning is a process where you cut down some of the branches of a tree. Why would you cut down some of the branches? Because when a tree is being created, it will first create a tree with all the possible scenarios. Then when it is checking the decision tree that whether I've created the optimal one or not, it will see that some branches are unimportant for it. So if any branch is unimportant for it, it will cut down that branch and not taking into consideration that branch for the prediction purpose. Because maybe this branch is not important for that tree. I'm not saying I'm cutting this branch for now, but this pruning is a concept where you cut down a branch of the tree. You can cut any one. This one also, this one also. Any branch you cut is called a pruning process. Why we do pruning? To make our trees shorter and optimal and not wasting time on a branch which does not give me proper information. Make sense? Pruning. So these are some of the terminologies that you will hear and you need to just keep them in mind when you're talking about this. So let us see a bit of mathematics. I'm not going to depth of anything as such, just some idea. How do we find the best fit variable and the value? If I have taken a tree, I started from this. I started with the income first. Then I decided this value. Why less than and equal to 38K? Why not less than equal to 25K? Why not less than equal to 20K? Why not less than equal to 40K? Why we have taken less than equal to 38K and why we have taken greater than 38K? We have to decide that. It is not random. I've shown you visually, but machine learning can't see visually, so it will make a decision based on this. So some of the metrics that we use to find the best split are, first, something called as Gini impurity or Gini index. Second, we have entropy and information gain. Like we were using cost function for the linear regression and the best fit S curve that we created in this case of the logistic regression. Very similar to that, we have Gini impurity. Gini impurity tells that how much impurity is there in a split. And if any split has more impurity, we don't do that split. The split which has more homogeneous approach, we do that split. So what it is, this Gini impurity says, and what is entropy and information gain, they both check the impurity of a tree after splitting it. So if you are splitting a tree according to a certain parameter, and after splitting, you're getting more homogeneous approach, then you take that approach. If you're getting less homogeneous, then you don't take that approach. What I'm saying is this. So when we take this data, and in this data, I could have split according to income column and age column, both the options I have. So out of income and age column, which should I take first? Should I split according to age first and should I put according to income first, we have to decide it. So what it decides, if it is splitting according to certain income, then am I getting more homogeneous data in that case? Means let's say this is the line I have taken. I've split it according to income. So the left side of that, right side of that, what we are getting? Is it more homogeneous than splitting according to age or not? That is what we are trying to see. So whichever is more homogeneous is having less impurity, and whichever is having heterogeneous, that is having more impurity. So what is our task is to have more purity in the answers, because when we have more purity in the answers, we can make a decision very easily. So these are the two metrics which will help us identify. Now what I have written here is CART algorithm and ID3 algorithm. Just talking about decision tree. Okay, I'll not talk about mathematics, anything for now, because we are already over the time. But what happens in decision tree, there are two approaches to make decision tree. One is using the CART algorithm, and one is using the ID3 algorithm. Two algorithms are there which will help me make the decision tree. If I make the decision tree using this CART algorithm, I'll be using this metric to find the best tree. If I'm using ID3 algorithm, I'm going to use this entropy and information gain as my metric to identify the best tree. Now, what is the name of this CART? It is called classification and regression tree. This CART algorithm is famous, and whenever you are going to make a decision tree in today's time, you will be using this CART algorithm where the metric will be gene impurity. Earlier, this ID3 algorithm was used, but the problem with ID3 algorithm is that you can't make a regression tree with this ID3. You can make only classification tree. Okay. So this CART algorithm is more dynamic, much better. So we take CART algorithm. And by default, when we use the sklearn logistic decision tree function, it will be using this CART algorithm. But to convert it from CART to ID3, just one simple change we have to do. I'll talk about that also. So I'll explain you the working of this Gini impurity so that you understand the mathematics. Same way you can understand the entropy and information gain also. Okay, right. So you have to take only one. Either you use the CART algorithm or you use the ID3 algorithm. They both are very same, just with one simple change, you can change between CART and ID3. I'll tell you about that. But since CART is the very popular one, I'll explain how Gini impurity is calculated. In the PDFs that you will have, in that entropy and information gain is explained. I will explain this also with a simple example. They both are very simple. The Gini index at a node is given by this formula. We just have a very simple formula in this case. Gini index is equal to 1 minus probability of being in class 1 minus probability of being in class 0. That is the formula. Let me go through few things. If you understand better, don't, no problem. But see with a very relaxed mind. Don't put a pressure that I have to understand it. So that you just have something to practice. You're not left halfway. So what are we going to do? We are going to decide how we should make a split. According to age parameter or according to income parameter. How exactly? So I'm taking a simple example to understand that. Suppose I have 7 records. In my data set, I'm taking an input data which has 7 values, or the information of 7 customers I have the data about. Now, when I have the data about 7 customers, if I split it according to age is less than equal to 25, I get 4 records, mean 4 customers. And age greater than 25, I get 3 customers. Total 7 customers were there. When I split it according to age, 4 customers, 3 customers according to age. Now, what we have is, we have out of these 4 customers, 3 customers belong to non-defaulted and 1 customer belong to defaulted, or anything you can say. Class 0 means defaulted, non-defaulted, whatever you want, you can take that. But we are making that split and then we will do calculations. Now, what will happen in the case of an outlier if the case annual income is 10 lakh? Can we tackle it on a decision tree? See, now what will happen if you have outlier data? Can we just make something which is dynamic in the case of outlier data? Because we have seen in the case of best fit line that it was not very dynamic according to outlier. If outlier was present, your data is affected. Got it? Your data is affected. And if outliers you remove, then you will be having a balanced approach. You can make a linear regression line. Similarly, your S curve was also affected by the outlier. So is this decision tree affected by it or not? We'll try to see that. This was a very easy and a visual explanation that I've given. So I think better than this, you will not see explanations anywhere because we have visualized the whole process, the background of that. So when we visualize the whole information, we saw that how we are deciding and how we are making a tree. We did those two things together. So if you go through this video, you will be able to get 100% idea, everything with a proper confidence. So we were talking about a case where we have outlier. Suppose we have outlier, then what happens? Is my decision boundary affected? Is the working of this affected? Then what happens in this case? In this case, then what happens is, suppose let's see a customer is present here. This customer is present here. Then will it be affected or not? We are talking about this. So you tell me if this is one of the customers, because outliers will be not much. Okay, it should not be here because it will be very higher age. It will be somewhere here. Okay. Suppose it is here. What is this point representing? This point is representing a customer who is having a very higher income. All the other customers who are there, they have this much of income, but there is a customer who is earning very high. And his age is something. So we have this customer. Now what will happen to this customer? Is my decision boundary affected with that? In most of the cases, nothing will happen to your decision boundary. Most of the cases. Maybe really something affects a decision boundary, an outlier, but not like this. Got it? Because what you can do, if you take a look at this point, it also falls into this boundary. Even if you ignore this data point for now, it is not going to affect your final decision making. Okay, nothing will happen if you have not taken into consideration that point also, suppose. So then also what will happen, you would be able to decide for a customer who is having that kind of income. You can easily decide if income is, let's suppose 200K, which is very high. So income is greater than 38K, 200K, and you check the age. Whatever it is, you will be able to decide accordingly. That tree will be created. So our decision tree is very robust in the case of outliers present in the data. We can control that. How longer a tree should be created or how shorter it should be created, we can control that. And how do we know, is my model overfitting or underfitting? Because decision tree has a problem of underfitting very easily. So we can just easily identify whether it is overfitting or not. I'll show that with the code and you will be getting an idea about that. See, you just have to do the same thing. What we have done, we have imported this. Then we loaded this standard scaler, which is going to help me for scaling the data, standardizing the data. We loaded it into a scaler. And then we are using this variable to fit. Fit on what? I'm saying that what is this scalar variable? The scalar variable is nothing but this function only. I've loaded this function into a variable. So you could do directly standard scalar dot fit extract. What you are doing with this, you are actually helping the standard scalar learn the patterns of your input data so that you can scale the input data. Make sense? So when you say dot fit is what? You're saying to standard scalar that learn the scales which are there in my data. Then what you have to do, then you have to transform it. So here it is learning the scales in the data. Just a minute. Learning the scales of the data. And what it is doing here, transforming the data. Here it is, we are just doing transforming of the data. So here, once your variable, the scalar variable or the standard scalar, once it has learned the pattern, what should be the scale of the data, then according to that same pattern, it is transforming the data. Okay, it is just transforming the data. So 1 minute. So if you notice here, what are you getting? You're getting this uh, numbers. How you're getting these numbers? You take a look. So what we have done, we have just taken this age column to this thal column and we have standardized it. We have changed the scales of it. So the numbers you're seeing here, 63, 37, 41, 56, 57, they have been converted into these numbers, 0.62, 0.64, minus 0.94. Those same numbers are converted into smaller numbers like this. And we have done this for all the columns. They have all been into same numbers, same kind of numbers. So there is no column which is having higher number and no column having smaller number. So it will be easier for your machine learning to work. That is what we did. Okay, talking about this split here, what we do, the main thing is this, we have to divide our data into 4 parts: X-train, X-test, Y-test, and Y-test. If you've not seen this also, then you need to start from the machine learning first video to get this. So we divide our data into these 4 parts. Have you seen that? The processes where I drawn on a data, X-train, X-test, Y-train, and Y-test. Have seen, okay. So the same thing we are doing with this code. What we are doing, there is a train test split function. This function is present inside this module. So someone has written this function for us. This function is what? This function has some code written, which will help us do the split so that we don't have to do it manually. We don't have to decide that this row should be my training row, this row should be my test row. The code is already written. And this is the function for that. So I'm just using this function and I'm giving what? I'm giving my input data and my output data. That take my input and output data and split that into these 4 parts: X-train, X-test, Y-train, Y-test. What is this X-train? Input training data and input test data. Y-train is input training, output training data and output test data. How are we splitting that? You are splitting that according to X and Y itself. Because X and Y is your input and output data, main original data. So from that only you will be deriving these 4 subsets of the data. Then we have a test size. Test size is equal to 0.2, which means out of 100% data, you are taking 20% as the test data. This random state also I have explained. Random state does what? That if you take a training data, you take the samples every single time. Suppose if I show you, if I have my hard data, let me show you. So what is that random state? Random state can have any number. You can give it 100, you can give it 10,000, you can give it 50,000. It is just a number. What that number does, random state, is it will tell your system to select some rows according to those numbers. It is like a seed number. So suppose 20% of the test data which you are taking for it, 20% is these 5 rows. So for your system, whenever you run the code, these 5 rows should be taken all the time as the test data. That is what we decide with random state. Suppose you change the random state. You have taken random state of 100, then you change the random state from 100 to, let's say, 1. Just any number you can take. So if you have taken 1, maybe this happened that these become your test data. Because test data is 20% of your main data set. Any 20% rows can be taken to become your test data, and you decide that according to this random state value. So why we do it? If you don't give the random state value, and if you run the code on your system multiple times, you will see different accuracy results. Because different test data, different training data will be selected. There will be little changes in your training and test results. Okay. So this is kind of a seed value that take this number, according to this, select some of the rows for training and testing, that should be all the time.
I have one more announcement for you guys. For dedicated learners like yourself who want to make a difference in their career, for the first time, we at Intellipaat have decided to offer a straightforward 20% discount on our premium data science course, which is in collaboration with iHub IIT Roorkee. If you want to take control of your tech career and do something extraordinary, do visit this link in the description box given below and fill the inquiry form. Promptly, a team of course advisors will reach out to you to activate the offer. So don't miss out this opportunity.
In the decision tree, we actually split the data into different portions, into different parts. And when we split the data into multiple parts, we get our answer more properly. And how do we want the answers? We want the answers with some homogeneity, with some purity. So once we get that homogeneity and the purity, we are able to get the answers very confidently. We can say something very confidently. So that is what we were talking about. Now, if you take a look at it, this red shaded boundary that I've created, the thick red boundary. So this thick red boundary was actually telling us that on this side of it, you have blue dots confidently. On this side of it, you have blue dots confidently. On this side of it, on this side of it. Basically, we have the blue dots with pure homogeneity, you can say. There are some red dots, but it does not matter much. And on the top side of it, we have red dots here, you have red dots here. So you can say a particular decision, you can take a particular decision at this point. So what you would say about this block number 4, that a person who has age of, so in this case, we would say that a person who has age of more than 29 and the income of less than 37K or 38K, that person was found to be defaulted. In the data set that we have a lot of information about different people. So we found out that out of all the people who have age of more than 29, but they have a salary of less than $38,000 per annum. So they were found to be defaulting the most in that cases. So these dots are nothing but these are representing a person. 1%, 2%, 3%, 4%. So out of all the people who are in our data set, these many people were found to be defaulted when their age was above 29 and their salary was less than 38K. So this told us an idea that I can decide something at this point with more confidence. Similarly, for block number 3 also, there's some idea for block number 2 also, for block number 1 also. We understood this very properly, and you should have gone through the concept of theoretical part. So what I'm saying now is this boundary that I have created, this particular line. So we have created this line here, which is splitting from the middle. Then we have this point here. Then we have this point here. Sorry, not mainly talking about the lines. So one we have this green line, which we have in the middle. Then we have this line. Then we have this line. These many lines we create. So how we created that? We created that basically by looking at it. But we don't do that in actual decision tree by looking at it. The same kind of process will happen, but it will happen with a mathematics. So we're going to talk about that mathematics today. So we need to talk about how to find the best split for our decision tree. That is the most important task. What will happen if I find the best split of our decision tree? Always remember, we have to make a short and efficient decision tree. That is the main aim when you're making a decision tree. Many type of decision trees could be created, some long, some short. Okay, some very efficient, some not very efficient. So we need to just create decision tree in such a way that it is asking less questions. And by asking less questions in a shorter amount of time, it can give us the correct answer. That is what we need to do. It should be fast, it should be efficient, and it should be correct. So how do we make sure that that is happening very properly? So again, some mathematics has been created for that. And the mathematics is The metrics that we use to find out the best split are this. What best split I'm talking about? This particular thing. That why did I take here age 29 and above? Why did I take here less than 38K and greater than 38K? At this point, if you're looking at this arrow, why did we take this green line? Certainly. Why not at 50K? Why not at 20K? Because we looked at here and we found out that on the left and right side of it, it is giving us more homogeneity. Not 100% homogeneity, but if I split the data from 38K, on the left side of it, we get little more red points. On the right side of it, we get little more blue points. So some homogeneity we were able to get when we split from 38K. If we split from 20K, I won't be getting that much, or maybe 50K, that won't be very efficient for us. So we just need not think about the first one. We need to take care after the further splits also. Like if I have taken for the income, then we have to take for age also, then there will be other parameters also. So how does that happen? Okay, that happens with this particular concept. There are two concepts, which means that there are two algorithms actually. And those two algorithms are, one is called an CART algorithm, second is called an ID3 algorithm. Using these two algorithms, we implement our decision tree. Okay, like we have seen the loss cost function in that case, S curve, the best fit curve. Very similar to that. The metrics that we have that takes care that we are making a very efficient decision tree is the Gini impurity and entropy and information gain. So out of these two algorithms, the CAT algorithm is something you will be using most of the time, as it is more dynamic and it is more better. So CART is the short form for classification and regression tree. So this CART algorithm can make classification tree also and regression tree also, which means that it can be applied for classification task also, data also, and regression data also. So it has the Gini impurity as the metric, and ID3 algorithm. If you want to use, you change the that metric to entropy and information gain. I'll tell you where do you change these things. Just one simple thing you have to change, and you can switch between CART algorithm and ID3 algorithm with one simple switch. We'll talk about that. So in this case, since CART algorithm is a very famous one, we will be talking about that here. We will be talking about this Gini impurity. So what is the case with this Gini impurity is that it will help us decide that at root node, what we should take. Like if we have, let's say we are talking about a heart disease patient, suppose. So if you're talking about heart disease patient, what is all the things we can ask? How can we make a decision tree? So we can make a decision tree in multiple ways. Okay. So in the multiple ways, what I'm talking about is, let's say we can ask the age of the patient, or we can ask the cholesterol level. We can ask their chest pain. We can ask their gender. Multiple things are there where we can start asking the question. So out of these, what is the first best question to ask? Is it the age? Is it the cholesterol level? Is it the chest pain? Is it the gender? So what I'm saying is, when you start making the decision tree, at any certain point, if you have to make this root node, or if you have to make this decision node, you have to see that which question, which parameter out of these is going to give me the most answer, a better answer, a more homogeneous answer. So let us say I ask on the basis of gender first, suppose. Okay, I ask the first question based on gender out of these four. So when I ask the question about the gender, what I'm trying to solve, I'm trying to solve a question of heart disease. Okay, suppose we are making a heart disease prediction. Which patient is going to have heart disease, which patient is not going to have heart disease. So this age, cholesterol, chest pain, gender, these are all input columns. In the data set, input columns are given. So I have told you that you take the input columns and you make root node, decision node, lots of things. So suppose I take a question. How do we decide? Should I take cholesterol at the root node, or should I take age at the root node, or should I take chest pain at the root node, or gender? How do I decide that? So visually, I've shown you that you will make that line splitting right side, left side. But here, what happens is mathematically, let's suppose you have taken gender. When you have taken gender in your data set, what you found out was 50% male are there who are having heart disease and 50% female. Okay, yes, 50% male and 50% female. So when you take a look at this gender parameter, the answer it is giving is very problematic. Can you say anything when it gives you answer in 50-50% ratio? It becomes very difficult, right? It becomes very difficult because there is an equal chance of male patient having heart disease and equal chance of female patient having heart disease in our data set when we are talking about gender. So when you get the ratio split into 50% and 50%, then this is called the most impure answer you can get, most impure. Okay, so it is as non-homogeneous as it can become. So we should be going away from this 50-50%. So gender, we got this. And when we get this 50-50 split, the Gini impurity value will be very high. Okay, very high. No, that is not 50-50% that you're thinking. 50-50 is not in two boundaries. 50-50 means that on this side also you have 50% blue dots and 50% red dots combined. So if 4 blue dots are there, 4 red dots are there here also. And 50% in this case means that you have 4 dots here also, 4 dots here also. Can you make any decision at this point? We have equal number of blue dots and we have equal number of red dots on both the cases. So I won't be able to say anything. Has the person defaulted? Has the person not defaulted? I won't be able to say anything. So this 50-50% split is the most difficult one for decision tree to decide anything. It is called most impure. Because if I, let's say, reduce this, now it becomes little easy for us. In this case, since we have more red points and less blue dots, I can lean towards the red answer that I can say on this side of the boundary, people are more defaulting. Makes sense? So in this case, we have to achieve such a split. We have to split from such a place that we get more of the blue dots and or more of the red dots. We should be achieving that. So let us suppose now with gender, we got this problem that we were getting 50-50 ratio of both the answers on both sides of this split. So when I take cholesterol, in cholesterol, what happens? We got the patients in, let's say, 70-30 ratio. That when the cholesterol level is, let's say, greater than 300, what we have talked about, we have to pick a parameter, and also for that parameter, we have to pick a value, like greater than 300, less than 200, what will be that value? So let's say when I have taken cholesterol here, not the age, let's say I take cholesterol. What is the cholesterol level of the patient? So when I studied the cholesterol level of the patient, I found out that the patient who have more than 300 cholesterol, in that case, there were, let's say out of 10 patients, there were 7 patients having heart disease and there were 3 patients having non-heart disease. So is this more homogeneous in this case? Because when I took the gender part, in the gender part, what we found out that out of 10 patients, 5 were found to be having heart disease, 5 were found to be having non-heart disease. So it became very difficult. But when you split according to cholesterol, can you say something with little more confidence? Yes, you can say. Because we have, yes, comparatively, yes. So that is always comparatively. So we have 7 patients of heart disease and 3 patients of non-heart disease. Since we have 7 patients of heart disease, we will say with a more confidence that the person having greater than 300 cholesterol is going to have heart disease, because that is the case with most of the patients in the previous cases. Similarly, if I have less than 300, then it is found out that we have more patients of non-heart disease now, and we have 3 patients of heart disease. So we are doing that split, and what we have to find out is, whenever we split something, whenever we take the root node or any decision node also we take, we should get more homogeneity in our answers. As much as possible, we should be achieving. When we split something and we get the answer as 5 of one class and 5 of another class, this is the most impure split, we can say. Most impure. Because 5 and 5, I can't say anything at all. But I have 6, 4, 7, 3. If 70-30 ratio is there, I can say that 70% part is little more obviously going to happen. So that is all decided according to a concept of Gini impurity. So let us see the mathematics. Leave everything and try to understand this mathematics for now. So there is a formula. The formula of Gini index says that when I say Gini index, it is just Gini impurity. The higher the Gini impurity, uh, the more difficult it becomes for us to make a decision. So what we will be doing, if let's say I have 10 input columns. So out of these 10 input columns, we have to decide which input column will become my root node at the start. Which out of 10? Because I can take any one of them, but all of them are not going to give me the best answer. So out of these 10 input columns, I have to pick the one which is going to be more homogeneous, which is going to make a more homogeneous split of the data. So how do we decide that? What we will do is we will take all the input columns and we will make multiple decision trees. And after making multiple decision trees, what we will do, basically, we will put them first at the root node. The first input column, second input column, third input column, fourth input column, all of them, we will put them at the root node and we will see how homogeneous they are. So whichever root node is giving me more homogeneous answer, I'll take that. That is going to be my answer. So how do we find out which is giving me more homogeneous? So that is given by this Gini impurity or Gini index. And the formula for this is 1 minus probability of being in class 1 square and probability of being in class 0 square. Let us understand that with an example. How that formula works. So I'm taking a very small example in this case. I have, let's say, 7 records, 7 rows in the data set. And when I take these 7 rows in the data set, I have to make a decision tree out of that. So in that case, I have 2 input columns. One is the age column, and one I have this income column. 2 income input columns are there. So should I split according to age parameter first, or should I split according to income parameter first? What should be my root node? Should that be income or should that be age? We have to decide that. So yes, let's see. We have not decided it yet, but let us see what is happening. You can't decide that directly. It may seem that it is easy for you to decide, but it should be gone through a formula. So suppose I have the 7 records. I have some data about 7 persons who have taken loan in the past. Who defaulted, who not defaulted, we need to see. So when we start here, we take the age parameter first at the root node. Age parameter. So we have on the left side, we are splitting according to age less than 25 and age more than 25. When we go less than equal to 25, we find out there are 4 people whose age is less than 25 out of 7 people. Now, in this 4 people whose age is less than 25, 3 people have not defaulted, 1 people have defaulted. Class 0 means not defaulted, and class 1 is defaulted. When I go through the age on the right side, let's say greater than 25. So there are three people on age greater than 25 out of seven people. Out of these three people, not defaulted one and defaulted two. Okay. So here you can see we have not defaulted three, defaulted one, which means that there are, let's say, three red dots here and one blue dot. Got it? Sorry. Not defaulted, right? Not defaulted, we were representing with the blue dots. So there are three blue dots and there is one red dot when we are splitting according to that. What we have here, we have 1 and 2. 2 is defaulted and 1 we have not defaulted. So this is the split now. Now I can say something, but we don't say something at this point by just looking at the data. We take it through the formula. So the parent node is being split at the age less than 25. To calculate the Gini index of the split, we need to calculate the index of each of the child node and then calculate their weighted sum. Let us see, it's a very simple thing. So what we need to find out, we have a formula. This formula says that 1 minus probability of being in class 1 square, probability of being in class 0 square. So what we are doing now, we have to find out Gini impurity of the left tree, of this tree first. Sorry, this direction first, this node, and then we have to find out separate of this. So we will get two Gini impurities, then we will combine to get a total Gini impurity of this split. So let us see first in the left child node. The probability of record being in class 1 is 1 upon 1 plus 3, 0.25. The probability of record being in class 0, 3 upon 1 plus 3. See, what we have here is class 0, 3 means non-defaulted 3, defaulted 1. 3 and 1. So that is what we are saying. The probability of record being in class 1 defaulted is 1 upon 1 plus 3. 1 out of all the data points. 0.25, 3 upon 1 plus 3 is 0.75. It's a very simple calculation. Once I've got these two answers, 0.25 and 0.75, we put it into our equation. 1 minus probability of being in class 1 square minus probability of being in class 0 square. Just put that into formula. We get 0.375. That is the impurity of the left child, the left side of that tree. Okay. So we get this answer 0.375. That is the answer. Now just not let the left child we have to see see the right child of also. In the right child, we have probability of class 1 and we have probability of class 0 again. See, right side. So we have these 1 and 2, class 0, 1 and class 1, 2. So when you take a look at this right child, class 1 is 2. So 2 upon 1 plus 2 is 0.67. And then the class 0 probability will be what? Just the 1 minus of this probability will get being in class no. So that is the answer. Okay, what is 1 plus 3? Total number. Simple. This is, see, how many out of these 4 people, how many are them total? So see, if I have to find out the probability of class 0, what I will say, 3 upon total people, 3 upon 1 plus 3. Okay, if I have to say probability of class 1, I'll say 1 upon 1 plus 3, right? This is the simple probability. That out of 4 people, we have in class 1 3 people. So this is the probability and this is the probability of this. Then for the right child, we are doing the same. We have 1 minus 0.67 and 0.33. See, you don't have to remember this answer for now. I'm just explaining it to you so that when you see this after the session, you can understand it. Don't need to remember. Just try to understand every step. Are you able to get it or not? Once you see the this page after the session, you can see, understand. So we have 1 minus probability of data falling in class 1, that is 0.67, as you can see here. And we have 0.33 probability of class 0. So when we take it, we get 0.442. So now we have got the Gini impurity of left child and the right child. What we do, we have to combine them together. This left child gave us the total impurity of 0.375 and right child gave us the impurity of 0.442. So we combine them together, and not just combine them directly, we have to take the weighted sum of both the child. So you see what are we doing? We started with this tree. And I'm saying that we have a left side of the tree and we have the right side of the tree. For the left side of the tree, we will be finding out some Gini impurity. And for the right side of the tree also, we'll be finding out some Gini impurity. So we get this answer, right? We get two answers, one for the left, which is this one, and one for the right, which is this one. Once we get this, then what we will have to do? I have just taken minus. So for class 0, what I've done, 1 minus, if I do this probability, I get automatically for the other probability. Simple, I've done minus. You could do 1 upon 1 plus 2, you can do that. 1 upon 1 plus 2, you will get 0.33, that same thing. But I have get these two answers, what I do now? Okay, what I can do now? So we have to take this whole thing. We have to add up the left part of the tree with the right part of the tree. The total impurity I've got, I have to add it up. But we don't add it up directly. We have to multiply with the weight of the left node and the weight of the right node. So what is the weight of the left node and what is the weight of the right node? So we multiply the Gini impurity of the left node with the weight of the left node and the Gini impurity of the right node with the weight of the right node. Then we add them together. What is this weight? This weight is nothing but, you see, what do we have on the left side? There are total 7 records. So if the complete data has 7 records, how much weightage we have on the right side? So there are total 4 data points according to age less than 25. Means there are 4 patients. So it means that on the left side of it, there are 4 by 7. This is the weightage of the left, you can say, split. What is the weight of the right split? It is 3 upon 7, because when you take a look at age greater than 25, there are 3 data points, 3 records according to that on the right side. So the weight of right side is 3 by 7 and the weight of left side is 4 by 7. That is the weight. Simple. It will be decided by the decision tree. You don't have to see that exactly. Whenever you are going to explain it in the interviews, you can take the same example, that suppose my decision tree has taken the age parameter and it has split according to age less than 25, greater than 25. How do we understand that this is good split or not? You don't exactly know where it is doing, but this is an assumption we are taking to understand how that calculation happens. No one is going to ask you what is the exact number. You can't find that out. When the tree is created, that tells you that what was the actual split. But whenever you explain in the interviews, you take this kind of assumption that if I have to explain that should age be my root node or should income be my root node, we do this kind of calculation. So I have taken the 4 by 7 as the weight of the left node and 3 by 7 as the weight of the right node. So this weight of the left node, I will multiply this with the impurity of the left node. This weight of the right node, I'll multiply with the impurity of the right. What is the impurity of left node and right node? The impurity of the left node is this 0.375 and of the right node is 0.442. Once I do that, what will I get? 4 by 7 into 0.375, 3 by 7 into 0.442. And this is the final answer I get, which is the total impurity that I'm getting when I split according to the age parameter. When I take the age input column and when I made it as my root node, I get a number which is this number. Now, what is this number? This is telling me the total impurity in the decision when you split according to age column. Now, what is this? Is this a good number? Is this a bad number? So to decide that, you can't decide it manually, whether this is a good number or not. So what happens? You have to make secondary, where you will take another input column as the root node, and you will do the same calculation and you will reach to this point. Okay. You will reach to this number and you have to compare the number for both the trees. One where the root node is age and one where the root node is income. You will compare them. Whichever has the lesser in this total Gini, this total impurity, whichever has less, that becomes my root node. So let's see. So this total Gini, how we have found out? This is the total impurity for the left side of the tree and for the right side of the tree combined together. This is not for each side. This is combined together. I have combined left and right together. If you talk about just left, so this is that number, 0.375. When you talk about just the right side of the tree, we have 0.442. So now what we are talking about, this complete tree we are talking about, left also, right also combined together. So don't get confused about it. Collective error, right? So when we have this collective, not error, it is collective impurity. Don't use the word error here. It is always impurity. So what is this number? We will talk about this, but I have got this number 0.405. Let's see. So this is the total impurity I've got when I split with the age column. Now what we are going to do, we are going to do another split. We are going to make another decision tree where also same data set I'm taking, same 7 people. But I'm now splitting according to income is less than $25,000 and income greater than $25,000. When I split according to income, what I'm looking at is the people who have income less than $25,000. You can see class 0, you can take anything, non-defaulted, defaulted, anything. Just understand that there is, suppose I take class 0 as non-defaulted. Okay. Or so there are 3 people non-defaulted whose income is less than $25,000. Whose income is greater than $25,000, 1 non-defaulted and 3 defaulted. So we have total 4 people in our data set whose income is greater than 25,000. 4 people. Out of these 4 people, 1 not defaulted, 3 have defaulted on their loans in the past. Defaulted means they were not able to pay back. So what is the parameter here? We have taken income as the as this root node, income. So when I took income, I split again and I do this. Once I did this split, what I need to do, I need to find out impurity for the left node and impurity for the right side of that tree. So I'm doing a very quick calculation here. Okay. Why are what we have here is Gini impurity of the left node. Same calculation, 1 minus probability of being in class 1. Probability of being in class 1 minus probability of being in class 0. You can put that anything first. It is both negative. So you see GI of left node, 1 minus probability of being in class 0 or 1. Probability of class is 1. So I think I have taken here class 0 first and then class 1 later. Here I have taken class 0 first and I have taken class 1 later. So what is this? The split when I have is 0. Of the left side, I'm total getting the impurity as 0. And on the right side, I'm getting a total impurity of 0.375. Now, what is this 0 telling me? When I get the Gini impurity of 0, what does this mean? I'm not deciding anything that income is better yet. What I'm saying is, when I split according to income column, you see, I get class 0 as 3, class 1 as 0. So do I get pure homogeneity here, or a complete purity I can say I'm getting here? That I can say with 100% confidence that the person who have income less than $25,000, all of them non-defaulted. 100% data is belonging to class 1. So when you split something and you get 100% in one class and 0% in another class, there the impurity will become zero, telling you that you have 100% confidence to take a decision at this point. That is for the left side of the child. When I am splitting according to income column, see, the formula is very simple. 1 minus probability of class 0, probability of class 1. How am I making the probability of class 0 or 1? See, if I'm talking about this, probability of class 0 first, what it will be? 3 upon 3 plus 0 of class 0. What is the probability of class 1? It is 0 upon 0 plus 3. Simple. No different calculations. Very simple, straightforward calculation. I've just split it. I got the answer that class 0 has 3 people, class 1 has 0 people. I put that into my formula and I get a number. That is the Gini impurity for the left tree and the right tree. So once I've got the Gini impurity for left and right tree, what we have to do? We have to take the weighted sum. Weighted sum means, see, if the impurity of this side is 0, what I multiply with it? The weight of the left child. The weight of left child is 3 upon 7. Okay, we have 3 records on the left side out of total 7 records. Here, what will be the total weightage? 4 upon 7. Because on the right side, we have total 4 records out of 7 records. So we have the weight of 4 upon 7 on the right side. Got it? Now, so once we have this answer, we have to just do this multiplication. Weighted sum into the left of the decision tree and the weight of right tree into the impurity of the right tree. And we get this answer 0.214. See, I've taken just the same formula which I took above with different examples. And I get this 0.214 as the final total impurity. This total Gini impurity is for when I'm taking income as my root node. So now, what we have to do, we have to compare this number with the above number. Which number? This 0.405 which we got. So this 0.405 is the total data. See, don't, I'm going to answer your further questions. Try to understand this first. Otherwise, you'll say you did not understand anything. When we have this two of them, I split according to the age column. I got this total Gini impurity, 0.405. When I split according to the income column, when I took the income as my root node, I got this as total impurity. Which one is better in this case? Whichever split has lesser Gini impurity. Okay, whichever split has lesser Gini impurity, that becomes our answer. The final answer that out of age and income, I should be taking income as my root node. Okay, I get to decide that income is my root node. Are you all getting this idea? You have understood this calculation, right? It's a very simple calculation. Gini impurity of the left node, Gini impurity of the right node, and total Gini impurity. Easy. Just these three things, nothing more than that. What you have to do, you just have to compare the Gini impurity of this. Now, what I'm saying is, suppose there are 10 input columns. Okay. Suppose there are 10 input columns. What you will do, you will make different decision trees. First time taking the column 1 as your root node. Second time you will take column 2 as root node, you will make a different tree. You will take column 3 as root node, you will make a different decision tree. And once you're taking these root node and then you're making decision trees, you are going to check, is this giving me total Gini impurity less, or is this one total less, or is this one total less? So out of 10 trees that you're going to make, whichever has the least Gini impurity, you are going to say that that will be my tree for the starting point. So column 1 has to be taken as root node, column 2 has to be taken as root node, column 3 has to be taken as root node. You can't decide that from your side. So you will be making 10 trees and you're going to compare their total gene impurities. Whichever has least gene impurity out of them, so that becomes our final answer. Simple calculation, very simple calculation. It will do this for every column, every parameter. And whatever input columns are there, it is going to do the same thing, all the input columns. Whatever it can do, once it has done all the calculation, it is just going to compare whichever has the least gene impurity. That is the final answer. Now, so the thing here is that the gene impurity, which is we are talking about, gene impurity value ranges from 0 to 0.5. The gene impurity value ranges from 0 to 0.5. That is the range of the values. Now, when we are getting closer to 0, that means we have less impurity. Less impurity means more homogeneity. When we are getting closer to 0.5, it means that there is more heterogeneity, more impurity. When we are getting closer to 0.5 value of gene index or gene impurity. So when we will get 0.5, let's say I split according to suppose eight records are there. And I split according to, let's say, age is less than 30 or age is less than 30, suppose. When I split that, I got 4 belonging to class 0 and 4 belonging to class 1. When I get this kind of answer, you can do the calculation. You will get the gene impurity of 0.5. The gene impurity of 0.5 tells us that this is the maximum impurity we can get. Why this is considered to be maximum impurity? Because we can't say anything at all with a certain decision. If it was like 5 belong to class 0, 5 people, and 3 people belonging to class 1, then I'm at least leaning little bit towards this, that our answer is more of the class 0 and less of the class 1, because more people have not defaulted, and less people have defaulted. So I can say, in general, the people who have age less than 30, they don't default in general, with little bit of confidence comparatively, not 100% confident. That is the thing. But can I say here, yes, when I have 50-50% ratio in both the classes at a split, it will give always the gene impurity of 0.5. That is the maximum. What your task is, you have to get close to 0 gene impurity. Your decision tree's task is to get a impurity closer to 0. The more closer to 0.5 it is, the worse it is going to become. So it tries to make a split where it is getting a very less impurity, and very less impurity makes that decides that you are making a very efficient decision tree automatically. This was the whole calculation. There's nothing more than that. Now you would ask that what we have done, we just don't have the root node. See, again, a lot of people are running away by just seeing this simple calculation. See, if you run away, you will not learn anything at all. So till how long will you run? This mathematics is not going to go away at all in this machine learning. So either you leave machine learning totally or you stick with it. It will be difficult at the start, but you will be doing it 100%. Should not run away at all. So now the idea here is that I just don't have the root node. I have decision nodes here also, decision node here also. Till now, whatever calculation I have told you is deciding the root node. Because what is our first task? Our first task is to decide the root node so that at least the tree starts making itself. Once I've decided the root node, that age should be my root node or the income should be my root node or anything else, once I decide that, then there will be this decision node. There will be this decision node, and then there is a decision node. For these nodes also, the same calculation of gene impurity is going to happen. Same type, same formula. What you have to do now? So with age here, we have taken income of less than 23K, greater than 23K. And for age greater than 30, we have taken income of less than 37K, greater than 37K. How have we decided that? So again, that calculation of Gini impurity is going to happen very same way. But you don't have to understand the further calculation, not required. Whenever you are going to explain these things in the interview, if you explain this concept of Gini impurity till this much, this is more than enough. Okay, this is more than enough that I have explained you. You can just say that the further calculations will be taken or will be done according to the same formula, according to the same concept. No one asks you more than that. Okay, so just understand this much mathematics. This much mathematics is also not simple. You have to remember this. But once you remember this, this is enough. But our decision tree is just an algorithm. It can't see anything visually. So it has to take help of a mathematics to decide where it should split, where it should make that boundary. So how it has decided that it should make the boundary of this income less than 38K and greater than 38K. Why exactly this I have made? So I can see this, but my machine can't see this. So for the machine to decide this, for the algorithm to decide that particular line, it has to take the help of a formula, which I have taken the Gini impurity formula. So what we did a simple calculation. The formula is this: 1 minus probability of being in class 1 minus probability of being in class 0. Just take this simple example. Anywhere you have to explain, take this example, explain it. That will be more than enough. And at the last, what you have to do, the total Gini impurity that you get for one split, that you have to compare for the total Gini impurity of the second type of split. If you have taken age as the root node, you will get a Gini impurity total. If you have taken income as the root node, you will get a Gini impurity. Compare them. Whichever is less, that becomes your root node, the final answer. We have talked about this. And once we are able to do this, what will happen? Why are we focusing so much on the Gini impurity? Because once we are able to optimize this Gini impurity part, then our decision tree will become most efficient automatically. Okay, by taking the nodes which are having less impurity, what will happen? You will automatically make a very good decision tree, which is shorter also, which is efficient also, and which is accurate also.
I have one more announcement for you guys. For dedicated learners like yourself who want to make a difference in their career, for the first time, we at Intellipaat have decided to offer a straightforward 20% discount on our premium data science course, which is in collaboration with iHub IIT Roorkee. If you want to take control of your tech career and do something extraordinary, do visit this link in the description box given below and fill the inquiry form. Promptly, a team of course advisors will reach out to you to activate the offer. So don't miss out this opportunity.
A chatbot is a computer program designed to simulate conversation with human users, often using NLP and artificial intelligence techniques to provide information or perform tasks. Hello everyone, in this video we are going to develop an Intellipaat EdTech chatbot using the Llama 2, which is an open source large language model. Now, before going deep dive into this project, first we will see the agenda. So now coming to the agenda, first we will see what is introduction to generative AI. After knowing what is generative AI, we will move forward to what are large language models. Moving ahead, we will see the use cases of LLM. And after that, at last, we will see the hands-on implementation of the project. So now, let's start with our first topic, that is introduction to generative AI. Generative artificial intelligence refers to AI models and systems that use algorithms to produce new content such as text, images, music, and more that closely resemble human-generated content. Now, these AI systems hold promise in diverse applications, from creative content generation to enhancing problem-solving abilities. So this is the basic idea about generative AI. After understanding generative AI, now let's see what are large language models. Large language models, or LLM, are a type of generative AI that are particularly skilled at generating clear and contextually relevant text based on the input they receive. There are multiple large language models developed. For example, you can include the GPT-3, GPT-4 from OpenAI, Llama from Meta, and Palm 2 from Google. These are the models that can understand language and can generate text. So this is the basic idea about LLM. Now, after understanding what is generative AI and LLM, we will see the use case of LLM. So the first use case of LLM is text generation. Text generation creates the human-like written content by using AI. The second use case that we will see is language translation. Using LLM, we can automatically translate text between languages. The next use case is sentiment analysis. Using sentiment analysis, we can analyze and determine the emotional tone of the text. Next, we are having text summarization. Condensing lengthy text into concise summaries is known as text summarization. And last, we'll see the chatbots, which are AI-driven virtual assistants for natural language interactions. And in this video also, we will see that how we can create a chatbot using Llama, right? So now guys, let's see the structure of the project, that how we gonna make a chatbot. So for this project, we are going to take a quantized model from the Hugging Face to build the chatbot. So if you write here Hugging Face, let me write here. And if I am writing here Llama, so you can see that I am getting a lot of results, right? Let me take any model. Let me click on this. Okay. And here you can see that we are having a lot of quantized model. If you go on the files and versions, you can see that these all are the quantized model. So for making a chatbot, we need to have a quantized model. So for that, I am downloading this llama 2 7bchat.ggmlv3.q8, right? So let me download it. You can just click on this and the download has already been started. So once the download has been completed, the next step is having the data. So now this is the data folder in which I am having the document that I have taken is the Intellipaat course brochure, which contains several courses. Let me show you. So these are the document in the form of PDF, right? So in this brochure, you can see that what is all about the program, what are the key highlights, right? How we can apply for this course, what are the application process for it, and many more, right? So this is the course for data science and artificial intelligence. Similarly, if you see here, I am having several other PDF for different courses, right? Now, my next step is, now once we are already having our quantized model and document, the next step is embedding. So our next step is the embedding. So whatever the data we are having, we have to embed out of it, right? With the help of an open source embedding model. Then I will fit into a larger model with the help of a framework known as LangChain. So using LangChain, we will retrieve the information from it. So this is the basic idea. Now let's see the implementation of it. So for that, I will be using a VS Code, that is Virtual Studio. So guys, this is a Virtual Studio. Now what I will do, I'll just go simply on File. I'll click on this Open Folder. And I will click on Intellipaat Chatbot. So you can see that Intellipaat Chatbot has been opened, right? And in this, I'm having one folder, that is data, right? I've already showed you the Intellipaat brochure. So now I'll just go on this folder once again on Intellipaat Chatbot. I'll click here and let me give the file name as code file. I'll just write here code.py, right? And it's time for coding. So the first library that I will be writing here is the LangChain library, right? So there are some required modules and classes that is provided by LangChain library in order to create a good chatbot. So I'll just write here from LangChain dot embeddings import Hugging Face embeddings. Let me execute this, and you can see that we have successfully imported this module. After this, we are having from langchain.vector stores import fast. But before that, let me explain you about that we are using here Hugging Face embedding, which are used for embedding purpose, and these are utilized by pre-trained models from Hugging Face transformer library. Let me write another module here from langchain dot vector stores import fas. Now, talking about this fas library, it is used for vector storage and similarity search. Fas is known for its efficient handling of high dimensional vectors. Next we are having again the same langchain module, so I'll just write here langchain.document underscore loaders import PyPDF loader and directory loader. So PyPDF loader is used to load the PDF files, whereas the directory loader is used to load the text documents from the directory, right? So these are the modules. Now moving ahead, we are having once again the same module from longchain.text underscore splitter. I'll just write here simply import recursive character text splitter. Don't worry guys, I will explain you what does it mean. So recursive character text splitter, this module is used for text splitting. It will break the longer documents into smaller text units, right? So let me just execute all these things. I'll just go to my PowerShell. I'll just write here Python code.py and let me execute this, right? And you can see that it has been executed. Okay guys, so these are the basic libraries that we'll be using. Now, okay, I have to write here langchain. Let me save it, and I'll just once again to run this file, I'll just write simply Python code.py. Okay, yeah, successfully executed. Now after this thing, we have to give the path, right? Which path? This folder path. So I'll just simply write here a variable name data path. And I will give you the path of this folder. So I'll just write here data and backslash. So now this data path folder will hold the path to a directory where data files are stored, right? Data files are stored here in this folder, all 5 brochures. And the second column that I'm gonna make is db fas once again path. Now what do you mean by this? So db fas path holds the path to a directory where the code may save or load some vector database. For example, using fas, a library for efficient similarity search on large dataset. So now what I will do here, I will write here vector store and then db underscore fas. Okay, let me save it and let me once again run it. I mean guys, you don't have to run every time. I'm just running it to show you. Okay, so from now onwards we'll just complete the code and we will see the output at last. Now after importing the modules and giving the directories path, the most important thing is to create a vector database. So I'll just write here, let me write down in comments, create vector database. Now to create vector database, I'll just create a function. I'll just write here def create underscore vector underscore database underscore, we can write Intellipaat, but it will be a long name, so let me write up to here, right? So now here I have just created a function which name is create vector db, right? And it is responsible for creating a vector database using the langchain library. So I'll just write here directory loader. Here you can see that we have already imported the directory loader, which was a class. Now here we are creating an instance, and in this instance what I will do here, let me just write, I will provide the path, that is data path. I'll just write here. So guys, let me explain you what I have done here. Here, a directory loader is created to load the documents from a specified directory, that is data path, right? After that, we are configuring to the PDF file. That's why we are here writing here global, and this is a syntax to load PDF files. And then we are using here PyPDF loader as a document loader class, which is likely used to extract text from the PDF documents. Okay guys, now after creating this, let me assign into the variable. So I'll just write here loader. Okay. Now, next step, what I will do here, I'll just load it. I'll just simply write here loader.load. So I'll just call this method to load the documents from the specified directory. So this line populates the documents variable with the loaded documents. So I'll just simply write here documents. Let me save it. After that, what I will do here, I will use here recursive character text splitter. Let me use it. Recursive character text splitter. And here I will give chunk size 500 and chunk overlap is equal to 50. Now what does it mean? So we are using recursive character text splitter to split the text, right? When I am giving here the parameter chunk size, it means the size of text chunks is to split the document into 500 characters. Similarly, for the chunk overlap, the overlap between the consecutive text chunks, that is 50 characters, right? This overlap allows for context continuity while splitting. Okay. After having this, let me assign it again into the variables. So I'll just write here text underscore splitter. Okay guys. Now let's see the further steps. Then I will write here text underscore split splitter dot split underscore documents. And inside this, I'll just write here documents. So now I have written here documents inside this function, right? Text underscore splitter dot split underscore documents. It means the split underscore documents method of the text splitter is called to split the loaded documents into smaller text chunks based on the specified parameters, and the resulting text chunks are stored in the text variable. Now we have already having our module Hugging Face embeddings, right? So it's time to use it. So I'll just write here Hugging Face embeddings. Okay. And inside this, I'll give my model name. Right. The model I told you to download, right? And the quantized model. Okay. So let me write here the quantized model. So if you see this folder, I'm just having only data, right? But I should have the quantized model. So let me put it. Now guys, I've already put that quantized model here, right? Now, as I told you that we have to put the quantized model, right, in the code, but not in this code, right? Hugging Face embeddings. Here, we will be implementing the model name as sentence transformer, right? So what we'll be doing here, let me first show you the code. I'll just simply write here sentence underscore transformers all meaning LM, and I will be using L6v2. Okay guys, and then I will write one other parameter. So guys, let's understand what I'm doing here. I am just creating an instance of Hugging Face embedding, right? which is using a pre-trained model from Hugging Face Transformer library that is known as the Sentence Transformers or Mini LM-L6 V2. Right, so this is the model name here we are using, and then we are configuring this model to run on the CPU. So that's why we have written here device as CPU, right? So now after understanding this, let's move to the next step. Now I'll be using here faz. I'll just write here faz dot from underscore documents, and inside this I will just give the parameter that is text and embeddings. Now you might have a question that why I have written here text and embeddings, because I'll just keep this as a variable name as text, and this will be the embeddings one. Embeddings. Okay guys? So now when I'm writing here faz.from underscore documents, it means that we have created a vector database using the LangChain faz class, right? Faz class. The database is constructed from the text, or I will say the text chunks and the embeddings. So the embeddings means here the numerical representation of the text. So this step likely involves creating high dimensional vectors for each text chunk using the specified pre-trained model. Now the next thing that I will be here doing as db.save underscore model, and I will give the path of db underscore faz underscore path. So let's understand the meaning of this code. When I'm writing here db.save underscore model and inside that I'm giving the faz path, it means that the created vector database is saved to a local directory which is specified by the db underscore faz underscore path. So this directory will contain the necessary files to load and use the vector database in the future. Now, after creating our vector database, what we will do here, we'll just write the main function. Alright guys, so let me put inside the function. So what does it mean here? So we are just creating the conditional block, and it will make ensure that the create underscore vector underscore db function is called when the script is run as the main program. So this means that if you, So this means that if you are executing this script, it will create the vector database using the specified settings. So it's time for us to execute it. So I'll just simply write here python code.py. And here you can see that it's giving an error because I have to just write here double equal to. Okay, let me just save it, and once again I'll just write here python code.py, and yeah, indentation issue is there. Okay, once again just let me write here python code.py, and on execution, okay guys, we were getting an error cause of indentation, and on execution we should get the vector database, but let me write here once again FAISS, it should be capital. Now let me save it and execute it. I'm writing here python code.py. Okay guys, I have used this db, but this db is the variable, right, in which these things were stored. So once again just let me save it and execute it. So okay, let me go to the terminal, and I will just once again go and python, and I will just write here code.py. Okay guys, so let's see why we are getting error. Okay, so here we can see that our function will be db.save underscore local. We have written here model, right? So let me replace it. And also, you know, this is the main class, right, of Python, so it has to be outside. Now if I'm executing it, let me save the file first, it's important. And if I'm writing here python code.py, and it will take some time, Okay guys, now you can see that we got a folder name as vector store, right? And if you see inside this, we are having a pickle file, right? That will automatically get saved with an index that you can see it over here in this folder. So what happens here, it will automatically create the embeddings for us and it should automatically create a folder, right? And it will save all the embeddings to the index of the metadata. So in summary, after understanding and having a proper implementation of this code, we got to know that this code reads PDF documents from a directory, splits them into smaller text chunks, converts the text data into a numeric representation that is also known as embedding, right? While using a pre-trained model. And it stores this representation in a vector database using the FAST library. So the database can later be used for various NLP tasks such as similarity search or document clustering. Now this is the coding implementation of the first part that I have given you the summary. Let's implement our model. So now what I will do, once again I will go on this Intellipaat chatbot and I will click on this file. I will just simply write here model.py. Now what I will do here, now coming to this model.py file, what I will do here, I will once again import the LangChain module. So this time I will be implementing here from LangChain dot document underscore loaders import py pdf loader directory loader, the same thing. Alright guys, now there is one more module that we're gonna implement here is from LangChain import prompt template. Now why we are importing here prompt template? See, importing a module related to prompt templates from a LangChain library includes tools for creating and using prompt template. Okay, so a prompt template is a predefined format for the input that can be used for various natural language processing tasks. So in general, when I am importing here prompt template, it will create and use prompt templates. We can do it, right? So let me write here from LangChain import prompt template. Okay guys, the next library that I have already told you about, that is langchain.embeddings, right? From langchain.embeddings, we're gonna import Hugging Face embeddings. Let me import some more module. Once again, I will just simply write here fast from LangChain.
Just a quick info guys, Intellipaat offers a data science course which will help you master Python, SQL, machine learning, AI and Power BI. Get a data science certification from IIT Empower, an innovation hub of IIT Madras. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your careers to new height. So visit the course page link given.
Okay guys, so we have seen how we have successfully generated the pickle file and it got saved with an index, right? So now we will focus on the main model, that is model.py file. Now let's see here the libraries. We have already seen the first libraries, right? How to load a PDF file. The second one is prompt template. If you want to create a prompt template or any template prompt, we can use this library. Third one we have already seen, right? Moving ahead, we are having from langchain.lms import C transformers. Okay guys, talking about this library is used to manage processing chains for natural language tasks. Also, it is used for the question answering from LangChain library. The next library we are having here from langchain.chains import retrieval QA. Now, this library is used for building question answering systems or retrieval based models. Moving ahead, We are having chainlet. As we all know that if you want a user friendly or a good user interaction, right, then this is the best to use. So it is a framework which is used for building chatbots or basically conversational AI application. Now, after this, what I will do, here you have seen that I have given the path, right? So I have defined a file path for the face vector store. Now this variable, that is df underscore face underscore path, stores the file path to the face vectors store, which is a directory where vectors are stored for efficient similarity search and retrieval. After this, I have created a custom prompt template. So in this custom prompt template, this variables define that it will be used for generating prompts in a question answer system, right? So the template includes placeholders for context and question variable. Here you can see that these are the placeholders, right? And this will be filled with actual content sharing during the question answering process. So when we are already giving our data, for example, the book brochure, what all courses the Intellipaat has, so at that time it can be used as question answering process. Now, here you can see that we have created a function with name set underscore custom underscore prompt, right? Now, this function creates a custom prompt template for question answering retrieval. It uses the custom prompt template string as a template and specifies the input variable as context and question. You can see that here we are having the input variable as context and question, and the template that is specified with the custom prompt template, right, that we have created here. Alright guys, so we have created a custom prompt template, we have set the custom prompt, now it's time to retrieve the data from it. So here you can see that I have created a retrieval QA chain, right, using the provided components and configuration. So these are the components and configuration. So here if you see, these are the three parameters, LLM, prompt and DB. Now what I am doing here, it takes in a language model LLM a custom prompt template which name is prompt here, right, and a vector store or retriever as DB. So this is nothing, this is a language model, this is a custom prompt template, and this is a vector store or retriever. Alright, now what will happen next, it will configure the chain with specific parameters such as retriever settings and prompt template, and it will return the configured QA chain. Here you can see that it will return our QA chain. Now after that, what we have to do, now once we are done with custom prompt template, setting the custom prompt and to retrieve the information from it, we have to load our quantized model. That is nothing but, I was talking about the model Llama 1, right? Llama 2 7B chat GGML. So we will load the model. Alright guys, and after loading the model, we'll specify the model name or path for the language model that we have already done here, and we will also specify the type of model which is llama here. Then here you can see that my maximum number of tokens, right, that is allowed during the text generation is 512 tokens. And here what does it mean by temperature 0.5? It means that here the temperature controls the randomness of generated text. Okay guys, now after this what I will do, so we got to know how to load the model. Now it's time to see that how this model function, right? So we will create a question answering QA bot. So here that's why I've written here QA bot, right? And after that what we'll do, we'll create an embedding object using a Hugging Face model for sentence embedding. Here you can see that I have already created a Hugging Face embedding object, right, for sentence embedding. Alright, next. So now what I will do here, we'll just load a local face vector store for document retrieval using the specified embedding. Here you can see that, right, using the specified embedding, I will just load a local face vector for document retrieval. Then I will load a language model LLM for generating answers. That's what here I am doing here. After that, once I have done with loading a language model, I will set up a custom prompt template for question answering. So this is a custom prompt which is used for the question and answering. Okay, moving ahead, I've written here retrieval underscore QA underscore chain function. It means I'm creating a retrieval QA chain for question answering using the loaded components. So this is all about this QA model function. Now, after this, we are having the output function. So in output function, we have created the final result as a function name for the user query, right? And we have initialized the QA bot by calling the QA bot function. So you can see that, right? We have repeat. So here you can see that we have initialized it with the QA underscore bot function. Now, once it is done, then we have used the chainlet. So in a chainlet code, we have used a decorator for handling the start of a chat session. Here you can see that we have used a decorator. Now we have created a function with the start name, and inside this function is executed when the chat session starts, right? And inside this also we have initialized the QA bot by calling the QA bot function. Do you getting any idea like the function? Like first we start with a custom prompt template, then we set the custom prompt, then we were retrieving QA chain, then finally we have loaded our quantized model, and then we have seen the model function and the output function, and now chainlet code. Okay guys, now after this what will happen at this stage? Once we have initialized the QA bot by calling the QA bot function, it will create a message to send to the user indicating the bot is starting. For example here, hi, welcome to Intellipaat bot, what's your query, right? Now this will send the starting message to the user. When I will execute this output, you will get to know, right? So let's wait and see the output. Here you can see that I have also written await msg.update. What does it mean? It means update the content of the message to provide a welcome message and ask for the user query. Okay. Once again, moving forward, this is c1.user underscore session dot set. Now let me give you an idea about this function. Here we have stored the initialized QA bot in the user session for future interaction. Okay guys. Now, second thing is that here you can see that this is a decorator, right? Decorator is used for handling incoming message during the chat session. So here once again I have created a function, and inside this function will be executed when a new message is received in the chat session. Then I have written here chan is equal to c1.user underscore session dot get. It will retrieve the QA bot from the user session. Next, if we are moving next, here you can see that I have created the object. This is the object, right? Async lang chain callback handler, right? So it will create a callback handler for asynchronous processing. Here you can see that we have already set the answer reach attribute to true. Next, we will use the QA bot to process the incoming message, and we will applying the callback handler. So here you can see that that's what even we are doing here, await chain dot a call. So basically we are using here chainlet for a better user interface. Now once it is done, then we want to get the generated answer from the response, right? So that's why I have created a variable answer, and inside that I have stored the result. And at last, once again, if you see this c1 dot message, okay, inside this it means send the answer back to the user. If you see this function cm dot message, it means it will send the answer back to the user as a message. So this is a basic idea about how to create a Intellipaat EdTech chatbot. Let me execute it for you. Okay, I am in the terminal. Okay, it's executing now. You can see that I got a chainlet file right here. So if I am writing here, like how to see your user interface, how to interact, how did you create a chatbot. So what I will do, I'll just simply write here chainlet run model dot py -w, right? Let me execute this. Let's see how our model is working. You can see that we are on the page of chainlet, and it's showing an error. Let me fix it. Okay guys, it's showing error cause we have to give the same file path, right? So I'll just give the same file path here. Let me copy this and okay, let me save it, and once you can see that it started executing now. So we have to wait for a few minutes even. So let's see how it is working. If it is 100%, you can see that it's asking, hi, welcome to Intellipaat. What is your query? If I go to this file, let's say 1.pdf. So as a learner, if I want to purchase this course, I will just check the criteria. Okay, what is the application process? So we should ask this question to this chatbot. Okay, what is the application process? What is the application process to enroll in data science and in artificial intelligence course? So I'll just type in data science and artificial intelligence course in Intellipaat. Okay. You can hide this also. If you go on this and click on the settings, just hide chain of thought, so you will not see any retrieval QA. So we have to wait for some time to see it. So guys, you can see that we got a generated response from our chatbot. That is, the application process consists of 3 simple steps, which include submitting their applications. An offer of admission will be made to the selected candidates and their application will be accepted upon payment of the admission fee. So if you see here and go application process, you will see that the text is not same, right? Now if I ask another question, okay, tell me what is the program curriculum, right? Or let's say what all projects that Intellipaat is offering. If I am writing it, what all projects does Intellipaat offer in data science course? You can see that it's showing that Intellipaat's data science courses offer a variety of real-time projects and case studies that cover various aspects of data science such as supervised and unsupervised learning, machine learning, deep learning, data visualization, data engineering, data governance. And you can see that even an example, right? Because we have already used the quantized model here. So it's already pre-trained large language model. So here you can see that the examples it's showing is some examples include predicting stock prices, detecting fraud in credit card transaction, analyzing customer sentiment, developing a recommend engine, building a smart home automation system.
I have one more announcement for you guys. For dedicated learners like yourself who want to make a difference in their career, for the first time, we at Intellipaat have decided to offer a straightforward 20% discount on our premium data science course, which is in collaboration with iHub IIT Roorkee. If you want to take control of your tech career and do something extraordinary, do visit this link in the description box given below and fill the inquiry form. Promptly, a team of course advisors will reach out to you to activate the offer. So don't miss out this opportunity.
So now, moving to the first question, what do you mean by the term normal distribution? Normal distribution, also known as Gaussian distribution, is a type of probability distribution that is symmetric about the mean. Here, mean, median, and mode are equal. Normal distribution appears to be bell curve in a graphical form. So here, you can see this graph. This graph is symmetry and also mean, median, and mode are equal. So now, let's move forward. So the next question we are having is, what is a skewed distribution? A skewed distribution takes place when one tail is longer than the other. Skewness defines the asymmetry of a distribution. Here, the data is not distributed equally on both sides of the distribution's peak. So basically, there are different types of skew distributions. The first one is the left skew distribution, and the another one is the right skew distribution. So in left skew distribution, it occurs when the long tail is on the left side of the distribution. That means here the mean is left to the peak, and also mean is less than the median, and the median is less than the mode. Along with that, left skewed distribution is also known as negatively skewed distribution. Coming to the right skewed distribution, it occurs when the long tail is on the right side of the distribution. It is also called as positive skewed distribution. Here the mean is right to the peak, and also mode is greater than median and median is greater than mean. Now, so let's see in the graphical form. Here you can see that this is a graph of left skewed, right? So clearly mode is greater than median and median is greater than the mean. So now let's see left and right skewed distribution in graphical form. So here you can see that it's a left skewed graph, right? Because the long tail is on the left side of distribution. Whereas if you are talking about the right skewed distribution, the long tail is on the right side of the distribution. In a left skewed, you can clearly see that mode is greater than median and median is greater than mean. Similarly, coming to the right skewed, here mean is greater than median and median is greater than mode. Now, moving ahead, the next question we are having, what is the difference between bias and variance? Coming to the bias, bias is a prediction error that is introduced in the model due to oversimplifying the machine learning algorithms. It is the difference between the predicted values and the actual values. So let's suppose you have created a machine learning model. So while creating a machine learning model, we'll get some predicted values. So basically the difference between the actual values and the predicted values is known as the bias. Now coming to the variance, variance occurs when the machine learning model performs well on the training dataset but not on the test dataset. So now moving to the next question, how will you handle missing values in data? So there are several ways to handle missing values in the given data. The first one is you can replace the values with mean, median and mode. For example, let's suppose if you are having any numerical column of let's say price and there are a lot of missing values, then you can replace it with the mean. Now, moving next, we are having the dropping the values. So let's suppose if you are having any column that is present in the data set and the null values are present more than 70%, then you can drop that particular column. The last is replacing with arbitrary values. So that means you can choose a random value without any reason or system. So the next question we are having is, what are the techniques used to detect outliers? So there are various techniques that are used to detect outliers. The first one is the box plot. So talking about the box plot, we know the length of the box is IQR, that is nothing but an interquartile range, right? And the minimum and maximum values are represented by the whiskers. So the whiskers are generally extended into 1.5 times of the IQR distance on either side of the box. Therefore, all the data points outside this range values are flagged as outliers. So the next technique that is used as z-score. So z-score is a parametric outlier detection method in a one or low dimensional feature space. This technique assumes a Gaussian distribution of the data. The outliers are the data points that are in the tails of the distribution and therefore far from the mean. So the last method that we are having is interquartile range. As we know, the formula of interquartile range is that it is quartile 3 minus quartile 1. Basically, it is the difference between the third quartile and the first quartile. So to detect the outliers using this method, we define a new range. So let's call it decision range, and any data point lying outside this range is considered as outlier and is accordingly tailed with. So the next question we are having is, what is the difference between overfitting versus underfitting? As we know that overfitting and underfitting are the two key problems in machine learning that decrease the performance of machine learning models. Now, coming to the overfitting, overfitting occurs when our machine learning model attempts to cover all or more than the required number of data points in the given data set. So you can see that in this graph, our machine learning model tries to cover all the data points, right? So now, what happens here as a result, the model gives inaccurate values in the dataset and all of these factors reduce the model efficiency and accuracy. The overfitted model has low bias and high variance. The more we train our model, the more likely it is to become overfitted. Told you, you can see in this graph, the model tries to cover all the data points. So it looks efficient, but in reality, it is not so. Because the goal of the regression model is to find the best fit line. But here, we have not got any best fit, so it will generate the prediction error. So now let's see how we can avoid the overfitting in model. So there are some ways by which we can reduce the occurrence of overfitting in our model. The first one is the cross validation. Second, we are having training with more data. So whatever the data is there, we can train it, right? So there are some ways by which we can reduce the occurrence of overfitting in our model. So let's see some of the ways. The first one is the cross validation. We can also train with more data. Then we can remove features too. We can early stopping the training too. Along with that, we can also apply regularization as well as ensembling. Now, after knowing what is overfitting, now let's see what is underfitting. So underfitting occurs when our machine learning model is unable to capture the underlying trend. So to avoid overfitting in the model, the feeding of the training data can be stopped at an early stage, causing the model to learn insufficiently from the training data. As a result, it may fail to find the best fit of the data's dominant trend. Underfitting occurs when the model is unable to learn enough from the training data, reducing accuracy and producing unreliable predictions. So let's back to the previous slide. So in underfitting, a model that is underfitted has a high bias and a low variance. For example, the following output of the linear regression model can help you understand about the underfitting. So here you can see that the model is unable to capture the data points in the plot, right? So now let's see how we can avoid underfitting in the model. So there are two ways in which we can avoid the underfitting in model. The first one is increase the model's training time, and the another one is the increasing the number of features. Okay guys, so the next question we are having is, what is the difference between supervised and unsupervised learning? Supervised learning is a machine learning method that uses labeled data to train models. For example, here you can see that how a player learns in the presence of his coach. So this is an example of supervised learning. Now, there are two types of problems that can be solved using supervised learning. The first one is the classification and the another one is the regression. So let me give you the example so that you can understand, right? So let's suppose we have an image of different types of cars. The task of our supervised learning model is to identify the cars and classify them accordingly. So to identify the image in supervised learning, we will give the input data as well as the output for that, which means we will train the model by the shape, size, color of each car. Once the training is completed, we will test the model by giving the new sets of car. The model will identify the car and predict the output using a suitable algorithm. So there are different types of supervised learning: linear regression, logistic regression, random forest, decision tree, etc. So now, after understanding supervised learning, let's see what is unsupervised learning. Unsupervised learning seeks to extract structure and patterns from the input data. It requires no supervision like supervised learning. Instead, it discovers pattern in the data on its own. Unsupervised learning can be used for two types of problem. The first one is the clustering and the another one is the association. Here you can see that in this figure, you can see that the model will train itself and divide the groups according to the most similar features between them. So let's take an example. So here we'll not provide any supervision to the model. We'll just provide the input data set to the model and allow the model to find the patterns from the data. With the help of a suitable algorithm, the model will train itself and divide the cars into different groups according to the most similar features between them. So the next question is, what is the difference between regression versus classification? So regression algorithms are used to predict the continuous values. Regression is a process of determining correlations between dependent and independent variables. For example, price, salary, etc. I'll give you the example of price versus experience. So let's understand by taking some examples. So let's suppose I'm having a data set which consists of one dependent variable and one independent variable. So the independent variable contains the years of experience, whereas the dependent variable contains salary. So as we know that as the experience of a person increases, the salary will also increase. So this is the example of the linear regression. So there are different types of regression algorithm: simple linear regression, multiple linear regression, polynomial regression, support vector regression, decision tree, random forest. Now, talking about classification, classification algorithms are used to predict or classify discrete values. For example, male and female, true or false. Even you can take the example of male. whether the mail is a spam mail or not spam mail, right? So let me explain you how does classification work. So let's suppose a computer program is trained on the training dataset, then it will categorize the data into different classes based on that training. Different types of classification algorithms are logistic regression, k-nearest neighbors, support vector machine, and kernel SVM. So guys, let's move further and see what is confusion matrix. So the confusion matrix is a table that used to estimate the performance of a model. It tabulates the actual values and the predicted values into a 2 cross 2 matrix. So now, let's see what is true positive here. So let me give you the definition of true positive. True positive denotes all those records where the actual values are true and the predicted values are true, right? So here you can see that the actual value is 1 and the predicted value is 1, and we got here true positive. Now, coming to the false negative, this denotes all of those records where the actual values are true but the predicted values are false. So you can see that this is false negative, where the actual value was 1 whereas the predicted value was 0. Next, we are having false positive. So in this, the actual values are false but the predicted values are true. So this is our false positive, where the actual value is false. So we are considering false as 0 and true as 1, right? So here we can see that the actual value was false and the predicted value was true, right? So after understanding true positive, false negative, and false positive, now let's see what is true negative. So this is a true negative. Here, the actual values are false and the predicted values are also false. So if you see, this is the true negative. Here the actual value is false and the predicted value is also false. So this is how the confusion matrix works. So now, coming to the 10th question, what is the use of p-value? P-value is the measure of the statistical importance of an observation. It is the probability that shows the significance of output to the data. We compute the p-value to know the test statistics of a model. Typically, it helps us choose whether we can accept or reject the null hypothesis. If the p-value is less than 0.05, then reject null hypothesis or else accept null hypothesis. Moving to the next question, we'll see what is a residual. So residual in a statistical or machine learning model are the differences between observed and predicted values of data. So here you can see that this is our best fit line, right? So these are the predicted values, whereas these values are the actual values. So the difference between the predicted values and the actual values is known as residual, right? So these are the residuals, right? Again, this is the point that we have done the prediction, right? These are the actual values. So the difference between the actual values and the predicted values will be our residual. The next question we are having is, what is dimensionality reduction? So the dimensionality reduction or dimension reduction is the transformation of data from a high dimensional space into a low dimensional space so that the low dimensional representation retains some meaningful properties of the original data. So let's take an example to understand in a simpler way. In machine learning classification problems, there are often too many factors on the basis of which the final classification is done. These factors are basically variables called features. The higher the number of features, the harder it gets to visualize the training set and then work on it. Sometimes most of the features are correlated and hence redundant. This is where dimensionality reduction algorithms comes into the picture. So there are various methods that is used for the dimensionality reduction. The first one is the PCA. So PCA stands for Principal Component Analysis, and the another one is the LDA, that is Linear Discriminant Analysis. So the next question is, what are the steps involved in machine learning? So the first step is data collection. Basically, we are defining the problem and assembling a data set. Then moving forward, we are having data preparation. So basically, we are preparing our data. Then we have to choose the model and train it, right? And after that, we will evaluate our model. So while evaluating a model, we will choose a measure of success. Also, we will decide on an evaluation protocol. The next step is parameter tuning. So basically, we are doing here scale up, right? Developing a model that overfits and regularizing your model and tuning your parameters. And at last, we'll do the predictions. So this is the way, and these are the steps that are involved in machine learning. Moving to the next question, what is pruning and the decision tree? So I will give you the simpler definition here. Pruning simply reduces the size of decision tree by removing parts of the tree that do not provide power to classify instances. Here, in this diagram, you can see that before pruning, there are a lot of sections of a decision tree, but after pruning, so here in this figure, you can see that before pruning, there are a lot of sections of the tree that are unnecessary, right? But after pruning, we have removed that particular section. Okay, so let me read the definition for you. Pruning in a decision tree is the process of removing the sections of the tree that are not necessary and redundant, right? So why do we use pruning basically? So why do we do pruning in the decision tree? So that our model performs better and gives a higher accuracy, right? What is RMSE in a linear regression model? RMSE stands for root mean square error. It is computed by taking the square root of MSE. MSE is where mean square error, right? RMSE measures the average magnitude of the errors and is concerned with the deviations from the actual value. RMSE value with 0 indicates that the model has a perfect fit. The lower the RMSE, the better the model and its predictions. A higher RMSE indicates that there is a large deviation from the residual to the ground truth. RMSE can be used with different features as it helps in figuring out if the feature is improving the model's prediction or not. Now coming to the question number 16, what is the use of elbow method in k-means clustering? So first we'll understand what is elbow method. Elbow method is one of the most popular methods to determine this optimal value of k. So what is k here? K means here the number of clusters. As I already told you, it is the most popular method for selecting k for the k-means algorithm, right? So to do this, you need to calculate the within cluster sum of squared error for different k values. So here you can see that it is written as WCSS, which is nothing but a within cluster sum of squared error, right? So it is described as the sum of the square of the distance between each data value and its centroid. You will then choose the value of k for which the WCSS error starts to become negligible. So here in this graph, you can see that this is the number of cluster and this is nothing but WCSS, right? And here at this point, this is your elbow. So the number of clusters will be 5. So the next question that we are having is, what is naive Bayes? So naive Bayes classifiers are a collection of classification algorithms based on Bayes theorem. It is not a single algorithm but a family of algorithms where all of them share a common principle. That is, every pair of features being classified is independent of each other. So basically you have to keep remember the assumption, right? So the assumption about each feature is that a feature should be independent and equal. So the next question is, what are the disadvantages of linear model? The first disadvantage is prone to underfitting. What does it mean? It means that it is a situation that arises when a machine learning model fails to capture the data properly. So this typically occurs when the hypothesis function can't fit the data well. Next, it is sensitive to outliers. So as you know that outliers of a dataset are anomalies or extreme values that deviate from other data points of the distribution. Data outliers can damage the performance of a machine learning model drastically and can often lead to models with low accuracy. Next, so the next thing is that you have to take the assumption of a linearity between features and the target variables. So here you have to assume that the feature is having a linear relationship with the target variable. Moving to the 19th question, when do we use normalization and standardization? So first we'll see what is normalization. So in normalization, it is used when features are of different scales. Along with that, it is affected by outliers too. So when do we use normalization? It is useful when we don't know about the distribution. Also, it varies from -1 to 1 or sometimes 0 to 1. Along with that, if you want to use it, then there is a scikit-learn library that provides a transformer called min-max scalar. So you can use this transformer and you can apply normalization. Next, we are having standardization. So standardization is used when we want to ensure zero mean and unit standard deviation. Unit standard deviation means standard deviation is equal to 1. Along with that, it is not bounded to a certain range like normalization. So in normalization, the scale was from -1 to 1 or 0 to 1, but here it is not bounded to a certain range. Next, it is much less affected by the outliers. So if you want to use standardization, Then there is a library scikit-learn that provides a transformer known as standard scalar. So this is all about normalization and standardization. Next question, explain hypothesis testing. Hypothesis testing is the process of testing assumptions for a population parameter on a sample of data. The process involves different hypotheses and statistical proof to accept or reject the hypothesis. Here, null hypothesis denotes as H0, whereas alternate hypothesis denotes as H1. Now, after understanding what is hypothesis testing, let's see the steps involved in hypothesis testing. So the first step is stating the hypothesis. For example, you can take the example of students with height more than 5 feet have BMI more than 20. Next, collect data, and after that we will see the evidence to fail or accept the hypothesis. Then we will test the hypothesis, and according to that we will take the decisions. So as I already told you, that let's suppose there is a student with height more than 5 feet and having BMI more than 20. So this will be your null hypothesis. So what will be your alternate hypothesis? Opposite of it. That is, students with height more than 5 feet do not have BMI more than 20. Now, according to the statistical test, will support the alternate hypothesis or null hypothesis, right? So this is how it works. So the next question is, what is the difference between training test, validation set and a test set? So first, we'll discuss about training test. It is a portion of our actual data set that is fed into the machine learning model to discover and learn patterns. So let's suppose that if you are having 100% values in the data set, so we'll take 70% of the values or 60% of the values to train that data set. Next, we will see about the validation test. So the validation test is used for hyperparameter tuning. And at last, we'll see what is test set. So the test set is used for the final evaluation of the best model. Moving to the next question, what are the different statistical techniques used in data science? The first one is the correlation. So it establishes and measures relationship between different variables. For example, if we are having data set, then we are having a lot of features along with the dependent variable. So it will show the relationship of features with the dependent variables. So next we are having regression. It allows identifying if the evaluation of one variable affects others. You can take the example of experience versus salary, right? Where one variable is affecting the other dependent variable. Next we are having time series. It predicts future values by analyzing sequence of past values. Basically, time series is used for the forecasting. Next, we are having the sentiment analysis. It determines the attitude of specific agents or people towards an issue, often using data from social networks. So the next question we are having, what is box plot? A box and whisker plot, also known as box plot, is used to show the spread and centers of a dataset. It is also used to detect outliers. It shows the dispersion of data across the mean. It summarizes the result as the minimum. So here you can see that. So this is a minimum, which means minimum value in the dataset excluding the outliers. Next, we are having first quartile. So this is the first quartile, or you can also say this as a lower quartile. So it means 25% of the data lies below the first quartile, right? So here, these are the 25% of the data that lies below the first quartile. Next, we are having median. Median is nothing but the midpoint of the data set. Half of the values lie below it and half above. So this is the median. Next, we are having upper quartile, that we say Q3, right? So it means 75% of the data lies below the third quartile. So here if you can see, this is our upper quartile, right? So 75% of the data lie below this quartile. Next, we are having maximum. So it means maximum value in the data set excluding the outliers. After that, we are having interquartile range. So this is our interquartile range, which is nothing but the length of the box, right? So it consists 50% of the data. Okay guys? Now, we will see what is whisker. So whisker is nothing but the upper and the lower whisker represent scores outside the middle 50%, right? So here you can see that we are having the lower whisker here, upper whisker is here. So this is all about the box plot. So the next question, what is SVM? So SVM stands for support vector machine. So what is the use of SVM? SVM are used for classification as well as the prediction task, right? So let us understand about SVM. It consists of a separating plane that discriminates between the two classes of variables, and this separating plane is known as hyperplane. The goal of the SVM algorithm is to create the best line or decision boundary that can segregate n-dimensional space into classes so that we can easily put the new data point in the correct category in the future. Right? SVM chooses the extreme points or vectors that help in creating the hyperplane. These extreme cases are also called as support vectors. So these are the support vectors. That's why we used to call the algorithm as support vector machine. So after understanding SVM, now let's see some of the kernels used in SVM. So the kernels that are used in SVM are polynomial kernel, Gaussian, sigmoid, and hyperbolic. So moving to the 25th question, what are a z-test, chi-square test, f-test, and t-test? Okay, so first let's see what is t-test. So we use t-test to compare the mean of two given samples. Also, t-test assumes a normal distribution of the sample. So when we have to use t-test, when we don't know the population parameter, that is nothing but mean and standard deviation, right? In that case, we use t-test. So after knowing t-test, let's see what is z-test. So a z-score is calculated with population parameters such as population mean and population standard deviation. So in a z-test, we assume the sample is normally distributed. So what is the use of z-test? So we use this test to validate a hypothesis that states the sample belongs to the same population. So in a simple terms, when we have to use the t-test as well as the z-test, so we will use the t-test for the small sample size, whereas we will use the z-test for the large sample. Coming to the chi-square test, or even you can say chi-square test, it depends, right? So we use the chi-square test to compare the categorical variables. A chi-square test fit for the two independent variables, used to compare two variables in a contingency table to check if the data fits. So let's see the definition here. So chi-square test is used to determine the difference observed and expected frequencies of a certain observation. Alright, so the last test we are having as f-test. So when we use f-test, so when the hypotheses of the interest are about the differences between population means. Okay guys, so the next question that we are having is, what is the difference between correlation and covariance? So now, first we will discuss about the covariance. So covariance shows the extent to which the two variables are dependent on each other. Basically, higher the number, higher the dependency. Now, what is the range of covariance? It varies from -infinity to infinity. Right? Now, moving to the third point, it is affected by scale of a variable. So now, let's see what is correlation. So, in covariance, it indicates the direction of linear relationship between variables. Basically, it shows the extent how two variables are dependent on each other, right? But in correlation, it measures the strength of two variables considering other conditions are constant, right? The next point is the range of correlation is from -1 to 1. So basically here we are having the Pearson correlation whose range is varying from the -1 to 1, right? Along with that, it is not affected by scale unlike covariance. Next question, what is cross-validation? In a simple term, cross-validation is used to validate models efficiency, right? So let me give you the formal definition of cross-validation. It is a technique for validating model efficiency that involves training the model on a subset of input data and testing it on a previously unseen subset of input data. In a simple term, it is a statistical method of evaluating and comparing learning algorithms by dividing data into two segments, one used to learn or train a model and the other used to validate the model. Next, we are having the cross-validation by k-fold. We can also do the cross-validation with one exception and many more. So this is the idea about the cross-validation. Moving to the next question, what is sampling? Mention some techniques used for sampling. So let me give you the definition of sampling. Sampling is defined as the process of selecting a sample from a group of people or from any particular kind for research purposes. It is one of the most important factors which decide the accuracy of a research or survey result. For example, if you want to take the sample that how many people are affected by COVID, so you will directly go into the population and out of that particular population you will take the sample about 1 or 2%. So this is nothing but known as sampling, right? So mainly there are two types of sampling techniques. The first one is the probability sampling and the another one is the non-probability sampling. So what is probability sampling? It involves random selection which makes every element get a chance to be selected. That's what the example just now I have given to you. So what are the different types of probability sampling? Repeat. we will see that probability sampling has various subtypes. We are having the such as simple random sampling, stratified sampling, cluster sampling, and many more. Now, after understanding probability sampling, let's see what is non-probability sampling. So non-probability sampling follows non-random selection, which means the selection is done based on your ease or any other required criteria. This helps to collect the data easily, right? So what are the subtypes of non-probability sampling? Convenience sampling, quota sampling, referral sampling, and many more. So this was the overall idea about sampling. The next question, what is ROC curve? So ROC stands for Receiver Operating Characteristic. It is basically a plot between a true positive rate and a false positive rate. So here you can see that we are having the graph of true positive rate and false positive rate, right? Also, it helps us to find out the right trade-off between the true positive rate and the false positive rate for different probability thresholds of the predicted values. So I will give you the idea about ROC curve. So let's suppose if the curve is closer to the upper left corner, the better the model is. In other words, whichever curve has greater area under it, that would be the better model. Now guys, moving ahead, what do you understand by random forest model? So random forest model is a combination of multiple decision trees. It combines multiple models together to get the final output, or to be more precise, it combines multiple decision trees together to get the final output. So now coming to the question number 31, what do you understand about a decision tree? So as we know that random forest is a combination of multiple decision trees, right? Whereas let me discuss about the decision tree. A decision tree is a supervised learning algorithm that is used for both classification and regression. The same goes for the random forest also. Here, each node denotes the test on an attribute and each edge denotes the outcome of that attribute, and each leaf node holds the class label. So here, if you see the diagram, this is the root node and these are the leaf nodes. Okay? And this is the edge. So moving to the next question, that is question number 32. What is boosting? Boosting is also a homogeneous weak learners model but works differently from bagging. In this model, learners learn sequentially and adaptively to improve model prediction of a learning algorithm. So let me give you some points about the boosting. Boosting is an ensemble model technique that attempts to build a strong classifier from the number of weak classifiers. It is done by building a model by using weak models in series. So what happens here? Firstly, a model is built from a training data. Then the second model is built which tries to correct the errors present in the first model. This procedure is continued and models are added until either the complete training dataset is predicted correctly or the maximum number of models is added. Right? So what is the uses of boosting? It is used to reduce the bias. As I told you here, each new subset contains the components that were misclassified by previous models. It is a way of connecting predictions that belong to the different types. Here, the models are weighted by their performance. Along with that, new models are affected by the performance of the previously developed model. What is bagging? Bagging is also known as bootstrap aggregating. So it is also a machine learning assembling algorithm which is used to design to improve the stability and accuracy of a machine learning algorithm. Right? So what happens here in bagging? It decreases the variance. Right? So bagging is used to reduce the variance of a decision tree. Along with that, it attempts to tackle the overfitting issue. So here every model receives an equal weight. Alright? Unlike boosting, here every model is constructed independently. Right? So this is the overall idea about boosting and bagging. Explain univariate, bivariate and multivariate analysis. So first we will see what is univariate analysis. So univariate analysis involves analyzing data with only one variable, or in other words, a single column or a vector of the data. This analysis allows us to understand the data and extract patterns and trends out of it. For example, analyzing the weight of a group of people. Moving next, we are having bivariate analysis. So here, it involves analyzing the data with exactly two variables so that the data can be put into a two-column table. For example, analyzing the data that contains temperature and altitude. Okay? Also, this kind of analysis allows us to figure out the relationship between the variables. Next, we are having multivariate analysis. Multivariate analysis involves analyzing the data with more than two variables. So here, the number of columns of the data can be anything, even more than two. This kind of analysis allows us to figure out the effects of all other variables on a single variable. For example, analyzing data about house prices, which contains the information about the houses, such as locality, crime rate, area, the number of floors, etc. Next question, what is recall? Recall tells you how many times the model was able to detect a specific category. In a simpler term, out of the total positive, what percentage are predictive positive? So let me give you the definition of it. It is a metric that quantifies the number of correct positive predictions made out of all the positive predictions that could have been made. For example, here you can see that this is a formula of recall, right? So recall formula is true positive upon true positive plus false negative. So basically out of the total positive, what percentage are predicted positive? Moving next, we are having precision. Precision is how good the model is at predicting a specific category. Basically, it measures the accuracy of correct positive predictions. So let's see the formula. So precision is equal to true positive upon true positive plus false positive. As I told you, basically it measures the accuracy of correct positive predictions. Also, the precision value lies between 0 and 1. Now, moving to the question number 37, what are the popular libraries used in data science? So there are popular libraries that are used in data science such as TensorFlow, SciPy, Pandas, Matplotlib, PyTorch, Scikit-learn. Let me explain you some libraries. For example, Pandas. Pandas is used for data analysis. Coming to the Matplotlib, this is a library that is used for data visualization, whereas Scikit-learn is a machine learning library. So moving to the question number 38, what is deep learning? Deep learning is a subset of machine learning, which is essentially a neural network with 3 or more layers. Deep learning is an advanced version of neural networks to make the machine learn from the data. In deep learning, the neural networks comprise many hidden layers that are connected to each other, and the output of the previous layer is the input of the current layer. I will give you the example of deep learning in a simple term. Deep learning teaches computers to do what comes naturally to humans. Along with that, it is a key technology behind the driverless cars, such that enabling them to recognize a stop sign, etc. So now, moving to the question number 39, what do you understand about linear regression? So when I'm talking about the simple linear regression, so there is one independent variable and there is one dependent variable. For example, experience versus the salary. So let's see the points here. So linear regression helps in understanding the linear relationship between the dependent and the independent variable. So as I told you the example of experience versus salary, as you are having the experience more than 3 to 5 years, your salary will be gradually increasing. Next, linear regression is a supervised learning which helps in finding the linear relationship between two variables. So here, one is the predictor or the independent variable and the other is the response or the dependent variable. So this is the basic idea about the linear regression. So now, coming to the last question, how to calculate the accuracy of a binary classification algorithm using its confusion matrix. So first of all, let me give you the definition of accuracy. So accuracy is also a metric that is used for evaluating classification models. So what is the formula of accuracy? Accuracy is basically the number of correct predictions upon the total number of predictions. So here, to calculate the accuracy, we need to divide the sum of the correct classified observation by the number of total observations. So when I'm talking about the number of total observations, so it will include true positive, it will include true negative, it will include false positive as well as false negative. The accuracy will be true positive plus true negative upon the total number of observations.
I have one more announcement for you guys. For dedicated learners like yourself who want to make a difference in their career, for the first time, we at Intellipaat have decided to offer a straightforward 20% discount on our premium data science course, which is in collaboration with iHub IIT Roorkee. If you want to take control of your tech career and do something extraordinary, do visit this link in the description box given below and fill the inquiry form. Promptly, a team of course advisors will reach out to you to activate the offer. So don't miss out this opportunity.